takers, it's glorious moment for me to extend a warm welcome to all of you to the third day of this International Conference on Renewable Energy 2022, organized by Center for Renewable and Non-Conventional Energy Resources, University of Rajasthan, Jaipur. This conference gave us an opportunity to refurbish knowledge and interact with esteemed delegates on mutual interest from all over the globe. Moving on further, the success of any event is determined by the inspiring presence of a great personality who lends a charisma to the occasion. Likely, we are extremely privileged to welcome our first speaker of the day, Professor Kanchan Mondal. I want to give a brief introduction of him. That Professor Kanchan Mondal presently is associated with School of Mechanical, Aerospace and Material Engineering, Southern Illinois University, Carbondale as director, and also acting as a professor, School of Mechanical, Aerospace and Materials Engineering, Southern Illinois University, Carbondale. His research and specialties are in clean energy production related materials and processes, energy efficiency, catalytic processes, gasification processes, combustion processes, separation technologies, hydrogen storage materials, flue gas cleanup, membrane technology, photovoltaics, electrocatalytic processes, environmental remediation, nanomaterials, high density recording media, supercritical fluid technology. He has published 5 book chapters, 86 research articles in peer-reviewed journals, and also granted $13.5 million grants for 36 funded projects. I welcome you, sir, for the talk.
Hello.
Thank you for that introduction. I'm still trying to upload the file to your.
You are unique, and I'm happy that you are here this morning to motivate young people. Your work is very fantastic. You are reducing carbon, working on alternative energy sources, hydrogen production. You are a unique personality, and I hope that your lecture will motivate them. I'm really thankful to you that at the short notice you agreed to us. You are you have very good association with our center, and you have visited a couple of times to our center for different conferences. It will be very honor to have you this morning. Thank you.
Thank you, Professor Jen. It has been an honor for the last 15 years that I've known you. We've had a lot of common interests going on.
हाँ जगनलाल जी, हम डाल रहे हैं, गूगल ड्राइव ढूंढ रहे हैं, हमको गूगल ड्राइव दिखा अभी, so I'm just trying to put it on the गूगल ड्राइव में हम डालने का कोशिश कर रहे हैं, ठीक है? Just give me save as desktop.
Are you able to now see this particular desktop of mine?
Yes, sir, your slides are visible.
Okay. Let me try to put it on presentation mode. Okay. Thank you again, Professor Jen, for inviting me to talk to you. I always enjoy every opportunity that I get to interact with you. My specific talk is towards net zero carbon emissions, because that's one of the key things that the energy sector is dealing with right now, which not only is related to the energy sector, but overall GHG emissions for climate change. The parts that I'm going to talk about more is the electricity and transportation sector, because that's what I am connected to. I do research in those sectors. To begin the talk, I want to talk about three key issues that affect the global society. One is energy, the second is food, and the third is health. I believe all of you will agree that they are interrelated and they are very critical for our prosperity and happiness. And all those three take away certain resources that we have, the finite resources that we have on this earth. So if we put pressure on one side, one of them, something else gets hurt. And we have a tendency of having a tunnel vision. So if you look out here, people are talking about fracking to get natural gas because that's one of the largest source of untapped energy, according to the person. But it might cause earthquakes and pollute the groundwater, but still it is a large resource, while they miss the big sun right in the background. So that's one of the things that we tend to have as individuals, as scientists. We tend to have a tunnel vision on what we are working on without looking at other potential solutions. And that's what I want to talk about, is that there are many solutions that to our GHG, curbing our GHG emissions, so that we do not have a knee-jerk reaction just to stop something and go for a solution that might end up having other problems down the road. So if you look at the global carbon flux out here, I want to point your attention towards the red numerals. So because of human emissions, we have around 9 gigatons of carbon that we emit in excess of what normal earth processes cause. Of those 9, 3 are taken up by the plants. If we do not cut anymore, if we do not go for any more deforestation, we can get 3 gigatons taken up by the biosphere and 2 gigatons taken up by the ocean, which leaves us with 4 gigatons, which roughly, if you look at it, if 5 gigatons out of 9 gigatons is taken off, what we really need to do is improve our efficiencies of our current systems. Just if we are able to double those efficiencies, we should be able to meet those. If we are not able to double all the efficiencies, at least we get certain alternates, that should help us too. So those are my initial comments, that the carbon cycle is essential. We cannot have our biosphere without carbon. And essentially fossil fuels are sequestered carbon, and that without anthropogenic activity, there is a greater amount of CO2 uptake than we are going to produce. So the human activity is what causes that imbalance. CO2 production is roughly 4 times greater than that can be cycled. So we have to somehow meet that 40%. And I keep on saying this, that we need to reduce it by the 40% instead of completely going renewable, is because not every country is, or not every locality is geared up, has the capabilities of meeting those, meeting 100% renewable resource. It would be great if we could have non-carbon and electricity sources, but not every locality can meet that. And that's why I keep on talking about, we need to look at, not only do we have to go to that mix, but also look at other options. The climate change is here, we cannot argue about it, and we need to take the action now. But any action we consider, we should look at both the long-term and the short-term implications. And I'll talk later on about things like, if you go in for hydropower, the people whom you dislocate to put in a dam is going to be affected disproportionately compared to the benefit that they might get in the short term. So we need to consider those issues as well before we go ahead and take action. So there are four steps we can do. One is stop fossil fuels completely. not everybody can fulfill the demand, energy demand. The other is capture the CO2 and sequester it. Capture takes energy, CO2 also sequestering requires energy, and there is no useful return. One of the big places we are looking into is how do we utilize. Issue again is CO2 is too stable and needs energy. So net, we are actually not creating new, we are not extracting extra energy. So we have to use some kind of renewable source to be able to convert that CO2. And the last one is reduce. I'm a big proponent of that. Although I also believe down the line, we have to move towards renewable energy. And to identify for locations that have issues with being able to go 100% renewable, one of the things I like is something called carbon emissions pinch analysis. What it essentially does is it tries to look at different energy sources and sees how much CO2 it emits per unit megawatt or per unit gigawatt, however you want to consider it. So the slope of those lines that I'm going to show right now indicates if it is more energy, if it is a lower GHG producing source or a higher GHG producing source. So the first one is renewable, and they have essentially only a fixed CO2 cost. Nothing comes during its operation. So it's not zero, but it does not continue increasing as you use that resource. Then essentially, then natural gas comes in. And in that natural gas, you can have multiple technologies, and each of them might be generating different CO2s per the energy it delivers. Then comes oil, then comes coal. Let's say this is 2021. Around some years later, if we wanted to cut our GHG emissions by a certain amount, which is what the whole Paris Accord is about, and the 2050 limiting the CO2, limiting the temperature to 1.5 degrees is all about, then we want to figure out how much renewable source we want to add. If we have an improvement, we increase the amount of resource that we have in any locality of the most efficient fossil fuel, we'll see that even then we are not going to meet those, not only not going to meet those limits, which is shown out here by the second dotted line, but we actually, for meeting the energy requirement, we are actually increasing the amount of GHG emissions. So what it tells us is that we have to introduce renewables no matter what. But how much renewables is okay to introduce without affecting our day-to-day life? So if you are able to introduce certain amount, which if we increase that and move the rest of the fossil fuel line onto the right, we see essentially that we can remove most of our coal, but we still don't meet the requirement. So for that, we have to introduce more CO2, so and to find more renewable, and to find out how much renewable we need, we move that the rest of the line to the right and see the amount of renewable we need for that locality. So each locality should be able to do some analysis of their own and say how much CO2 they need to meet those carbon emissions requirements that does not disrupt the local population's way of life. So there are two things. Significant CO2 reduction can be achieved by inducing a shift in technology and fuel choice. That's what I showed in the second line that we had drawn. And regulation and carbon taxation can drive businesses to reinvent themselves to basically move towards more renewable energy. The options that we have are improving energy efficiency. That's what I told. If we can increase all of them by 40%, it would be great. Switch fuels to more renewables. That's what most countries are targeting. Non-renewable like hydro and nuclear, go for those. Carbon capture and sequestration, some of the power industry is already looking at it. Carbon capture and utilization. And we can switch technology for end users, such as electric vehicles. And finally, reduce our demand, which basically means we do not use as much unnecessary energy and as before. So we'll talk about a little bit about the zero carbon electricity and say what US is doing in this area. This is one of the single most important step towards decarbonization, since that is the ultimate goal. We can have two sets of zero carbon electricity mix. One is direct, which includes renewables, onshore wind, offshore wind, solar, hydro, fossil, and then we can have fossil fuels with carbon capture, utilization, and sequestration, and we can have nuclear. Amongst them, the renewables, we need to somehow store the electricity. We can, because they are intermittent, as we all know. So we need to find a way of storing that energy. So we need a grid electricity storage system, which may be electrochemical. That's where a lot of stress is effort is going. A large and old system, which is mechanical. That is also like, for example, pumped hydro can be a storage system. We can store it as chemicals, or we can store it thermally, like we do right now in CSPs, the concentrating solar power stations. The other indirect ones are using zero carbon fuels, and then using those, producing zero carbon fuels, and then on need, converting it to electricity. Those zero carbon fuels can also lead to green synthetic fuels, such as synthetic methane, synthetic methanol, some hydrocarbons. I'm going to talk about some of the green synthetic fuels as well. So why do you think renewables is the matter of choice for almost every country who can afford to do that? Number one is that there is a large social acceptance of the renewable, because in social media, amongst people, they believe that renewables do not cause major trouble in terms of clean air and clean water. On the other hand, if you go for nuclear, people have concerns over accidents and weapons infiltration. If you go for bioenergy, there are two things that affect it. One is excess bioenergy means you need that space for cultivating those crops. It leads to both ecosystem degradation as well as competition for food. The third one that we were talking about is power production with carbon capture and sequestration. People are not completely sold on it, even though many operations are still viable, are working right now, are in use. The main issues that they have is technological issues. For example, out here in Illinois, they do use certain drones to measure if any CO2 is leaking out from some of the sites. Land use obstacles, you cannot, you have to put in pipelines for transporting it, and getting permission for the pipelines and not affecting the path that it carries the CO2 from has become an issue. But the biggest issue for CCS still is the levelized cost of electricity, that when you do that, you don't still get competitive electricity prices. The key technologies that we have in terms of renewables is mostly solar and onshore wind is what US is looking at. Offshore wind is an area that the government is trying to focus on. And apart from solar PVs, concentrating solar power also seems to be a big part of US government's Sunshot program. As far as electricity storage is concerned, like I said, pumped hydro and batteries are the key technologies governments are still looking at. But within batteries, we have lithium-ion issues, primarily because of the cost and its supply. Its supply can be disrupted because, again, lithium in the concentrations that you need is not well distributed across the world. And then the second part is, once these run out of their useful life, they are currently being dumped. So we need to have a way of recycling the lithium from there rather than filling in landfills. Within the United States, the largest source of clean and domestic power is still hydropower. There are 101 gigawatt of generating uh, capacity, and there's a plan to move it to 150 gigawatts by 2050. What it has been calculated is that around 5.6 gigatons of CO2 can be reduced by 2050 by this move, which saves around $209 billion of damage due to climate change and $58 billion due to air pollution healthcare costs. Once again, putting hydro, that's why I go down to all the way to the bottom. If you see, we must ensure equity and justice during deployment, because yes, it does save a lot of money in terms of air pollution, healthcare costs, and climate change. But it also impacts immediately the people whose lives are going to be disrupted due to the deployment of that hydropower. Overall, it can generate 16% of world's electricity. And if all the world's water resources were used, we could only triple it, which means that hydropower is not the single source that can meet all our needs. Wind power is the second largest renewable energy producer. The maximum potential is roughly around 120,000 gigawatts, is around 11 times the projected global demand. So wind power can meet those requirements. Amongst the wind power, if you look at it, the largest onshore turbines produce 4 to 5 megawatts, whereas the largest offshore turbines can go up to 14 to 15 megawatts. So there is a drive towards going for offshore turbines because it not only limits issues on land. In fact, in Illinois, where I am from, a lot of the windmills are in places where land can be cultivated. So essentially, those areas are being affected because of the wind turbine being installed there. The farmers get good money for locating the wind farms there, but the long-term issues with the land getting degraded has not been considered. As far as offshore turbines are concerned, the biggest challenge is to develop resilient structures that can withstand the nature's forces, which comes down to solar energy, which kind of is my favorite renewable. The US government has the Sunshot program, and it expects that if it is deployed properly, around 1.5 million jobs can be created, which would be helping some of the jobs that are going to be lost in the coal industry and the oil and natural gas industry. The National Renewable Energy Laboratory study found that 40% of the nation's electricity can be supplied by 2035 and 45% by 2050. On the right-hand side, if you see the deployment, around 16,000 gigawatts of power is going to be supplied by 2050. And if you look at the entire decarbonized energy system, which basically means that not just electric power, but other things that can be done with the electricity that is generated, that's around 3,000 gigawatts by 2050. But we still need aggressive cost reductions, and the sunshots showed that we might be able to achieve it. And I'll show you some of the numbers in the slide next after this. The National Renewable Energy also collects good information on improvements in cells. One of the things which I say is that we need to be technology agnostic, because if we buy into only one technology, when a new technology comes in, we are not ready to move to it as quickly. So if you look at the silicon has been there for a long time. Then they have tried to improve on it by including some of the thin films, which can have multiple absorption zones. Furthermore, they are looking at also concentrating solar photovoltaic cells, which increase more than 1 sun. Those have high conversions. But if you look onto the right, and there's this picture of perovskite tandem cell, SI tandem cells, they have certainly jumped up to the conditions where it meets some of the multi-junction cells itself. So having given that, it's much easier to probably deploy that, has longer term stability. And then if you put it on a concentrating system, then you will start having. Have I gone over? Then one of the things that has enabled the deployment of more and more solar panels within the United States is its cost. If you look at that, at the cost per dollar per watt, it has consistently kept on going down as the PV module shipment. So this the U.S. government NREL Sunshot program, they looked at the 2010 cost, and then they put in a 2020 goal initially. So in 2010 for residential, it was 52 cents. For commercial, it was 40 cents per kilowatt hour, and for utilities, it was 28 cents. They put in a target and at 2020 for 10 cents for residential, 8 cents for commercial, and 6 cents for utility. The utilities achieved the 6 cents by 2017. The residential and commercial are still not there. We haven't seen the latest report yet. At least I haven't seen the latest report from 2020 numbers. But now they have moved on to 5 cents for residential, 4 cents for commercial, and 3 cents for utilities. And within that, by reducing that by half, from roughly 6 cents in 2020 to 3 cents in 2030, they are going to double the capacity with half the cost. And when they introduce battery storage to it, the amount that they can deliver is going to be even higher, at 3 cents per dollar. Concentrating solar power plants. Also, the Sunshot program tried to look at it, where it was 21 cents per kilowatt hour in 2010, and they wanted to get it down to roughly around 10 cents per kilowatt hour for peak hours, and at the base load to around 5 cents. They were able to get close to that. They were able to get down to 6 cents, but not yet to 5 cents. But there's still 8 more years to go before that 5 cents needs to be achieved. So I'm going to share a little bit of my work out here. Because rare earth and critical materials are not universally distributed. For right now, China is the sole producer of some of the materials that we need for solar and other renewable energy needs. So how can we find those within our resources to stabilize the supply chain? DOE has been looking into coal as a potential source of rare earth elements. But if you what we have proposed to the DOE is that not just look at individual rare earth materials, but create a full value chain. So the number one is getting graphene quantum dots out by a particular way of processing, which will not only get the graphene quantum dots, but also gets some amount of liquids, which are aromatic in nature or liquid fuel in nature. I'll talk to you about later on how CNTs can be synthesized. We have the capability of synthesizing CNTs with specific aromatics, but the mixture that is going to come out, we can still create alignment, multi-walled carbon nanotubes, which can be used as capacitors or catalysts. The remainder of the residue can be used for making electrodes. And then the mineral matter that is left from that whole system can be then now extracted with as rare earth nitrides because of its magnetic capabilities, and carbides, along with alumina, silicon carbide, and iron carbide. So this creates a whole range of value production. And the cost of it, if you were able to just get graphene out of it, you would probably recover most of the cost. So, for example, in 2019 price, when I did this analysis, if I put in a gram of coal, it would cost around 0.0042. I would be recovering 40 cents by getting 1 milligram of graphene quantum dot. But we can also get the rest of the things, which is 6 cents out of, from the organic liquids, around 16.442 cents from the multi-walled carbon nanotubes, and from carbon alone we could get we would get around 0.0187 cents. So you can see we could easily recover the money for the coal without burning it at all. So in terms of other research needs, apart from trying to stabilize the chain, the supply chain, we also need to improve on our battery electric vehicles. We need to find more end users for direct electricity, including heat pumps, which we already have, electric cooking we already have, but the direct reduction of ores, only aluminum and a few others go through that. Most of them still use fossil fuels. We need to figure ways of using direct electricity or direct zero carbon fuels for that. And there's a definite need to expand and upgrade interconnected smart grid power, because whatever we do, we need to be able to respond to the supply issues as well as the demand as it goes for as we go forward. Dr. Jen, do I continue, or I think I'm almost there on the time? Can't hear. Within the hydrogen supply chain, this is something I always talk about, as no matter what you look, you have to look from the starting to the end. The supply chain, we know we can get it from water and hydrocarbons. The separation can be, the processing can be thermochemical, which is well known, but it can be electrolysis, which is well known, but there are a lot of improvements that need to come in. It can be photochemical or it can be biological. The distribution of pure hydrogen is still an issue. It is the longest and the largest would still be distributed through pipelines, and they need to be improved. Physical storage for short usage or in vehicular usage, those need to be improved significantly, not only in terms of capacity, but also in its round trip energy consumption.
Sorry to interrupt you, sir. We have 5 more minutes, so you can complete your presentation.
Yes, thank you. And that's what I was asking. So I'll go forward and go to almost to the end of the presentation to say, so in summary, what I wanted to say is that what we need to do is we need to ensure that CO2 production rates for meeting the global demand is less than 4 gigatons per year. And that's what we need to focus on. Decarbonizing the electricity sector is still the lowest hanging fruit because it does good not awareness, but uh, good politics, as well as there is a lot of development that leads us to believe that we can decarbonize the electricity sector. But to decarbonize it, we need to switch to zero carbon electricity. We need to develop technologies that use electricity in industrial and chemical sectors, because that's the part where reduction of ores or conversion of chemicals where you need heat or some way of providing the energy for the reactions to take place. We need to develop energies that use electricity or zero carbon fuels and its derivatives for transportation. We already have electric vehicles out there. There are a few fuel cell vehicles and they need to be improved. But the biggest thing is that we do not have anything that are hydrogen vehicles yet. And we do have hydrogen vehicles, but not to the same extent. And it has not penetrated enough like the electric vehicles. That needs to be looked into if hydrogen is to become a serious competitor. We need to improve efficiencies in existing technologies. That itself can reduce some of the GHG emissions. New and more efficient, and we need to combine with renewable carbon sources to be able to achieve those. And finally, we need to use comprehensive global solutions rather than one solution at a place. So to give you an example out here, a few days back, there was a report from California in which they are composting, they're collecting compost from, asking people to separate their garbage into compostable materials and non-compostable materials. And by doing so, they say that they can annually reduce emissions equivalent to removing 100 million gas-driven cars. So you can see there are other solutions out there too, which needs to be implemented along with just changing the way, not the way, but the sources and making it more expensive. Well, whenever we do want to, whatever we do want to implement, we need to ensure the safety, security, and justice for all. And by that, we mean we need to see what is the long-term safety issues, what is the security issues in terms of supply, and are we being just to all by implementing these changes? Thank you.
If there are any questions for Sir, you can ask right now.
Hello, Professor Mondal. I want to have some information because your lecture giving me a feeling that America is very soon going to shift to renewable energy. Any comment on this?
Well, not completely, but yes, this current government has put in a lot of political weight into going for 100% renewable. So two places. One is the overall United States itself. They are looking to decarbonize as much as possible by 2050. And the state that I live in Illinois, they are looking to do so by 2035. They are even more aggressive in changing over to renewables. And what state has 50? Go ahead.
Very interesting. Zero carbon electricity.
Yes.
Is it possible?
Like I said, not every place it is possible. And even within. Now, what people mean by zero carbon electricity is during its operation. It doesn't mean its life cycle. One of the key things that one has to look into is what is its life cycle greenhouse gas emissions, not just when it is operate, excuse me. So for example, in a windmill, putting in that kind of structure, those high structures require a lot of concrete and other structural materials. They all currently produce GHG in its production. So that source material carbon dioxide emission needs to go into those calculations. They cannot say that that is zero emission. All they are saying is zero emission during the operation of that that technology. So solar cells, when it is running, it is fine. But what it is also hurting, like they are in a number of fields where in the Midwest, where one can cultivate it, but they are missing out on that cultivation, which means there isn't enough of GHG or CO2 that can be picked up by the vegetation. So one has to account for those things too. So to answer your question, there is always a consequence, but not everybody looks into it.
Thank you. Thank you so much. Thank you very much for your fantastic talk. It seems to me that America is leading in renewable energy. That's fantastic.
Yeah, the National Renewable Energy Technologies Laboratories is putting in a lot of faith into it.
So nice of you coming to the talk.
Thank you for having me.
Thank you, sir, for thought-provoking presentation. We are grateful to have you with us as our guest speaker.
Thank you.
Joining with us today is Dr. Dinesh Topwal. Dr. Topwal is Associate Professor at Institute of Physics, Bhubaneswar, India. He is working in interdisciplinary research areas ranging from innovative studies of the basic properties of condensed matter system, which includes investigating the electronic structure and magnetic properties of various thin films, nanoscale systems, and strongly correlated systems. His research interests also extend to various advanced functional materials which have potential technology applications. He has published around 70 research papers in high impact factor journals from 2000 to 2021. Today, Dr. Topwal will be delivering his talk on new generation of photovoltaic material, understanding the fundamentals. We are honored to have you here with us, sir. You may start with your presentation. Over to you.
Thank you very much. Can you just allow me to share the screen? I want to try it once more. It says host disabled participant screen sharing. So I'll just try to see. Okay, you are doing on my behalf. That's good. Let me just
share it. We can.
I would just okay. That's fine.
Okay.
Let me enlarge this guy. Okay. Thank you very much, and good morning to all of you. First of all, I'd like to thank the organizers of this meeting, especially Dr. Jagannathan, for giving me this opportunity to share my work at this elite forum. In today's scenario, as our previous speaker has pointed out, the importance of renewable energy cannot be debated any further. And in that context, this conference is well timed and is well represented in terms of the topics covered. So today I'm going to talk on, let it be on the slide 1. I will tell you when it goes to the slide 2. Okay. So today I'm going to talk on new generation photovoltaic materials and its fundamentals especially. And it's very important to understand the fundamental issues involved here. Excuse me, can you just go to the slide 1 itself? I will let you know when to go to slide 2. Okay, the slide before itself is fine. So based on the topic of my discussion or presentation today is new generation photovoltaic materials, understanding its fundamentals. And it's very important, as I said, to understand the fundamentals, because before commercializing, it's you need to know about the system very well. So the topic which I am covering under this new generation photovoltaic materials is organic inorganic halide perovskites, which came into limelight about 10 years back, and they are excellent candidates for solar cell application. Okay, this is the plan of my talk. I'll just tell you about some introduction about these systems, some fundamental issues which need to be addressed, and I will address one fundamental issue here, that is the phase separation scenario in this system. Okay, next slide, please. Next slide. Yeah. So to understand why hybrid perovskite-based solar cells become so important, let's look at this plot. This plot was also shown by the previous speaker. It's quite a busy plot, but what it basically tells us is an efficiency of various solar cell technologies evolved over the period of the years. Here, the x-axis is the efficiency, whereas y-axis is the efficiency, and the x-axis is the year in which this efficiency was developed. So I would like to take your attention to the plot marked in blue here. Can you click next click? Just a click. Yeah, that's all. So I would like you to take your attention to this plot marked in blue inside this blue ellipse, where you see this is for the commercially available silicon solar cell and its journey over the last 45 years, where the slope of the ellipse tells us roughly the rate at which the efficiency of those solar cells have evolved, right? So you see in year 1985, the efficiency of silicon solar cell was close to 20%, whereas now it's close to 25%. So just 5% increase from 1985 to 2020, whereas a new technology of hybrid perovskites have come into the market now, which just last 10 years, where this red ellipse shows the rate at which the efficiency of these new solar cell materials have increased, and they have they have almost the efficiency of these new generation solar cell material is almost same as that of the silicon solar cell now. So next slide, please. Now the question is that if both silicon solar cell and this hybrid solar cell have the similar efficiency, then why do you choose this hybrid solar cell? So the answer to this question lies in the basic process of making the solar cell. Here, these hybrid perovskite solar cells are generally grown by the solution-based technology. What it means is that this is a very simple process available in most of the chemical labs. Just you require a beaker, some solution, or a spin coater, and so on. And you can cast the film directly out of solution at room temperature or at moderate temperature, say at 100 degrees Celsius or so. Unlike silicon solar cells, which can be made at much higher temperatures, like 1000 degrees. So that's why these technology or these films which you grow are more economically viable. Now to understand this, so this is the typical solar cell made out of these hybrid perovskites, where FTO and gold are two electrodes, and we have this hybrid perovskite absorber material in between, and you have a hole transport and an electron transport material, which is TiO2 layer at two ends of this absorber layer. Now, there might be few students as well, so I'll just, in 2 lines, I'll tell you the basic principle of how the solar cell works. So when a light falls, so on the extreme right, you can see the plot here. When the light falls on the sample, the electrons from the valence band, they get the sufficient. If they get sufficient energy, they jump to the conduction band, right, leaving a hole in the valence band there. And this electron, which has gone to the conduction band, then drops down to the bottom of the conduction band, whereas the hole which was created in the valence band floats at the top of the valence band. So this is how the electron hole pairs are formed when the light falls, and these electrons and these holes are then taken out through these hole or transport layers, through the electrodes, which is gold and fluorine doped tin oxide in this case, and thereby recording a photocurrent here. But this particular material, this hybrid perovskites, are really a wonderful candidates for this application, because these electron and holes can travel a distance of hundreds of nanometer or tens of microns before recombining. Apart from that, the band gap of this material is at a very sweet spot, 1.6 eV, which is in the in the solar spectrum, visible part of the solar spectrum. Absorption coefficient is very high, 10 raised to power 3 to 10 raised to power 4. Open circuit voltage is very high. Okay, but okay, next click, please. But there are certain limitations to this technique as well. No, there are certain limitations that it is something that it is still a new technology, and you require these compounds are still a little unstable. They are sensitive to moisture, but then people are working on it. And as I said, it's just a few years, only 4 to 5 years. So it's a long way to go. Now, let us understand a little basics about these compounds here. So hybrid perovskite, they have a structure of ABX3, where A is, it can be a methyl iodide, MaCH3NH3, something like that. B could be lead or tin, and X side could be chlorine, bromine, and iodine. And this particular complex generally undergoes a crystallographic phase transition with temperature. So what happens at higher temperature, this molecule, the Ma molecule, rotates itself in all the directions with equal probability, presenting itself as a sphere. And as you lower the temperature, and that's why you have a cubic crystal structure. But as you lower the temperature, this molecule aligns itself along a certain direction, right? And thereby this the PB lead octahedra gets distorts, and the crystal symmetry is lowered from cubic to tetragonal to orthorhombic, as seen from the crystal structure, from the XRD, that at 375 Kelvin it is cubic, and then 250 it is tetragonal, and then orthorhombic. Next slide, please. Okay, next. So now let's talk about some fundamental issues about this particular compound. Apart from the commercial limitations, there are some fundamental issues which also need to be addressed here. For example, the orientation of the molecule. As I said just a few seconds before, that the molecule inside it, the CH3NH3 molecule, orients itself along a certain direction as the temperature is lower. That means the compound would then present itself as a ferroelectric material, because this molecule is a polar molecule. But then there are many measurements which are done, and sometimes it is found to be ferroelectric, sometimes it's found to be paraelectric, and you can have a look at the loops, what you're getting. It's a very strange type of loops you get. Also, from the crystal structure point of view, still no consensus have been achieved on this, how, in some cases, it crystallizes in polar space groups, which means it is ferroelectric in nature, whereas in other cases it crystallizes in a non-polar space group, which suggests that it is not a ferroelectric in nature. So there is a lot of debate which is going on in this case. Okay, next slide, please. So, and also another thing is that the dual emission in these compounds. So when you try, one is trying to make a single crystal film, a solar cell, what one grows is a thin film. And it is observed that in case of a thin film, you get a PL peak, which is a single PL peak, as it is written here, PL on thin film. You get a single peak here. But when you make this compound in a single crystal form or in a polycrystalline form, as it is shown in the next thing, this PL on powdered sample, you see two peak structure there. So there was a lot of debate in the literature telling what these two peaks are. And based on the lifetime of measurement of these two peaks, it was very well established on, people believe that it is the surface and bulk effect, because the lifetime of these two peaks are very different. But then we performed measurement on a single crystal sample. We took a single crystal sample, shined light on one side, and tried to collect the light from all other phases which is coming out. And we found that along 0, 1, 1 bar plane, it's always the peak 1 which comes, whereas along 1, 0, 1 direction, it's always the peak 2 which we get. So irrespective of wherever you shine the light from. So this suggests that it is not a surface and bulk effect. Both these peaks are actually related to the bulk, and we believe that it can only be because of the orientation of the molecules, this A site molecules in there. Okay, next click, please. And for that matter, we replaced MA by FA, and we see that here too on the blue plot which is there, we get two peak structure. But in the case when we replaced it with the cesium ion, which is a spherically symmetric ion, we get a single peak. So which again is a confirmation of our thought that it is the rotation or the alignment of these molecules in that cage, which is causing many properties, various different properties which is give rise to. Okay, next slide, please. Also, this is the band structure or angle resolved photoemission measurements. This is the measurement which we did at Electra, and where me and Dr. Jaganlal were together as a postdoc. And here also, based on this angle resolved photoemission measurement, and we also did the band structure calculations, aligning this MA molecule along a certain direction. And we find that if we align MA molecule along a certain direction, it does not reproduce the experimental data at all. Whereas if you allow this MA molecule to rotate freely in all the direction and present itself as this CSPbCl3, as a CS ion, the experimental data is reproduced. So suggesting that the A site, the orientation of A site plays a major role in the basic properties of this material, and which need to be addressed properly. Okay, next slide, please. Now coming to the another aspect, which is the solar cell aspect of it. So we try to make the solar cell out of this material, where you have a perovskite on the bottom right hand side. We have a perovskite, and then we have a spiro as a hole transport material, and TiO2 as the electron transport material. We made the solar cell, and by carefully choosing the hole and electron transport material, where the band gap mapping and so on, and we got an efficiency of about 18% when we made these solar cell out of this. Okay, next slide, please. Okay, yeah, so we got an efficiency of 18%. Next click, please. But the question was how to increase the efficiency of these materials further. So now if we have a closer look at this solar spectrum, you see that the peak, the solar spectrum peaks at around, in the visible part of this visible part, whereas the commercially available silicon solar cell has a band gap of about 1. And as you saw, the silicon has a band gap of 1.1 eV. So the commercially available silicon solar cell works very well in the far infrared region, right? So you see what I'm trying to tell? The solar spectrum has, the maxima in the visible region, but the commercially available silicon solar cell works very well in the far infrared region. So looking at this, what we try to do is, can you have a next click, please? Okay, we try to, make a new material, whereas we try to change the concentration of iodine and bromine in such a way that the band gap changes. So here you see that for x equal to 0, the band gap is 1.6, and if we make x equal to 1, the band gap changes to 2.3 or so. Right? So one can have a different concentration of iodine and bromine and carefully make an absorber material which can have the maximum absorption in the region of our infrared. So the idea was to make a tandem solar cell where of one perovskite material which could absorb the visible part of the solar spectrum very efficiently, and grow it on top of silicon solar cell, which is commercially available, which works very well in the far infrared region of the solar spectrum. So, and in this way, we would definitely get a much higher, and that was an expectation, get a higher efficiency, because each of these solar cell individually has an efficiency of about 20%. So we were expecting close to 40% efficiency. But next click, please. But then what we found is that the efficiency increased only to 25%. It was not as per expectation. So the question was, why did this happen? Okay, next. Next click, please. Okay, so the question was why the efficiency of tandem solar cell did not scale up. So if we have a closer look at this entire issue now, so we see that this is how the band gap on the changes with different compositions, with different iodine and bromine concentration. But it was found that if you shine light on the sample for a very long time, the entire PL spectrum collapses. So you had earlier, we made a material with a band gap anywhere between 1.6 to 2.4, but then, okay, something, excuse me, I think the screen went off.
Sorry.
So, yeah.
We'll be, yeah, we are getting your slide.
Sure, okay, that's fine. Okay, so the entire PL spectrum collapses, and we get on a single click here. So that means if we have made a solar cell using these, we have chosen the hole doped and the hole transport and electron transport material based on the different compositions of iodine and bromine. That's this combination, by matching their band gap and all those things, it does not work any further, and that's why the efficiency has not increased to the level which we wanted. Right. So also we see that the spectral evolution of PL signal changes with time. You see at time t equal to 0, the PL signal was here at the bottom. If you see that at where t equal to 0 is written, the PL spectra looks like this. But at t equal to 45 seconds, the PL spectra continuously changes. Okay, next slide, please. 15, slide 15, please. Not only with time, it also depends upon the fluence. So for example, if you shine a light with the power of 0.5 milliwatt, it takes about 3 hours for this conversion to happen. Whereas if the incoming light has a power of a 5 milliwatt, it just takes 8 minutes for the spectrum, the PL spectrum, to transform completely from one to another. And as I showed in the previous slide, it took about 45 seconds in other case. So also depending on what type of samples you made, whether it's a large grain or small grain, the results were very different, and you were getting, so the sample, so it was something that the sample was changing in the presence of light. So there was a lot of debate going on in the literature. And at that time, there was one paper which came up, which talked about phase separation scenario. In this paper, what they actually told was that when the light falls on the sample, the material, this intermediate compound, completely separates into MAPB I3 and MAPB Cl3. Though this result could never be reproduced. That was the one and only one paper which told this, and these results were never reproduced by any of the scientists or anybody around. But then it triggered a thought process that maybe you get an iodine and bromine rich domains which are present, and these domains are dynamic. They are not very static domains are not there. More than that, it was found that this effect is reversible in nature. As you see here on the right hand side bottom, this is a reversible effect. When you do not shine a light, when the light is at time t equal to 0, you get this black color, the spectra which is plot, which is with black color, with the band gap of say around 1.85 eV. When you shine light for a long time, you get this red color spectra plot, which you get with a band gap of about 1.7. And then you put off the light, wait for some time, and then again the this black spectrum is reproduced back. So it is a reversible effect is what you see. Okay, next slide, please. 16. So measurements were done with cathodoluminescence on this particular sample. And when you shine light on this particular sample, earlier everything was illuminated, but after some minutes, it was found that only at the grains is what are, they appear bright. That means after the iodine and all those rich regions are the grain boundary regions are the iodine rich region. Molecular dynamic simulations were performed on this particular system, and it was believed that when these electron hole pairs are created, when these electrons and holes are moving around, these charges deform the surrounding lattice through the electron phonon coupling, and these charge excitations generate sufficient strain, which is there mostly present at the grain boundary, causing this phase separation scenario. But out of these molecular dynamic simulation, one more thing came up, and that was the this phase separation is temperature dependent. That was the outcome of that in this theory, but it was never been shown. So we went ahead to show and to check whether this prediction of theory that there is the phase transition or demixing transition is a function of temperature or not. Next slide, please. So for that, we made compounds, the various type of compounds and all with various strain sizes. And yeah, so let's go to the slide 18, which might be probably my last slide in some sense. Yeah, okay. And then we made these three samples, x equal to 0.15, x equal to 0.24 and 0.27. I mean, there is a specific reason why we have done it, which I'll explain. This was a very involved experiment. It took about 6 months for us and my students, a continuous work to have this one slide for us. So I'll just explain you the measurement protocol. So you have a sample at a high temperature, or say at room temperature. You then cool it down in the absence of light. Go to the temperature which you want the measurement to be done, and then switch on the light and make the measurement as quick as possible. That's at time t equal to 0, and you say pre-illumination data. Then you continuously illuminate the sample for 4 hours. So you are continuously, the light is falling on the sample 4 hours. And then at the end of the 4 hours, you collect one more data, and that's called post-illumination data after 4 hours of soaking, right? And this pre-illumination and post-illumination data is represented in black and red color. So you see that for x equal to 0.15 sample, black and red color data just falls one on top of each other at all temperatures. So we made our first statement saying that below a critical composition, light-induced phase separation does not occur at all. Then we went to the next sample, which is for x equal to 0.24. And here too, you see that below 190 Kelvin, at 77 Kelvin and 150 Kelvin, black and red plots lie one on top of each other, suggesting that there is no phase separation in these compounds at lower temperature. But when we increase the temperature beyond 190, say at around 200, 225, 275, you see a separate peak which is coming up there. So that is the indication of phase separation. So we have the results of this molecular dynamic simulation, which told that you have, where they predicted that this phase separation is temperature dependent. Here is where we have first time shown experimentally that yes, it is indeed temperature dependent, right? So further, it was found that this phase separation occurs only in the narrow temperature region, only between 200 to 275, and beyond that, when you go at 300, again, there is no phase separation. Just the black and red plot falls one on top of another. So to test this hypothesis that whatever we are doing is correct or not, we made another compound, which is x equal to 0.27. And you have chosen this compound in such a way because our experimental setup, we cannot heat beyond 230 or 330 or something. So we need to have these phase separation transition within 230 Kelvin. So that's why we've chosen 0.27 as a compound. And here too, you say that below 200 Kelvin, there is no phase separation. You have a narrow region in which there is a phase separation, which I've shown in 225 and 300, and above that at 325, again, there is no phase separation, right? So, and later we figured it out that these phase transitions, wherever these photo-induced phase transitions occur, they are pinned to the crystallographic phase transition. It occurs only in the tetragonal phase, not in the orthorhombic and not in the cubic phase. Right? We are still to understand and perform an experiment to figure it out. Why is it so? We do not have an understanding yet, but we're sure that we will find out what the answer is. Now, coming back to the previous question which we had. So can you go back to slide 20 now, please? 19, 20. Yeah. So now we come back to this question which we had, that we made a solar cell with one perovskite solar cell on top and the silicon solar cell, and we were expecting an efficiency to increase. So we did not the efficiency did not increase at all, because the temperature at 300 Kelvin, what we were using, there is the phase separation happening. Right, so that's why the silicon, the perovskite solar cell did not behave the way it was supposed to behave. It was working in this phase separation scenario, right? But if we could have used, but this system, this particular tandem solar cell could work very well above that particular temp, about 300 or 325 degrees Celsius, or below 200 degrees Celsius, right? So we were looking in the wrong direction. So that's why I said that it's very important to understand the fundamental issues associated with the system, because that would tell us that how to make a system, and then it will help in commercialization. Okay, thank you. So you can go to the next slide. And that's my last slide. Thank you very much for your kind attention. Please. I'm sorry that it was a little because I was not controlling the presentation, so I did not have a control on the mouse, so it might be a little tough to understand. But anyhow.
Sir, the presentation was wonderful. We are open for a session. If anybody have any questions for Dr. Topal, they may ask here.
I have one question.
Yes, sir.
I think that is it possible to absorb all the photons of visible light for solar energy application in photovoltaic solar cell?
It is possible to absorb all. So in which region? So you are saying that, so if you look at the solar spectrum, the maximum energy which it comes in the visible region. So you require a material with a band gap which is you know wherein you have a band gap of more than that, right? And we can definitely absorb this the entire energy, and that was the entire practice. You know, the idea behind using these solar the tandem solar cell, where the visible part were absorbed by one particular absorber, the far infrared part was absorbed by another material, as so that you can have, you know, because it's at times not possible to have one material which can cover everything. So till the time such material is found, one has to look into this, and it may happen that you may find such material, but then how much, what is the efficiency of, you know, of that material to absorb those photons also is a matter of debate. Like, for example, even the silicon solar cell, it absorbs the visible part of the solar spectrum. It does absorb it. But then its efficiency to absorb that visible part of the solar spectrum is less compared to a solar cell which has got, you know, a band gap in that region. So it's a matter of, you know, you have to decide between the efficiency and the things. So, yeah. Okay.
Thank you very much, Dr. Topal, and such nice a lecture. Are you listening? Yes?
Yes, yes. Yeah, thank you.
Very nice lecture, and I really enjoy your lecture. And every time I am seeing your lecture because you are a big scientist in this field also. Okay. So thank you very much again for the lecture, and I really appreciate your time for the conference also. Okay, thank you very much.
Thank you. Thank you very much for having me on the, for my talk. Thank you very much. Thanks a lot. And hope to see you sometime soon in person.
Yes, yes, we will meet. Okay.
Sure. Okay.
May
Thank
I
you.
ask a question?
Yes.
This is Kanchan.
Yes,
I'm an
please.
engineer and you're a physicist to the core. So my
Yes.
question is more not related to physics, but more towards the engineering side of things.
Mm-hmm.
So fundamentals are important. It comes down to whether something is working and why they are not working when they don't. My issue is with the current tandem cells, they are still looking at lead. But what I have seen was that when they have lead, over time and in the presence of relatively higher temperatures, let's say you put it on a rooftop, it tends to get hotter also because of greenhouse effect. And the lead seems to degrade. Do you have any comments on that? Or moisture also seems to have the same effect?
Sure. Sure, that's true. I agree with you that, and as that lead is an issue. And for that matter, instead of lead, different compounds have been tried. For example, tin. There are issues of phase separation for that matter, instead of Ma, which I have told, and that is what was tried first. One is trying to put a combination of Ma and Fa, and also Cs, which is cesium, which is what we're trying to do. And that's how one is trying to avoid the phase separation scenario completely. And in that case, again, the next point you told about the stability and the moisture part of it. Yes, I agree with you that initially when this particular compound came into picture and people were talking about MAPB ICRE as a solar cell material, then moisture was a very big issue. And but it has been, we are trying to deal with this issue. It's like, it's a very young technology. Even silicon existed all throughout, right?
Yeah, I
we
agree
knew
with that.
silicon existed, and
In
it took
10
a
years, it has changed the
long
landscape.
time. And at the end, what you have in a silicon solar cell also, you encapsulate it between certain layers, and that's how a silicon solar cell is made. So one has to now form that encapsulation, and all those things have to be done in this case also. And I believe that it's just a matter of time, just because it's much easier to handle these things compared to the silicon and others. So in that case,
preparing it is much easier in terms of the conditions under which it has to be prepared.
Yeah.
But the thing is that once you put it on a rooftop, you don't want to go there after 3 months and try to take it down.
No,
that's what I was.
No. It won't go. Once you have encapsulated them, as I told you, once you encapsulate them, once you do all those things, it is going to work same as any other solar cell. It's just a matter of time, because there are certain variants of this particular compound with CS and other, which can go to a much higher temperatures compared to compared to the lead iodide cases. So it can work at 50-60 degrees Celsius easily. There are variants which are available, but at this moment their efficiencies are lower. But I guess in another few years we would be having.
Is there anything which would replace that? You said ABX3, right? To replace the something which is not as toxic.
Yes, tin is there. At this moment, tin is available. Then one talks about a double perovskite type of things is what one talks about. You replace it with silver and something like this. it's going on. It's an emerging field. It's a very hot topic. It's something like this. If you go to a material science conference, and there are sessions devoted to this particular hybrid perovskites, only for this hybrid perovskites, and it created a stir which was there in 1980s, which was a stir created for high temperature superconductivity. A similar stir is there for this particular compound. Even today, if you check the highest number of publications in one particular field, if you find, I'm sure that this would be one of those fields.
I agree.
So this is how people are behind it, and when so many people are okay, so I guess we should get a result sooner than later.
To nearly 25% is a big jump within 10 years.
Yes, that's true. That's true. So that's why I said this is a big jump in and it's not 10 years, it's only 5 years, because first 3 years was just 2%.
Right.
So it's just a matter of time.
Thank you. It was very informative. I loved the talk.
Okay. Thank you very much.
Thank you, sir, for sparing your valuable time and for informative and interesting session with us. Now, I would like to introduce our next guest speaker, Dr. Rajendra S. Dhaka. He is Associate Professor in Department of Physics, IIT Delhi. He has been scientific collaborator at Paul Scherrer Institute, Swiss Light Source, Villingen, Switzerland. He has done his graduation from University of Rajasthan, Jaipur. He was guest scientist at IAM ESS, Germany, and has been a visiting scientist in Tokyo, Japan. Today, he'll be sharing his knowledge on development of 2D materials as anode for sodium-ion batteries. Welcome, sir. You may start with your presentation now.
Good morning. Can you hear me?
Yes, sir.
Okay, good morning all. And let me first thank organizers for putting up this really nice and interesting conference. And particularly, I thank Dr. Chhagan for inviting me and giving me this opportunity to share our recent work related to energy, of course. And I must also thank all participants, as being on Sunday, I see that there are around 70 participants. So I really appreciate their participation in this conference. So I'm sorry that I have changed the topic and the subject of my presentation, but I think it is still in the line of the conference. As you see, the conference is related to renewable energy, and Dr. Dinesh nicely explained the generation of renewable energy using solar cells, and he explained all the details. So I will try to go to the next level. Can you hear me? So I will try to go to the next level, where though we generate energy, we have these days renewable resources of energy. However, we need to store energy. So in this today's presentation, I will be sharing our recent results where we work on high voltage cathode materials, and then we try to store the energy in sodium-ion batteries. Okay, and we actually at IIT Delhi work on different projects, though today I will be covering our project on sodium-ion batteries. However, we recently published a news article in Indian Physics Association. So if you are interested, you can go through this physics article and you will get all the projects which we are working on at IIT Delhi. So the outline of my talk, I will briefly give you the motivation and try to convince you that why we need to work on sodium-ion batteries. And then I will share some of our recent results, what we are doing at IIT Delhi. And mainly in this talk, I will be focusing on cathode materials. Let me go to the pen here. Okay. So you will be happy also to note that in this direction, 2019 Nobel Prize was given to these 3 great scientists, on their discovery or on their work to develop batteries, particularly lithium-ion batteries. And of course, then we can argue that why do we need to store battery, as this conference is on renewable energy, and as also Dinesh rightly explained how to generate renewable energy using solar cells. And now I'm going to the next step and asking and saying that we also need to store energy. I will try to convince in 1 or 2 slides that though we have sources of renewable energy, but we need to store energy. And as we all know that in recent time, particularly in COVID time, and in fact, if you compare since 1983 to 2018, there's a huge demand. The demand of energy devices is increasing significantly with time. And therefore, we need to store energy. But still, I have not convinced you that why do we need to store energy, okay? So let me tell you that the energy resources for the community mostly belongs to fossil fuel, right? And that includes oil, natural gas, coal, and so on. And these are the resources, they share the major global energy resources, and it has been predicted that they will share around 80% by 2035. But, you know, by using extensively these fossil fuels, we are going into the problem. And these are actually the main causes of global warming and climate change. And mainly, as we know, that due to the emission of carbon dioxide, right? Therefore, the development and utilization of renewable energy, such as solar cells or wind energy for giving or providing power, are really essential, right? However, I'm sure all of you would agree with me that these resources, all the renewable energy resources, are mainly dependent on environmental factors, right? So their dependence has to be overcome, right? And when we talk about normal operation of power grid, that of course will require stable and continuous source of electricity. So the effective use of clean energy is now a great challenge for us. And mainly, as I said, due to discontinuous availability, and these depends on both time and weather conditions. So now the big challenge, big question to all of us is to how to store the electrical energy, the current. So this is the key point, and we have to think about the effective storage devices for renewable energy. And for me, for the sustainable development of the society, these 3 components are very important. The harvesting green energy, that as Dinesh also talk about, we have these days many solar cells. In fact, these solar cells are now everywhere, and we are able to, you know, harvest a lot of green energy. But as I said, that these are environmental dependent. So we need to store energy. So the second factor is to store energy. And the third very important factor is to manage the use of this stored energy in a proper way, right? And these days we talk about electric vehicles, then of course all these devices, laptop, smartphone. These days everyone is having even more than one smartphone. We every day, for these days, even for the communication, we need electronic devices like laptop and all. So we need to store energy. I'm sure by now we convinced that we really need to store energy. And I will be talking about battery. Of course, there are different ways of storing energy. I will be discussing about battery. So just for the sake of students' knowledge, I give brief introduction how battery works. So, you know, in battery, you have 2 electrodes, anode and cathode, and they are separated by electrolyte. So you can see in this picture, the anode mostly in the graphite is being used for lithium-ion batteries. And as cathode, this lithium cobalt oxide is being used in lithium-ion batteries. When we talk about sodium-ion batteries, of course, the counterpart is sodium cobalt oxide. And as an anode for the laboratory testing, we use pure sodium as an anode. And they are separated by electrolyte and a separator, right? So what happens during charging and discharging? During charging and discharging, when we charge with the electrical energy, when we plug our mobile phone to the power plug, in this case, what happens? These metal ions. So when I say metal ions, when you use lithium-ion battery, these are lithium ions. When you use sodium-ion batteries, they are sodium ions. So these metal ions, they move from cathode through the electrolyte and separator to the anode. Okay, and they come and get settled here. And then when it is discharging, that time what happens? These metal ions basically deintegrate. So they basically move back to the cathode and get settled in their structure. Now you can say that, okay, lithium-ion batteries are being used everywhere, very well established technology and so on. So why you are working on sodium-ion batteries, right? So I will try to convince you in the next 2 slides, and I'm sure that you will be convinced that particularly for Indian context, we need to think of alternative of lithium-ion batteries. And of course, there are few advantages as well as few disadvantages. And our job is, to overcome with all disadvantages to make these batteries work in India. So the advantage is that, the sodium being next to the lithium in the periodic table, they share very similar chemistry for the energy storage mechanism, right? And of course, sodium, I would try to convince you that is more attractive, mainly because sodium is highly abundant and uniformly distributed in Earth's crust, right? And more importantly, as I said, for Indian context, there are almost no lithium resources in India. Okay, so our government has so many initiatives, and these days we talk about electric vehicles everywhere, particularly in big cities where we are, suffering from the pollution. And in line of self-reliant India, there is need to think about something which is available within India, and therefore we need to develop sodium-ion batteries, right? And this is one aspect. Of course, the second big aspect is that, as I said, sodium is highly abundant and uniformly distributed, so it will be cost effective. And when I say cost effective, I just give you an idea. This is the table taken from one review article, but just to give you an idea that for lithium batteries, we use the carbonates for making electrodes, and the cost of lithium carbonate, you can see it is $5,000 per ton, whereas for sodium, the sodium carbonate price is only around $150 per ton. So you can see the difference in price between sodium materials and lithium materials, and that motivates us that we need to develop another system, another energy storage devices which everyone, the common society, can use. And particularly, as I said, when we talk about India, we should think about the resources within India, and we should not depend on other countries. And when we are using lithium-ion batteries, we are dependent on other countries. But of course, I talk about positive points about sodium-ion batteries, but there are many challenges. Otherwise, by now you have seen sodium-ion batteries everywhere. And the challenges mainly come from the natural, properties of sodium as compared to lithium. And the main important factor here, which is playing the role, is the ionic radii of sodium, which is roughly twice bigger than lithium. So that basically, slows the diffusion kinetics, and therefore there will be lower capacity of sodium batteries as compared to lithium, and also the rate capability, cyclic stability. These are the parameters I will talk about in the next slides, but these are the parameters which are very important for a stable battery. And more importantly, as I said, for lithium-ion batteries, the graphite is being used as an anode, is very well established, but that graphite is not suitable now for sodium-ion batteries, right? And mainly because the layer spacing in graphite is not enough to accommodate larger sodium ion. Right? And when we talk about thermodynamics and so on, then sodium is also not energetically favorable to go and sit between the layers of graphite. So these things, brings many challenges, and moreover, the bigger size of sodium makes also difficult to find a host electrolyte, right? Because while charging and discharging the sodium metal ion, they have to diffuse through the electrolyte material, right? So I will skip this. So basically, due to all these, there are during charging and discharging, there are problems, and one of the biggest problem is the larger volume variation, the larger volume expansion while charging and discharging, right? And that cause to degrade these electrode materials, and therefore there will be quick capacity decay. So as we talk about these days, the life of battery 5 years, 6 years. So for sodium-ion batteries, this is a big challenge, that the capacity decay is relatively faster as compared to lithium, and of course the low Coulombic efficiency. So when I say Coulombic efficiency, means the storage, the sodium storage while charging, and the sodium storage while discharging. So the discharge capacity and the charge capacity, right? So then, of course, now we have to think about how we can overcome with these challenges, and therefore we need to develop all the components of the battery to develop sodium-ion batteries, right? But of course, we already have lithium-ion technology, established lithium-ion technology, and we have knowledge of that. So we take advantage of that, and then we go to the next step. So for lithium-ion batteries, we know that these transition metal ions are being used as cathode, right? Where in sodium-ion batteries, the intercalation reaction, the charge and discharge reaction, that will require space to accommodate bigger sodium, right? And also there will be a requirement of multivalent ions in the cathode to have the compensation of charge neutrality. Okay. So this means the diffusion of sodium while charging, discharging also depend on the crystal structure of electrolyte as well as the cathode. And of course, the sodium is bigger, heavier than lithium. So that also brings us the challenge towards the electrode potential. So because when you talk about energy density, you need to have specific capacity as well as the higher electrode potential, both, right? So this lower performance of sodium-ion batteries we need to overcome, but at the same time, if we compare cost per kilowatt hour of energy that sodium can provide us, still we have a great motivation to motivate further generation to develop sodium-ion batteries which are really cost effective, and particularly at the larger scale where we don't worry too much about the weight of the battery. So in this case, then there are a few components, and as I said, we need to develop cathode, anode, electrolyte, and we also need to test all these solvents, binders, and all. And our aim should be to increase the energy density. And of course, these days we don't have too much of time, so we also want the fast charging, and we don't want our battery to discharge fast, so we need higher power density. And this is a big component for us, particularly in India. The cost effectiveness and safety environment, these are the factors we should focus on. So in this line, what we are doing at IIT Delhi, as I said, we synthesize these electrode materials using different routes, different methods like solid state hydrothermal sol gel in both bulk and nanostructure. So we synthesize these materials in different ways. And of course, then we need to characterize and investigate their physical properties using different tools before we go for actual device. And then we need to prepare and assemble this device, which is called coin cell here. And we then test electrochemical performance to test their specific capacity and the life cycle. And of course, as I said, this is a very new area of research to develop sodium-ion batteries. Particularly in India, there are very few groups working in this direction. So we should, optimize so many parameters to overcome these challenges, and we target to get reasonably high performance of the sodium-ion batteries, at least comparable or close to lithium-ion batteries, so that we can bring these devices in the market. So keeping those in mind, we started this project in 2017, and now we established all these facilities in our group, where we have the battery cycler for electrochemical testing. We have a new globe box for developing, assembling all these coin cells, and we also need a couple of small instruments to assemble for cutting electrodes and so on. And in today's presentation, we'll be discussing our very recent results on a particular material which has honeycomb structure called Na2Ni2TeO6, which is considered as high potential and stable electrode for sodium-ion batteries. It's still unpublished work, but it is available in arXiv. And in this work, we try to, understand the diffusion kinetics, which is very important to understand the battery mechanism. So going to the crystal structure, you can see the crystal structure here. This is the honeycomb-like ordering here. You see there are NiO6 polyhedra and TiO6 polyhedra, so are shown here in different colors, the TiO6 and NiO6. And there are 3 sites for sodium, 1, 2, 3, and these are shown in between these layers. Okay. The important thing here is that the interlayer spacing is around 3.5 angstrom, which is more than sufficient to accommodate sodium atoms, right? And therefore, it is considered to show high performance as well as long stability, right? In these panels, B, C, and D, these are shown the sites for each sodium. So sodium 1, sodium 2, sodium 3. And here you will be wondering that why this ball has different color. You can see here the red color, the blue color, and the green color. This actually represents the sharing, the site, how much site is filled with the sodium at that particular site. Right? And so this material is having layered structure and significantly larger interlayer spacing, which is required for accommodating larger sodium ion, and it has also significantly high ionic conductivity. This material having nickel will have redox couple of nickel 2+, 3+, which is considered to be high voltage, around 3.6 volt. Okay, and therefore this material is considered for this application of sodium-ion batteries. And moreover, the theoretical capacity of this material is around 138.5 milliampere hour per gram when we consider to take both the sodium out from the structure. So therefore, the synthesis of this material was done by solid state reaction method. So basically, we used all these materials, precursors in stoichiometric ratio, mix them and grind for a few hours and heated for a couple of hours at high temperature. And then you basically get the honeycomb structure of this material. And you need to then characterize. So ICRE and the ritual refinement confirms the hexagonal structure of this material with the latest parameters A, B, and C, which are in agreement with the literature. The EDEX measurements also show the stoichiometric composition of this material, and then SCM measurements as we use solid state reaction method to prepare to synthesize this material. So we expect the particle size of the order in the micron range. And if you see these SCM particles and the zoomed view, you will realize that these show the layered structure of this material, which is supposed to be useful for sodium intercalation deintercalation. For more characterization, doing Raman spectroscopy, we see all different Raman active modes from TiO6 as well as NiO6 octahedra. And there are also few modes which are stretching modes of NiO bonds. So we are able to see all these Raman active modes. And by performing high resolution TM, we found that this material is highly crystalline, and the interlayer distance is also consistent between the HR10 and the one obtained from X-ray diffraction refinement. So with this, then we are more or less convinced that our material is single phase and perfectly in the structure which we wanted to. Then the next step is to fabricate coin cells. And for that purpose, we are doing everything in our lab, starting from preparing the sodium disc, which is being used as counter electrode, then the electrolyte. Of course, we purchase electrolyte raw material, but then we mix with the solvent and prepare the final step. And then fabricate the coin cell and perform these different electrochemical measurements, the cyclic voltammetry, electrochemical impedance spectroscopy, galvanostatic charge discharge, and so on. Okay. So let me see how much time I have. Yeah. So we'll then try to skip, where basically we prepare slurry by having cathode material and some conductive additives and binders and so on. We dissolve them in some solution, and we then dry for a few hours. Then we basically coat that slurry on aluminum foil. The thickness is roughly 20-30 micron or so, right? And after that, we also prepare our electrolyte and everything we need to do in the inert environment, because we are dealing with sodium, pure sodium metal as well as sodium related materials. So for that purpose, we do everything in this globe box, where the oxygen content and the water content are less than 0.1 ppm. Okay. And this is the crimping machine which is inside this globe box, where we basically, keep all these elements in this order to fabricate this particular coin cell. Okay. So you can see here the top cap, the spring, then the spacer, then basically this is what is important: the anode material, the cathode material, the separator, and the cathode. Okay. So these four are the elements, the components which we prepare and assemble, put all together in this fashion and assemble this coin cell. Once you have assembled coin cell, you can then take out from this globe box and can do further measurements. So for that purpose, then the first task we need to do is to test the current versus voltage behavior. And that is what is called cyclic voltammetry, and that will give you the information about reversible sodium extraction and destruction. Right. So basically, you see here, these measurements are done at very slow scan rate, 0.05 millivolt per second. This is what is the voltage scan here on the horizontal scale. And these are the 3 cycles. So you will see, of course, in the second cycle, between the first and second cycle, there will be a significant change because of various things happens during the first cycle, like solid electrolyte interface formation and so on. However, you see that there are oxidation peaks at very well defined potential, and also the reduction peaks at very well defined potential. And you will see these peaks in all these cycles that basically demonstrate that there is reversible insertion and deinsertion of sodium into the structure. Right? The second important point you have to focus on is to test the electrochemical capacity. So you can see here the specific capacity plotted on the horizontal scale versus potential. So we did measurements between 3 volt to 4.4, 4.5 volt. And the profile, the charge discharge profile is exactly matching with the cyclic voltammetry profile, where you can see all these redox peaks, the oxidation reduction peaks. The profile is matching also in the charge discharge profile. Okay, so you see all these plateaus which are correspond to these redox couples, while this is the charge, this is discharge capacity, this is charge capacity. Okay, so you can see that at very low current rate, of course, this is low current rate, 0.05 C, where 1 C is equal to the theoretical capacity. And in this case, what we have seen is that the discharge capacity at this current rate is almost around 82 milliampere hour per gram, right? And we then, of course, tested this while charge discharge at different current rates. You can see this voltage versus the concentration of sodium when we extract sodium, when we insert sodium back. This is during the 4th cycle. And we can see this profile is very well matching with the cyclic voltammetry and the potential versus time profile. So all these plateaus, the redox couples, are consistent with all these measurements. Then the very important factor here is that how fast we can do this charge discharge process. And for that purpose, we need to compare, we need to test the rate capability. So rate capability, what do I mean is that we have tested this, for example, at very slow rate. So 0.05 is considered at very slow rate. And then 1 C is considered as fast speed. Okay, so the high current rate. And you can see when we go from 0.05 to 1 C, the capacity is, of course, decreasing. And that is expected because when you are doing fast charge discharge, you are not giving enough time to these metal ions to go and settle in the structure. Even before they get settled, you are asking them to come back. Okay, so the performance, of course, will degrade. But the important point is that after doing these measurements, if you go back to your slow discharge rate, you should be able to achieve the initial capacity back. So that is what is shown in this plot, specific capacity on vertical scale, cyclic cycles, number of cycles. So you can see for each current rate, we did around 10 cycles. Okay, and then going from 0.05 to 1, right, the capacity is decreasing, of course, but then when we go back to 0.05, we are almost back to the initial capacity, right? So that basically, demonstrate that your cell is capable to go in the faster cycle, faster charge discharge cycle if required, and it can come back, it can restore the initial capacity when you go back to the slow charge discharge process. Right. On the right scale, we have plotted the Coulombic efficiency. As I said in the very beginning, this is also very important in the sense that your charge capacity and discharge capacity, there should not be significant difference between these two. Whatever the charge capacity you are getting, you should be able to get the discharge capacity. So in simple terms, let me explain that in one case, you are taking out sodium from the cathode material, right? In other process, you need to bring it back to that cathode material. So the number of sodium ions you are taking out, you will be able to bring it back to that structure, right? So that is how we define the Coulombic efficiency. And you can see this line is almost close to the 100%. So that means the number of sodium ions which you are taking out, you are able to put them back. Okay, so we are able to maintain almost 100% Coulombic efficiency for all these current rates. This is also very important. Then, of course, another important point is that the cycle life. So let's say I charge my mobile phone once per day. Then if there is no degradation in the capacity for, let's say, 500 cycles, that means more than 1 year, right? I will be happy. So to test that, we did these charge discharge measurements at two different current rates. So two different current rate means 0.1 C is slow current rate, 0.5 C is fast current rate, right? So you can see these profiles here, the potential versus specific capacity. And here we are showing cycles up to 320. And for this current rate, we are showing cycles up to 500. And you can see, if you focus on this high current rate, the fast charge discharge process, you see there is almost constant capacity. Of course, there is around 20% degradation, but in 500 cycles. So if the capacity is degrading only 20% in, let's say, almost 2 years, that is still okay. So therefore, this cathode material is considered to be highly stable for sodium-ion batteries. Then we always try to, understand the kinetics, the diffusion kinetics, which is actually playing a crucial role to understand the storage, the sodium storage mechanism. So there are, of course, different methods. We focus on 3 methods, and I will be showing you 2 methods in this presentation. Yeah, I think I have some time. So one is that you need to do cyclic voltammetry, so the current versus potential at different scan rate, right? And when you increase the scan rate, you can see here 0.05 to 0.3, right? You will see the increase in the current. Okay, this is the current in milliampere, and you can see going from 0.05 here to 0.3 here, there is increase in the current, peak current. Okay. And there is also shift in both redox couples. So basically in oxidation and reduction is moving slightly towards lower potential. Oxidation is moving slightly in higher direction. Of course, that we don't want. That shows that there is some irreversibility in the sodium extraction, but that is what it is. And by taking the peak position and the peak current of these different oxidation and reduction peaks, and using this equation, we try to find the diffusion coefficient, which is D here. Okay, so the IP here is the peak current, then the scan rate, then N is the number of electrons that are taking part in the reaction. The A is the area of the electrode, the concentration of sodium in the cathode, and finally the D is the diffusion. So we basically plot the IP versus square root of scan rate. You can see the plot here. And by taking the slope of this, will give you the values to put in this equation, and finally you get the value of diffusion coefficient, which is of the order of -10, -12 centimeters square per second. Okay. We also, I will skip this slide where we try to extract the information about the diffusion controlled mechanism or the capacitive controlled mechanism, and we found that this is kind of a pseudo capacitive behavior happening in this particular material. We also then try to do electrochemical impedance spectroscopy that will give you the idea about the charge transfer resistance, and also you can extract the diffusion coefficient using this equation, and that comes out to be again of the order of -12, which is consistent with the value which we extracted by cyclic voltammetry. And then to understand the stability, the structural stability, we did X-ray diffraction measurements at different stages of charge discharge. So A point is at the beginning, so the OCV, and then we did one measurement at fully charged stage and one measurement at fully discharged state. And what we found that the structure, you can see the X-ray diffraction and the refinement and we see that the structure is really stable even at the fully charged state as well as fully discharged state. Then, of course, we need to see which redox couple is playing the role in the mechanism. And we found out by doing X-ray photoelectron spectroscopy that the nickel redox couple, the 2+3+, is taking part into in the reaction, and not the tellurium and the sodium. That is what is expected.
Sorry to interrupt, sir.
I'm finishing in 1 minute.
Yeah, okay, thank you.
Okay. And then, of course, you need to check the structure after long cycling. So you can see the XRD pattern after 500 cycles, and the structure is exactly same as it was in the beginning, which shows that this material is highly stable even after going through so many charge discharge cycles. So with this, let me conclude. And in this study, we try to demonstrate that this material is very stable, having relatively high capacity for sodium-ion batteries, and it is really useful for powering portable devices and for large-scale applications. So with this, let me thank Day-3, who is my postdoc and did this work. We obtained these samples from BARC, and I also thank Professor Basu, who is a collaborator in this project. Of course, I thank all the funding agencies who are supporting our project on this very important aspect. And we also have industry collaborator Hero Electric, which we are trying to develop batteries for electric vehicles. So with this, thank you for your kind attention. And I think I have taken extra time, so I'm sorry for that. Thank you.
Okay. Thank you very much, sir. Hello. Thank you very much, sir,
Thank you.
For a nice lecture, and I really appreciate your time also to give us. And I am really happy to see you, and I congratulate to you to be a chairman of INEAS.
Thank you, Sagar.
Okay, you may proceed.
So I will be happy to take questions.
Thank you so much, sir. We are very fortunate to have you with us, and your session was full of knowledge and valuable thoughts. Ladies and gentlemen, here I want to make an announcement, or I want to mention here that Professor Rajendra S. Dhaka has been elected as chairman of Indian National Young Academy of Sciences. In short, INEAS. Dear audience, now we are moving forward. So now it's a moment to add a golden feather in the hat of success. So we are entering into oral presentation session.
Okay, so there are no questions now. I have taken extra time, so you are not giving me chance to speak to audience. Anyway, that's fine. Thank you.
Doctor, I have some questions.
Yes, sir. Sorry, I have taken extra time, I guess. I did not...
I have just a small query.
Yes.
I am from Indraprastha University, Dr. Rajesh Kumar.
Yes.
So do you have all facility regarding this battery?
Yes, now we have all facilities in our own group. Last 2-3 years, we were collaborating with other groups, engineering department in IIT Delhi, but now we establish all in our own group. Yes.
Okay. Because I am listening first time regarding this battery work from the IIT Delhi. Maybe some people are working and long back, but I am hearing first time. So I did some work at the US related to this lithium-ion battery at RPI. So if I get chance, then can I visit your lab?
Yes, for sure. We also have a summer faculty program at IIT Delhi. I think the call is now open. So you please feel free to apply through that as well, so that you can officially get opportunity to visit and work here for 2 months.
Oh, okay, sure. Sure. Thank you, Doctor.
So you
Thank you.
feel free to contact me. I will give you more information.
Okay, okay, sure. Thank you very much, sir. Thank you.
Sorry, sir, for that, Hari. I again request audience that if you have any queries or you want to interact with the speaker, the session is open for you. Ladies and
Thank you so much.
if you have any queries, you can ask. I think there are no more questions. Thank you so much, sir, for your valuable time you had for us from your busy schedule. Thank you very much. I'm heartily gratitude full for you.
Thank you. Bye bye.
Now we are starting our presentation session.
Hello, can you hear me?
Yes, sir, you are audible.
Yes, sir.
So as we are starting our session, I want to introduce the chairperson of this session. The first chairperson of this session is Professor Kedar Singh. Presently, Professor Kedar Singh is positioned as Professor at Department of Physics, Jawaharlal Nehru University, New Delhi. He has done his PhD from University of Rajasthan, Jaipur. He has expertise in condensed physics, experimental condensed matter physics, nanomaterial, thermoelectric materials, quantum dots, core shell materials, plasmonic nanocrystals, chalcogenide glasses and their nanocrystals. He has published 244 research articles, 5 book chapters in reputed journals. I welcome you, sir. Our next chairperson is Dr. Rajesh Kumar. Dr. Rajesh Kumar has been working as Associate Professor of Physics since 2016. Dr. Kumar joined us as Assistant Professor of Physics at Guru Gobind Singh Indraprasth University, New Delhi. He obtained his PhD on ion-induced modification in polymers and their characterization from Aligarh Muslim University. He completed his postdoc from University of Rajasthan. He is recipient of Young Scientist Award as well. His current research activities are related to material science, nanotechnology, and condensed matter physics. I welcome both of you, sir.
So for the session, participants will be divided into break rooms with one chairperson, and they can give their presentations one by one. Every chairperson will be a co-host, and they can call the participants to share their work. It is requested to the participants to enable their mic and video and share their screen first, and then start with the introduction and their presentation. Participants who are not giving presentation at that time must disable their mic and video to avoid any chaos and confusion. Participants' presentation will be evaluated by assigned as well as other chairpersons at our end. Break room will end automatically after 12:30 p.m. I repeat, break room will end automatically after 12:30 p.m. So try to keep your presentation short and to the point. Those candidates who will not get notification for joining into break room, they will be having presentations with us outside the break room. Also, if any participants due to technical or network issue comes out of break room, they can mention in chat box and type their room number, and we will try to resolve the problem and make them go in the break room assigned. And for any other query or technical issue, it is requested, please type your query or issue in chat box so that we can resolve it. Thank you so much, and please be patient. We are creating break rooms for all of you.
I repeat once again that we are going to have oral presentation. Parallelly, we are arranging our break rooms for the rest of the people for poster or presentation who didn't had earlier yesterday. They can present today in their break rooms will be allotted. And if you have any queries related to anything, you can tell us in the chat box.
Yeah, please start with the first presentation.
Yes, sir, we shall start.
Yes.
So we're going to call our first presentator, that is Subhash Chandra Arora from Gurukula Kangri, Haridwar, Uttarakhand.
Yes, ma'am. Am I audible?
Yes, you are
Yes,
audible.
yes. Please share your slides.
Sir, I don't have my PPT right now. Can the organizers share the PPT for me?
Yes, we are doing that. Please keep patience for that.
Okay, ma'am. Thank you.
Just in a while, we are sharing your slides.
Okay, okay. Thank you.
I request all the participants, except the presentator, please keep your mic off to reduce the noise echo. Dear participants, you have to conclude your presentation in limited of amount of time, that is 7 minutes only. Participant, can you see your slide? Mr. Subhash Chandra Arora, can you see your presentation? Is it visible to you?
Yes, ma'am, it is. I'm just starting. Just a second.
Okay.
Please start.
Okay, so am I audible, ma'am?
Yes, you're
Yes,
audible.
please start.
Okay,
Go ahead,
thank you.
go ahead. Because time is
Okay, so
running. We are also late in time. Please.
yes, sir, I'll finish my PPT in less than 5 minutes only.
Okay, okay.
So, okay, so good morning to all the members who are present in this conference. My name is Subhash Arora, and I'm doing my PhD from Gurukul Kangri University, Hyderabad. The topic of my paper is using diffusion of innovation framework along with the attitudinal factor to predict the future of mobility in the Indian market. As we all know that pollution of the environment is currently a global concern. Advancement in technology is making the lives of humans better, but has also disrupted the ecosystem to a greater extent. Although there are many activities that are contributing to the current day carbon dioxide emissions, but it is primarily the transportation sector that is becoming a cause of concern. Burning of fossil fuels and rising use of private vehicles are the two major reasons behind the increasing phenomena of climate change in today's time. Ma'am, can you change the slide, please?
Please change the slide. Organizer, please change slide.
Therefore, to address this problem, what we need to do is we need to adopt more environment-friendly mode of transportation, that is electric vehicles that are currently available in the market. Now, these vehicles are being defined as vehicles that use electricity as fuel for propulsion. It is a novel renewable technology with potential to reduce the global temperature rise and also to help the countries to achieve their intended targets under the Paris Climate Agreement 2015. However, the sales of these vehicles has not picked up despite its numerous advantages in terms of fuel efficiency and its positive contribution to the environment. Therefore, I undertook this study to analyze the potential factors which the Indian consumers, holds about this technology in the present day market. Ma'am, can you change the slide, please? Next slide, please. So these were the variables that were identified in this research. This is basically a framework which was developed by Rogers in 2003. So the first this slide, ma'am. Next slide. The diagram one. Next. Yes. So this was the previous one. So this was the model that was developed. In this model, there are basically 6 independent variables and 1 dependent variable with attitude also acting as a mediator between the 5 independent and the dependent variable. So the aim of this study is to find out which of these independent variables has the most significant influence on the purchase intention of the Indian consumers. Next slide. This was the review of literature that was done. With the help of these studies, the conceptual framework was being developed for this research paper. Next slide. So the gap identified in this research was that although there are studies available across the world, numerous authors have identified what are the potential barriers in their respective countries. But the research in India is very limited, and we can say that the market for these vehicles is gradually developing, but still a comprehensive study needs to be undertaken so as to find out which are the most influential factor that the Indian consumers hold about this technology so as to make them future buyers of these vehicles. Next slide. So a questionnaire was being circulated by me. The questionnaire was being developed from the previous literature. That questionnaire was being circulated in the New Delhi region. And this was the demographic profile of the respondents who actually helped me in collecting the required data. Next slide. So the reliability and validity of that questionnaire was being checked through SPSS software. The results showed that the factor loadings, the Cronbach alpha, the composite reliability was found to be adequate. That means the questionnaire that was developed was being reliable since it was being adopted and not created by me. The last column of AV, that is average variance extracted, indicates the validity of the questionnaire, and the threshold limit of 0.5 was the limited criteria that authors have and to check the validity component of the items that were part of the questionnaire. Next slide. So the results of this study indicated that it is primarily the attitude of the consumers that plays the most significant part in their purchase decision towards a particular product, and especially a high involvement product such as vehicles in the market. This was followed by the rated advantages. We can take an idea from the P column where the star signifies which factor has the most influential impact and which does not. Although the direct influence of attitude and complexity was identified, but none of the other variables were found to be having that much impact on the purchase intention. However, the indirect influence of all those 5 variables was identified via attitude acting as a mediator. Next slide. So lastly, what we could say is that the Indian consumers are pretty much optimistic about this novel technology of electric vehicles, but parallelly, they are finding this technology to be a little complex in terms of their charging duration and their speed and their limited speed availability. So what we can say is that the transportation sector needs to change its propulsion technology so as to make the goal of sustainable development a reality in the near future. Thank you.
Okay. Thank you, Subhash. But my one query this: what is the future of this the electric vehicles in India?
What is the
future? Because this is a very good talk, but just I'm asking the future of the electric vehicles in India.
So the features of the vehicles or the market?
Yes, you can say market also.
So the vehicles offers numerous advantages in terms of their limited negative contribution to the environment. Plus, the fuel efficiency of these vehicles is actually very good when we compared it to the combustion vehicles that we use in today's time. But the negative points associated with these vehicles is that firstly, there is absence of charging infrastructure. Like we have petrol pumps today, there is absence of charging infrastructure. Then on the other end, charging duration is the major barrier because we can fill up our petrol vehicles in less than 5 minutes, but a big four-wheeler would take at least 4 to 5 hours to charge fully. So the consumers are seeing this charging duration factor as a drawback of these vehicles because taking a vehicle taking 4 to 5 hours to just recharge is a potential barrier, and the consumers in today's time are not that much patient so that they can wait their vehicle being charging for more than 4 to 5 hours. So there are barriers or there are negative points, there are disadvantages that are still to be chalked out.
Okay. Then if you see this is the electric vehicle, especially I'm saying for cars, very costly. Then in future, this is the cost will reduce or it will be the same?
So the major reason why the electric vehicles are being priced highly in the market is because of the battery that is being installed in the car. The battery is half the price of this vehicle. If you go to the market and want to purchase an electric car it would be roughly around 9 to 10 lakhs, whereas a petrol vehicle could be purchased with just 5 to 6 lakhs rupees in your pocket. So the government is doing its part by investing in the R&D of this technology, and hopefully the world will come out with a better or upgraded battery technology that will help to reduce the price of this vehicle in the market in the near future.
Okay, good. Very good talk. Thank you very much.
Thank you, sir.
Thank you.
Thank you
so
for your
much.
time. Thank you, sir.
Okay, then next, then anyone ask some question, please? We can take only
Yes,
one
sir.
question. Hello.
If anyone have any questions, they may ask right now.
Or participants can drop.
Now I would like to call our next participant, Abhishek Parida from Indian Institute of Technology, Guwahati, Assam. Abhishek, if you're here. Okay, so I'll call the next name, Sayantan Jana.
I think he's not here.
Our next participant will be Alok Kumar from Indian Institute of Technology, Guwahati, Assam, India. Alok, if you're here.
Maybe call next.
Next, please.
Ajay Meena.
Hello,
Ajay.
hello. I'm audible, ma'am.
Yes, you are.
Can I share my screen?
Yes, we are sharing your slide.
Okay, ma'am.
Ajay Meena, from where?
Sir, I'm from Indian Institute of Technology, Tirupati, sir.
Is this
IIT Tirupati, yeah.
Yes, ma'am. It is visible.
Very good. Please start.
Good morning, all. Today in this presentation, I am going to talk about the suitability of LaNi5-X COX for low temperature thermochemical energy storage applications. So, next slide. Okay, so my content for this presentation is you can see here introduction and PCI curves and bent-up plots for LaNi5-X COX and performance parameter of storage systems and result CTs. Next slide. Okay, as we all know that energy requirements are increasing day by day, and currently most of the energy demands are met through conventional sources of energy, and these sources generate CO and CO2 into atmosphere, and that is very harmful for environment and also contribute in global warming. So we need to move towards the renewable energy sources like solar energy and wind energy. So for that thermal energy storage is a big area for study, and thermal energy storage maintain the supply and demand chain of the energy industry, because if demand is high, then you can supply the energy from storage centers and vice versa also. Next slide, ma'am. There are three types of thermal energy storage: latent heat storage, sensible heat storage, and thermochemical heat storage. In latent heat storage, materials used are paraffins, fatty acid, and salts, whereas in sensible heat storage, the materials used are water, brick, soil, and rock, etc. And coming to the thermochemical heat storage, it is the most significant heat storage, and it is based on reversible chemical reaction and absorption process. And metal hydrides are the most efficient material for thermochemical heat storage because of the high storage density and long-term heat storage and the advantage of the thermal stability during the cycle. And the thermochemical heat storage have the storage density of 500 to 3000 megajoule per meter cube. Next slide. Okay, so PCI curves shows that metal will hydride above the pressure, which is called the plateau pressure. And for measuring PCIs, we use the PTC Pro simulator. and PCI curves are plotted between the pressure and the hydrogen storage capacity, and the Bentov curves are based on the Bentov equations. And next slide, ma'am. Okay, so here what we have done, we took the material Ni5, then substitute the some content of Ni with the some content of cobalt, and record all the changes in the PCI curves. So here are PCI curves for LaNi5-X COX for 3 different temperatures: 70 degrees centigrade, 90 degrees centigrade, and 110 degrees centigrade. This is for x equal to 0, and this one is for x equal to 0.25, and this one is x equal to 0.5, and last one is for x equal to 0.75. Next slide, ma'am. So for comparison, we have created absorption and desorption PCI as 110 degrees centigrade, and then created the Bentov curves for all 4 materials with x equal to 0 to x equal to 0.75. So this is the absorption PCI for LaNi5-X COX at 110 degrees centigrade, and this is the desorption PCI for LaNi5-X COX at 110 degrees centigrade. And here are also Bentov curves are plotted. Bentov plots are plotted. This is for hydrogen absorption, and this is for hydrogen desorption. And these Bentov curves are plotted based on the Bentov equations. And next slide, ma'am. Coming next, all the performance parameter of storage system were calculated, like pellet to pressure and maximum absorption capacity we got from the PCI curves, and enthalpy and entropy for absorption and desorption were calculating using the Bentov plots. Like our slope of the Bentov plots used to calculate the enthalpy of absorption and desorption, and the intercept of the Bentov equation is used to calculate the entropy of absorption and desorption. And the COP of the system was obtained from the energy required by the energy stored. Next slide, ma'am.
Next, please.
Slide.
Next slide.
From all the parameters were calculated, we can conclude that hydrogen absorption desorption pressure decreases with increasing CO content from x equal to 0 to x equal to 0.75 for a constant temperature, and also entropy and enthalpy of formation also increases with increasing CO content from x equal to 0 to 0.75 for a constant temperature. And these are the results we got from our study. This is the graph, how energy density is varying with respect to x for a constant value of temperature. Like this blue one is for 110 degrees centigrade, and so on, so on. And the maximum absorption capacity we obtained was 1.561 weight percentage for LaNi 4.5, CO 0.5 at a temperature of 70 degrees centigrade. And for calculating the reaction enthalpy, we use the Bentov equation, which is shown here. And the highest energy density and COP of 247.931 kilojoule per kg and 1.011 respectively were obtained using the material Ni5-X CO 0.75 at a temperature of 70 degrees centigrade. And for all the temperatures, energy density is you can see from this graph is increasing linearly with varying the CO content from x equal to 0 to 0.75 for a constant temperature. And with this, I want to thank Mr. Sarad Babu and Professor E. Anil Kumar for helping out through the study. And I also want to thank the Rajasthan University and ICRE team for providing this opportunity for researchers. Thank you very much.
Thank you. If there are any questions.
Yes. First from audience side, then I will ask one question.
Yes, sir.
Yeah. Ajay Veena, you take this is the LaNiCO.
Sir, we have taken the LaNi5, then we replace the some content of Ni with CO. For different content, we have made the PCI curves and then comparison.
No, it is good. Then there is any reason to take LaNiCO?
Sir, actually, we are working on like AV5 type of material, so we will do the same study for every AV5, like as much as possible AV5 type of materials in the future. Like sir, we want to do for every material of AV5 type of materials.
No, what is the motivation do you want to work on this material?
Actually, sir, because of the more stability and higher storage density we got from maybe 5 type of materials. So because of that, we have chosen this material.
Good, very good. Dr. Rajesh, would you want to ask any question? Any query?
No, sir. No, sir. It's okay.
Okay. Thank you. Thank you. Nice. Very good.
Thank you. Thank you very much, sir. Thank you.
Maybe call to the next one.
Yes, our next participant is Bhim Singh from CSIR National Physical Laboratory, New Delhi.
Yes, ma'am.
What is the name of participant?
Hello.
Yes.
Bhim Singh.
Yes, we are sharing your presentation.
Yes, ma'am. Yes, ma'am, please.
Bhim Singh.
Is it visible to you?
Yes, ma'am. Yes, ma'am.
Yes, you
Let
may
me
start.
Yes, myself Bhim Singh from CSIR NPL New Delhi. This is my title of talk: Growth and Characterization of Bismuth Selenide Thin Film and Flexible MOSE2 MO foil for application in flexible energy devices. Next, please. This is the outline on which I will talk I deliver my presentation. Next, please. So first of all, I want to give a short introduction to thermoelectric devices. Thermoelectric devices is an energy convert device that convert heat energy into electrical energy by generating voltage due to temperature difference between both ends of the materials. And the performance of thermoelectric device can be governed by the dimensionless thermoelectric figure of merit, ZT, where ZT is equals of S square sigma T upon K. Bi2 bismuth selenide as a one prime candidate for the study of topological surface state for thermoelectric application because it have a narrower band gap, approximate 0.3 electron volt, and high carrier mobility. Due to this suggestion that it may be useful for thermoelectric device application. Here is some references where I have got some motivation that our material may be useful for thermoelectric device application. Next, please. So why flexible thermoelectric devices? Existing thermoelectric devices are rigid because they are composed of hard metal based electron semiconductor, hindering the full absorption of heat source from uneven surface. So that's why flexible thermoelectric device capable of generating electrical energy when it is directly attached with hot sources such like human skins and hot water pipe that can be useful for the application such as cell power sensor and temperature detection. And flexible thermoelectric devices can also useful for wearable electrocardiographic systems as well. Next, please. These are some application of bismuth selenides. These are many application various fields such as infrared photodetectors, for thermoelectric devices, topological insulator, quantum Hall device, laser photonics, smart windows cooling. Next, please. This is the crystal structure of bismuth selenide that's shown rhomboidal crystal structure with hexagonal planes. This material show the quantiple layers where the one quantiple layers consist 5 atomic layer structures that can be shown in the figure. Next, please. So why we need flexible metal foils? So the selection of flexible substrate for energy device application is one of the challenging tasks because it depends on several parameters such as melting point, robustness, cost, and electrical properties, etc. But recently, flexible metal foils have attracted a lot because of their low cost, high thermal and electrical conductivity, flexibility, and scalability. That's why in this way we have first time grown Bi2Se3 thin film and flexible MOSE2 MO for metal foil at 400 degrees centigrade by magneton sputtering technique for the potential application of flexible energy devices. Next, please. Next, please. This is the thin film growth magneton sputtering system which we have used, and this is the post selenization process after the thin film growth to get high stoichiometric thin film. These are some thin film characterization tools which we have used in our thin film: FESEM operating voltage 15 kilovolt and XRD X-ray source 0.15406 nanometer and Raman spectroscopy at wavelength 514.5 nanometer. nanometer at room temperature. Next slide, please. First time we have growth bismuth selenide thin film on MO foil. This is Raman and XRD analysis of bismuth selenide thin film that revealed the formation of good quality of bismuth selenide thin film that can be seen from the FWHM, and the XRD reveals the high crystallinity of bismuth selenide thin film on MO foil that can be seen from their signature peaks. Next, please. These are the FESM image and elemental analysis EDX that reveals the nearly stoichiometric bismuth selenide thin film obtained on MO foil by the monotone spectrings. These are the FESM image that reveals the hexagonal nanoflex with grain size 500 to 650 nanometer on MO foils. Next, please. To growth bismuth selenide thin film on MoSe2, we first growth MoSe2 thin film on MO foil. These are the Raman and XRD spectra. We get their signature peak of MoSe2 on MO foils that correspond to the peak position 168, 240 and 285. That reveals the formation of good quality MoSe2 thin film on MO foil that can be shown from the FWHMs. And on the right hand side, there are the XRD show that their signature peaks of MoSe2 that reveal the high crystallinity of the bismuth selenide MoSe2 thin film on MO foils. Next, please. Where is FESM image? Okay, sorry ma'am, FESM image is not visible in this. I don't know what's the problem, but the growth of these here is the FESM image of the bismuth selenide thin film or MoSe2. I don't know where is the FESM image, but FESM image reveals the hexagonal nanoflex of bismuth selenide thin film with grain size 150 to 250 nanometer. This is the elemental analysis of EDX that reveals the growth of bismuth selenide thin film on MoSe2 and MO foils. Next, please. These are the Raman spectra of bismuth selenide thin film on MoSe2 that reveals the formation of good quality bismuth selenide thin film on MoSe2. Here we can see then Raman spectra, the peak position of Raman shift is slightly shifted due to the presence of internal strain in prepared thin film compared to bulk bismuth selenides. And on the right hand side, XRD scan of bismuth selenide confirm the high crystallinity of bismuth selenide thin film that can be seen from their signature peaks of every thin films. Next, please. This is the summary of our materials. X-ray reveals the crystallinity of bismuth selenide thin film, and Raman spectroscopy also reveals the good quality of bismuth selenide thin film on MoSe2 MO foils. Surface morphology study also reveals the hexagonal nanoflex on MO and MoSe2 substrate, and EDX analysis revealed the stoichiometric bismuth selenide thin film obtained on MO foil. And finally, grown bismuth selenide thin film on MO foils will be further utilized for the studies for thermoelectric and photoelectric performance for potential application and futuristic flexible energy devices. Next, please. And this is my acknowledgement. I would like to acknowledge Director of CSIR NPL, Mr. J.C. Viswas, my HOD head, and Dr. J.C. Tavale, Dr. B. Galot, Dr. B.S. Yadav, and Surface Science Spectrum Lab member, ICRE DST and CSR SRF fundings. Thank you. Thank you, sir. Thank you, ma'am.
Yeah, okay. Thank you. It's a very nice presentation.
Thank you, sir.
This is only one question.
Yes, sir.
You deposited some thin film.
Yes, sir. Yes, sir.
Then if you see this is the material, then why do you want thin film really of this material?
Sir, because I discussed that we have got some motivation. I have discussed references because already people make thin film, thin film for energy thermoelectric devices. In this way, we have growth bismuth selenide thin film.
Okay, then suppose this is the bismuth selenide bulk material and thin film. Then what will be the difference in of the physical properties?
Because sir, thin film materials have high carrier mobility than bulk materials, and it have also a tunable band gap that can be tuned by layer thickness. This is the most important for optical and thermoelectric devices application. That's why we grow bismuth selenide thin film.
Okay, then what is the thickness of your thin film in angstrom? Sorry, nanometer thickness.
Sir, we have get different thickness of our thin film because MOSE2 we have MO foil we grow to 500 to 600 nanometer, and on MOSE2 we have found 150 to 250 nanometer sometimes.
Okay, good. Then how can we control thickness of the thin film?
Sir, by the annealing temperature, we have annealing.
No, you are using the sputtering technique.
TR ice पड़े हैं वो डालो कैसरोल में बल्लू को.
Yes, sir.
So you are using the sputtering technique. No?
Yes, sir. Yes.
So are you using the DC sputtering or RF sputtering?
RF sputtering, sir.
So what is the difference DC sputtering and RF sputtering?
In RF sputtering, we use the frequency 13.56 something, but in this we don't use this frequency as like this. RF sputtering used for metal, semiconductor, and insulator, but DC sputtering we cannot use for insulator materials.
Okay. Yes, we've seen some very good work, but please try to understand some basic.
Yes, sir. Yes, sir.
Okay. Who is your guide? Who is your
Dr. Sunil Singh. Dr. Sunil Singh Kuswa.
Okay. Thank you. Any question from audience side?
Kedar sir, I have one question.
Oh yes, sure, please.
So, Bhim Singh, why you have choose the MO foil for substrate? Why you have not choose the silicon and other substrate for the deposition of thin film?
Sir, we have used flexible MO foils because it have high melting points and flexibility, scalability, and high electrical conductivity, thermal conductivity. That's why we choose metal foils, flexible metal foils for flexible energy devices applications.
Okay.
Yes, sir. Thank you.
Kedar sir, over to you.
Thank you.
Thank you, sir.
Bhim Singh, it's a good work
sir.
really.
Thank
Please
you,
admit next candidate. Bhim Singh, आप वो करिए अपने को.
Yes, sir.
Yeah.
Now I would like to call upon our next participant, Sophia Rani Sheikh from IIT Guwahati. Sophia Rani Sheikh from IIT Guwahati. Next, I would like to call upon Savan K. Raj from CSIR Bhavnagar, Gujarat. Savan K. Raj from CSIR Bhavnagar, Gujarat.
This is the
now.
Yes. Okay. Yes. Go ahead. Yeah. Please next.
Next, I would like to invite Mr. K.C. Bhamu.
Yes, I am here. Yes. So,
Mr. K.C. Bhamu, sir, please, can you share your slide with us?
yeah, it's ready. Yes, I am sharing. No, I will share from here.
Yeah, yes.
Yes, sir, you can share your slide.
Yes, okay. Is it visible now?
Yes, sir,
Can you
your
see?
slide.
Okay, can you see it is movable?
Yes, sir, you may go.
Yes.
Okay, okay. So if it is movable, okay. So I will not talk basic about this introduction and all. So my talk will cover that how we DFT people help the experimental guys. Okay, so my talk is basically on density functional theory. So first I will talk that how we understand the DFT, and then introduction, then my work. So actually we DFT people guide experimental person. So sometimes they synthesize their material and they think that they require very high pressure and high temperature. So for that particular target, we can tell them how they can reduce the temperature and pressure for the synthesis material. Okay, and then also if we help them, then they can reduce their manpower and equipment cost, and also they can reduce their chemical cost. So in DFT, we work on this this quantum level, and we predict the material at that continuum level that we are seeing in that macroscopic world. So we work at the quantum level and we predict the property at a continuum level. So this is my work. This is a liquid organic hydrogen carrier. This is basically hydrocarbons. So I will tell you how we can use this for energy applications. So from the fossil fuels, we see that the use of fossil fuels emit the CO2 in that environment, and that result in that global warming, and it also increase that mortality rate globally. Then we have the other technology, battery technology, that is having short lifetime and limited storage capacity, and it also demand maintenance cost. So this is also have some limitations. So we need to think about that alternative technology. So that is how we can keep our earth green and clean. So we require economic and environment friendly resources. So hydrogen is a very known element that is 75 exists by its mass. So let's say like 1 and 1 can make 11. In that same way, hydrogen, if we hydrogen and hydrogen combine, they can produce that energy. So I was reading that article yesterday. The French aircraft makers announced that they will test this hydrogen fuel engine. So this is the future of hydrogen energy. That is theme of our workshop also, conference also. So this liquid organic hydrogen carrier that are basically organic molecules. They are low cost, reusable, safe, and environmental friendly, and we can use already available transport infrastructure that we have for oil transportation, rail transportation. So we don't require any other new infrastructure for these NOx compounds. So this is my system where all the carbon atoms are fully bonded with the hydrogen atom. When we release the hydrogen from this carbon, we can obtain this hydrogen lean system. So so this is reusable. So where we load the hydrogen in the system, and we transport this hydrogen molecule or over this carrier using already available transport, and release the hydrogen. There we can use that hydrogen for our daily life applications. So this is a reusable molecule. So these are the some computational parameters that I used for my computational study. So how we can support experimental people. So actually it's sometimes it's difficult to dehydrogenate that system for experimental people. So we tell them that how they can go for the complete dehydrogenation. So for example, in early days, experimental people were having problem for the ammonium synthesis. For ammonia synthesis, they require high temperature, high pressure. And then DFT people did several reaction mechanism on the platinum catalyst, and they predict that the splitting of nitrogen is that rate determining step. So then now experiment people directly target on the splitting of nitrogen and they synthesis that ammonia. In that same way, when we do the dehydrogen of the system, experimental people can target on these readily bonded bonds, that these are the most sluggish step for that dehydrogen. So experimental people target this and obtain the complete dehydrogen. So in this work, we can tell them that this releasing that hydrogen from this step is a rate determined step that we have observed from our kinetic study. So for the pristine system, the average dehydrogen energy was 17.51, that is equivalent to almost equivalent to dibenzene toluene, that is commercially available LOHC molecule. So we try to reduce that dehydrogen energy. So we try to substitute nitrogen and boron nitrogen as a co-substitution elements in that organic molecule, and we found that when we have that boron and nitrogen in that LOHC system, this dehydrogen energy was reduced from 11.5 kilokelvin per mole to 17.5 kilocalorie per mole to 11.17 kilocalorie per mole. So that is maybe I think most that is lowest among all the reported dehydrogen energy. So the RDS I showed you was predicted that when we release the hydrogen from the that particular bond, so the required kinetic energy was 188.5, and that was really very high. So experiment people can focus on this step to reduce that the practical conditions. So when we have boron, so we can reduce the dehydrogen energy. So basically what happened, so I talk about that this system is reusable. So what that mean, how we can predict that this is reusable? So we carried out a homolumos study. So here in the left side, we have that hydrogen rich system. And when we release the hydrogen step by step, we see that homolumo gap is decreasing. At the end, we have lowest homolumo. So this lowest homolumo gap for all the states predict that this system is still in unsaturated mode and available for next reaction. It means we can reuse this from here to hydrogen rich system. So these are my conclusions. So we predicted that, okay, how we can reduce that dehydrogen energy. And when we have some heteroatoms in the carbon ring, we can significantly reduce that dehydrogen energy. So that basically help expert people to understand how to reduce that temperature and pressure. So these are my references. This work was supported by Korean government. And I'm open for expert collaboration with these fields. When we go out, please keep wearing mask. Thank you.
Yes. Because this is a very good work, really. It's on hydrogen, because of hydrogen fuel we need really in future. This is very important.
Yes, sir. But it's very cost effective, sir. Very cost effective.
Yeah. This is very efficient work also. But my question is here: what are the practical problem to use, the hydrogen fuel?
Sorry, sir.
What are the practical problems to use hydrogen fuel?
Sir, this actually we are producing hydrogen. Okay, so we like that we have nitrogen in the nitrogen cylinder. So in that same way, these organic molecules are used to store that hydrogen in the liquid form. So my title is liquid organic hydrogen carrier. It means these organic molecules are in a liquid state. So we easily can store them and transport on the remote location, and we can just extract hydrogen from there. So wherever we want to use the hydrogen, we can use. Even it can be in the fuel cell, even in that cars or daily lives.
So is it costly or cheap?
Sir, very cost effectively we can synthesize these organic molecules from the industrial byproducts. So we can say that it's kind of extremely low cost among all the available technology. It's very growing field, and Germany and the South Korea is working very hard in this technology, and soon we will be having some future in India also.
So when will it start in India? Any group is working in India in this program?
For now, my friend Dr. C.S. Praveen just started from the Kerala University. I'm supporting him.
Okay, good, very good. And which software you are using for
Sir, I'm using various software, like mostly I use Quantum Espresso, but I also use WASP and Win2K.
Okay, good, very good. Then yes, then what is your email address? I want to contact
Sir, my email address KC. I can type in chat box, sir.
Okay.
We are open for collaboration for experimental people.
So you are faculty there?
Sir, I'm senior postdoc here. I did my DS Kotari from the Goa University, then NPDA from NCL Pune, and now I'm senior postdoc fellow at University of Ulsan, South Korea.
Oh, okay, okay.
So I typed my email ID in that chat box.
KC
Bhamu.
BHAMU @
85.
Sorry, it isn't visible. Could you narrate? KC Bhamu @
gmail.com.
Very good. Yes, we will contact you because we want to start such type work in JNU, Jawaharlal Nehru University.
Yeah. Sure, sir.
Yes.
Sir. Manish sir is also there.
My knowledge, Professor Kedar Singh, then definitely we want to start this work.
Yeah, thank you. So our technology, our motive is to produce that energy with very low cost materials.
Oh yeah. So that is, so it is important really. This the low cost material. Then
I also work on the optoelectronics, thermoelectronics, and electrochemical water splitting. So there's also my main fields, but LOS is growing field. So I'm starting this field.
First, we are interested to use this hydrogen stuffs really. Eh?
Sure, sir. Sure. Welcome, sir.
Okay, thank you very much. Thank you. Any question from audience side, or Dr. Rajesh want to ask some question?
No, sir. It's over.
So, okay, then thank you.
Sir, if the audience have any question, they can type in the chat box. I will be available. I will happy to answer all the questions.
Oh yeah, yes, definitely, yes. Could you please send your CV to me? If you see this is the Professor Kedar Singh, and this the
yes, sir, sure. I will share, sir.
Go on
I will share.
School of Physical Sciences, so then please see my email. Then you can send.
Sure, sir. Sure.
Okay, then thank you.
Thank you
very much. It's very nice talk. Yes. Next candidate, please.
Now I would like to call upon our next participant, Alok Kumar from IIT Guwahati. Alok Kumar from IIT Guwahati.
Yeah, good afternoon, one and all. So I will share my screen. Am I audible?
Yes, sir, you are audible. Sir, is the presentation visible to you?
Yes.
Okay, sir, you may start with your presentation. Sir, you may begin with your presentation.
Yes, please start. Alok Kumar, please start your.
Maybe some network issues.
Technical issue. We can wait for a few minutes.
Okay.
Or you can call to other participant.
This you can call again. Then Abhishek, Parida, one is the some this is the other Sophia Rani Sheikh. She's not here. SK Raj, CSIR. You can remind those candidates if they are there.
I'm announcing the name. If someone is present, you may give your presentation now. Mr. Abhishek Parida, Savan K. Raj, Mr. Savan K. Raj from CSIR. So you can give your presentation. Savan K. Raj from Bhavnagar, Gujarat. Mr. Savan K. Raj from CSIR, Bhavnagar, Gujarat.
Or you may call again to Alok.
Mr. Savan K. Raj, are you there for the presentation?
Yes, ma'am. Can I start?
Yes, sir. Yes. You can start with your presentation.
Okay. Ma'am, is it visible?
Yes, sir. It's visible.
Ma'am, is it visible?
Yes, sir. It's visible.
Okay. So, hello everyone. Myself, Savan K. Raj. I am from CSM CRI Bhavnagar. I am doing PhD under the guidance of Dr. Vaibhav Kushrist. The topic is three-dimension nickel iron doped graphene oxide Maxine architecture as an efficient water splitting electrocatalyst. As we know that there is a need of fossil fuel day by day, but as we know that also the depletion of fossil fuel is there. So we need a clean and green substituent which can replace them. So hydrogen is that candidate which can replace this fossil fuel, as it is it cause no environment to no harm to environment. So we perform hydrogen evolution reaction and oxygen evolution for by using our electrocatalyst. Water splitting is a technique which can produce hydrogen and oxygen. So we demonstrate nickel iron doped graphene oxide Maxine architecture for an efficient water splitting electrocatalyst. So Maxine basically is a 2D material which have a formula of Mn+1 Xn and Tn, which M represents the early transition metal and X represents the carbon or nitrogen and T represents the surface function, whether it is hydroxyl or fluoride or any other group. So other electrocatalysts like platinum, iridium, ruthenium are also there, but they are very costly, and due to the low earth abundance, we cannot use them at a large scale. So we basically use earth abundant material, which is nickel and iron, for their experiments. Maxine basically synthesized by max phase, and we use titanium aluminum carbide for this experiment. So basically we each aluminum layer from the max phase, and we get titanium carbide Maxine phase. From that, first we synthesize graphene oxide using Hammer's method and Maxine, as I talked already earlier, and we combine them using calcination and freeze drying method, and we get a GMX, which is nothing but our nickel iron dope graphene Maxine at oxide at Maxine. So these are the basic characterizations which are done for, which are successfully deliberate that our material is synthesized. And the first one is as from the right side we can from the extreme right side, the first one is IR, the second one is XRD, and third one is XPS spectra. Then in left side corner we have the same images, and beside them it is a 10 images. So basically same images explains the A B images explains how the aluminum is etched from the max phase, and it's seen like this. The C, D, and E images shows the GMX, our synthesized material, at different temperatures. The C1 is at GMX 400, which is calcined at 400 degrees Celsius. The D is for 500 degrees Celsius, and E is for 600 degrees Celsius. And F is the we can see the nickel and iron distribution on the GMX surface. G basically represents the mapping of the element. H is titanium. In I we can represent, we have iron. J in nickel. K is carbon, and the I is elemental composition. In 10 images, we can see the uniformly distribution of nickel and iron nanoparticle on the surface of GO. And we can in figure B we can see the Maxine sheets, which are zoomed in figure C. In we can also see the nanoparticle of iron and nickel are neck to neck combined with each other, and are oval and spherical in shape. In G we can see that lattice spacing of nickel, which is 2.9 nanometer, and in H we can see the 2.5 nanometer lattice spacing for iron, which is represents the its phase, which is 400 and 311 respectively. Also, we beside them there is the XPS image or XPS spectra of for each of the element present in that our composition, that is iron, nickel, titanium, and carbon. Our result and conclusion is like that. Our first graph represents the LSV plot for this is linear Swift voltammetry plot for our prepared GMX, which is for OER, oxygen evolution reaction, and B is for hydrogen evolution reaction. In right side, HER and OER plot are deliberated for 50 millivolt. The first one A and B for 10 millivolt, and beside them A and B for 50 millivolt. Yes, and the plotted from the right side, second one we have Tafel plot for OER and HER, and beside for OER, in which we can see the ruthenium and GMX 400, 500, and 600. We can see that GMX 500 is basically showing good Tafel plot, and for this experiment. So we carry forward only GMX 500 for our experiment. So basically the studies has been mainly focused on GMX 500. That's why we have only take HER for only GMX 500, which is HER Tafel slope, which is 110 millivolt. Basically, Tafel slope states that how much fast is your reaction, and how sustain how fast is the reaction is going on. After that, we perform the stability. We perform the 50 cycles for that our GMX 500, which shows in our CV plot, and at 5 millivolt per second. In mechanism, beside them, we have mechanism for OER and HER. OER basically is a four-step process, and HER is a three-step process. So in conclusion, we have we can say that our GMX material synthesize is showing a good is bifunctional at electrocatalyst, which is showing OER at very lower potential of 370 millivolt, which is just 90 more than the standard ruthenium oxide, and HER at 470 millivolt at 10 millivolt. So I would like to acknowledge sincere gratitude to ICRE to give an opportunity for presenting my work. Dr. Vaibhav Kushan as a supervisor for guidance and support for pursuing my work. Analytical discipline of CSM CRI, my family, friends, and colleagues. Thank you so much. And I will be happy if you have any questions.
Yes.
And as basically my slides are only 4 because as we mentioned that only 2 to 3 slides should be there. So I have make only this much of slides.
Okay, it's good work really.
Sorry, sir?
It's a very, very good work. But my question is how you can prepare a vaccine material?
Sir, basically we bought max phase titanium aluminum carbide in which aluminum is there, but we each the aluminum as seen in first slide, max phase is a max phase which is titanium aluminum carbide is there. So we have to each aluminum using LIS and HCl, in which in situ HF. So, sir.
No, just you purchase it, but how we can prepare this material?
Sir, we can prepare this by ball milling process also. We can separately combine these elements and ball milling is there, and you can calcine the material for 800 and 700 degrees Celsius at inert atmosphere. So we can prepare the max phase also.
Then have you done this thing or just
no, sir. We have not done. We just simply prepare. So we simply purchase from the company.
Oh, okay, good. Okay. Then why do you want make this the RGO mix there? Sorry, graphene oxide.
So basically, graphene provides the support to the nanoparticles. That's why.
Oh, okay. Then any other property of this graphene oxide?
Graphene basically provides the surface area and the holding property to my composite material. Maxine I have select because it has a porous structure, and it has its unique and electrochemical property, which is we can see in other literatures where they have been vastly used in supercapacitor applications and HER/OER experiments.
But here you are using graphene oxide. If better is this, if you use reduced graphene oxide, then I think you will get better result.
Yeah, sir. Maybe you are right, but yes, sir.
Yeah, okay, thank you. It's good. Any
thank you so much, sir. Thank you so much.
Yes, any question from Dr. Rajesh and the audience?
Sir, I'm KC Bhamu. I have one question.
Okay.
So, these days MOF are also showing better performance than Maxine.
Yes. Actually, I am preparing one MOF for the same experiment in nowadays. Yes.
Because MOF are having more surface area than Maxine.
I'm not audible.
So MOF is having more surface area than Maxine and providing more active site for the reaction mechanism.
Yes, definitely, yes.
Yeah, sure. So this was my just idea to give you. So yeah, thank you.
Yeah. Organizer, there is some background noise. Could you please unmute this participant?
Participants, please kindly
mute system. Yes.
I would request all the participants to please mute your mics.
Yes. Okay. Now this is it's a very good talk and very good work of the. Okay. Thank you, 7K Raj. That's very good work. Next.
Now I will call upon our next participant, Sayantan Jana from IIT Guwahati, Assam. Sayantan Jana from Guwahati.
Hello. Yes, ma'am. Can you please hear me? Am I audible?
Yes, sir, you are audible.
Hello. So could you please share my presentation, or shall I share the screen and presentation from my computer?
Sir, can you share the slide from your end?
Okay, sure. Just give me 1 minute, ma'am. Just give me a few seconds, ma'am. I'm having little internet connectivity issue here, so just give me a few seconds.
No problem. No problem.
Thank you.
Sir, are the slides visible to you?
It's okay.
Yes, ma'am. Yes, ma'am. It's visible to me.
So you can begin with your presentation.
Okay. Thank you so much, ma'am.
This is Satyam Jana. Okay. Yes. Okay. Jana. Yes.
Yes, sir. That's me only, sir. So, good morning to everyone. My name is Sayantan Jana. I am a research scholar in the Department of Mechanical Engineering, IIT Guwahati. Today, I'll be presenting our work, hydrogen desorption studies on a embedded cooling tube type metal hydride reactor designed for fuel cell applications in front of you. My supervisor is Professor P. Muthukumar. Could you move the next slide? Excuse me, ma'am. Can you please move to the next slide?
Next slide, yes.
Yes. So in this particular slide, I have shown what I'll be talking about in this particular presentation. So why in the introduction, I'll talk about why hydrogen storage is critical. Then in the background, how metal hydride-based hydrogen storage solutions can help. Then I'll talk about the different metal hydride reactor-based designs that are used typically. Then I'll talk about the experimental studies that have been carried out in our lab and what is the scope of the experiments. Then finally, I'll talk about the experimental outcomes and how they can contribute in fuel cell applications. Can you please move to the next slide, ma'am?
Next slide, please. Yes.
Okay, so all of us we are presently facing a harsh climate change action, and now the world leaders are pledging to have net zero carbon emission by 2050. So to make that happen, hydrogen is being considered as a game changer. So there are several reasons why this is so. One of the reasons are like it has a very high calorific value and it has zero combustion characteristics, and it can be produced from renewable electricity. Now, storage of hydrogen is really a challenge. Why? Because it has very low gaseous density. Now, typically the storage methods that are employed nowadays, that is a high pressure storage, say up to typically 700 bar, or cryogenic storage, say at 20 Kelvin temperature. So both these kind of storage, they consume a lot of energy, and they are since they are high pressure, they are also, we have to make the container very thick. So metal hydride can solve this problem because metal hydride can absorb hydrogen at near ambient. There are metal hydrides that can absorb hydrogen in near ambient condition and store for a long time. Can you please move to the next slide? So if we look at what are metal hydrides, so basically they are metals and their alloys that absorb hydrogen reversibly. So the exothermic reaction, I mean, the forward reaction is exothermic in nature, while the reverse reaction is endothermic. Phenomenon forms the basic thermal applications of all the metal hydride based hydrogen storage systems. And during absorption or storage, we need to supply, we need to take away the heat so that the reaction can be carried forward. And during the desorption of hydrogen from the metal hydride, we need to supply heat to the system. So they are basically very safe because hydrogen won't come out unless the metal hydride is very, heated. And they can be stored in near ambient condition, as I have shown in the left side of the slide. On the right hand side, what I have shown is that how polymer electrolyte. Sorry, ma'am, can you please go back to the previous slide? Just for 1 second. Excuse me, ma'am.
We are not audible really to you.
Sir, am I audible, sir?
Yes, now, yes.
Sir, actually, I was not done with the previous slide. So, ma'am, could you please go back to? Okay, maybe I'll continue with this slide only. So, what are the challenges that we face with metal hydride based hydrogen storage devices is that they have very poor heat transfer characteristics due to very low effective thermal conductivity, that is in the order of 0.1 to 1 watt per meter Kelvin. So the strategies that has been adopted over the years by researcher is one is the augmentation of existing thermal conductivity by introducing high conductive metal structures like say wire mesh, matrix, foam, etc. Or another method is compacting the metal powder into pellets or capsules. And also they have used extended natural graphite in order to improve the thermal conductivity. Another method how we can improve the overall heat transfer through metal hydride bed is to minimize the heat conduction part, that is minimize the bed, or introduce an external or internal heat exchanger like say extended surfaces, coil tubes, external jacket PCM, etc. Can you please move to the next slide, ma'am?
Next slide, please.
Can you please move to the next slide? So the scope of the present work is we have designed, developed, and fabricated a metal hydride reactor that is basically cell and tube type. It contains 99 embedded tubes and an outer cooling jacket. The reactor was filled with kg of lanthanum cerium nickel based alloy. The consumption is Na.C.1 Ni5. It's a very excellent hydrogen storage alloy. I'll talk about it later in later slides. And we carried out hydrogen desorption at different hydrogen heat transfer temperatures and flow rate to assess its suitability for to be integrated with a PUM fuel cell. Can you please move to the next slide now? Ma'am, next slide, please. Yeah, so in this slide, I have shown the metal and the alloys. In the bottom, the figure shows the photograph of the metal hydride reactor. So as I said, it is a cell and tube reactor, and the CAD images and the geometric dimensions are shown on the top. It has a cell dimension of 168.28 mm with a 7.1 mm thickness, and designed alloy capacity 20 kg. On the right hand side, I have shown the PCT, that is pressure composition temperature curve of the alloy, La.9C.1 So it has a midpoint plateau pressure around 2 bar at 25 degrees C and a maximum storage capacity of 1.8% and a low hysteresis around 0.6. Please move to the next slide, ma'am.
Next, please, next slide.
So experimental procedure. What we have done is the right hand side. I have shown the schematic of the experimental setup. It basically consists of a hydrogen cylinder, the metal hydride reactor, a mass flow controller, various valves, a vacuum pump, two constant temperature and water flow meter. So the valve arrangement are shown here, and all the designated instruments are also shown in the figure. So prior to start of the experiment, what we did was we checked for the leakage in the circuit as well as the metal reactor by supplying argon gas at 80 bar, and we kept it pressurized in that condition for 1 and we checked if any pressure drop is there, and we found that no pressure drop was there, so it is a leak-proof system. We also subjected it to a vacuum condition by using a rotary vacuum pump and degassed it up to 0.001 millibar. Then during absorption, what we do is we supply hydrogen from the hydrogen cylinder through the valves V1, V2, V3, and V6. And the rate of hydrogen transfer is monitored by the mass flow, Coriolis mass flow controller. During this option, what happens? The valves V6, V4, V5, and V7 are opened, and all others are closed. And during absorption, low temperature heat transfer fluid is transferred from the low temperature bath, and during desorption, high temperature fluid is transferred using the hot bath. Can we move to the next slide, please? So this is basically we have carried out a series of parametric study. So the parameter varied that I already mentioned is two things. One is the heat transfer fluid temperature during this desorption. Another is the heat transfer fluid flow rate. So the temperature we have chosen for variation is 40 degree to 60 degree at a gap of 10 degree. And at that during that period we have fixed the flow rate at 20 LPM. And when we studied the effect of variation of flow rate, we fixed the temperature at 50 degrees C. And in our metal reactor, we have attached two K-type thermocouples. The probe length are shown in figure, and also a pressure transducer to monitor the reactor pressure inside. Can you please move to the next slide? And another two K-type thermocouple was there to monitor the HTF inlet and outlet temperature. Please move to the next slide. Ma'am, please move to the next slide.
Next slide, please.
So this is the part results and discussion. So as I said, first we will see what is the effect of heat transfer temperature variation on discharging of the metal hydride reactor. The left-hand side figure shows the amount of hydrogen dissolved at different heat transfer fluid temperature 40, 50, 60 with time. So as we can see, the amount of hydrogen dissolved at three different temperatures, they are almost similar, a few grams apart, but the rate at which it was dissolved is faster at higher temperature. So that is quite obvious because at higher temperature, as we know from the hydrogen properties, the equilibrium pressure at higher temperature will be higher. And since we are dissolving it to ambient, the potential for mass transfer will be more. So the rate will be higher. Right-hand side, what we have shown the bed temperature for three different cases. So the bed temperature usually goes down, then slowly.
Hello. Hello.
Hello, sir.
Yes.
Kedar, sir?
We are not. Yes. We are not audible. This.
Yes.
Presentation.
Jana. Yeah.
Okay. Yes. I think now this is complete. I think so.
I got disconnected.
Yeah. Okay. Yes.
Sir, I got disconnected, sir.
No problem. No problem. Rajesh, would you want to ask some question?
No, sir. It's okay. It's okay.
Can I go to the? Can I explain this page, sir? The conclusion part, sir.
Yes. If you want, then you can go. But now we are running out of time. Jana, your presentation is good, really.
Just give me 1 minute, sir.
Okay, if you want, then we can.
Please give me 1 minute to explain.
Okay.
Thank you, sir. Ma'am, can you please share the last slide of my presentation, ma'am?
Rest of the participants, please wait, because we are going to have our invited lecture now. And if you have any kind of queries or you want to interact with each other, then the session is open for a few minutes.
Ma'am, how many presentations are left?
Yes, sir?
How many presentations are left?
Sir, all the presentation has been completed.
Okay,
Actually,
okay, it's okay.
that is not present. So I think
Sorry,
now-
ma'am, can I request? Actually, I was disconnected when my paper ID is 05175. Alok Kumar.
Yeah. Yes. Alok, do you want to present? Yes,
Yes, sir.
please
Yes, sir.
allow him. Yes.
Can you share screen from my side?
Sorry
I'm
to
connecting from mobile.
Sir, sorry to interrupt. We are going to have an invited lecture, so we can resume our.
Give him for 3 minutes only. Hello? Organizer, please give him 3 minutes. Alok Kumar.
Okay, sir, you can continue then.
Yeah, yes.
Sir, excuse me, sir, this is one thing I want to say that my abstract was 0.59, so my schedule. Excuse me, sir, this is 5205 Abhishek Parida. Sir, I have also a presentation to make, but when can I make my presentation? Because I was being contacted to present my presentation within next 15-20 minutes. I got a call at 12 o'clock.
The person who was asking for 3 minutes, we are giving you 3 minutes to present
Yes,
your.
kindly share the slide from your side, madam.
Okay.
So, presenter, we have very short time because the invited speaker is waiting.
Don't worry, sir. I will not take more than 3 minutes.
Okay,
Thank you for
3
giving
minutes plus 3 minutes.
Okay, sir. Thank you. So this is Alok Kumar, student of Professor P. Muthu Kumar. So this work is being carried out under the guidance of Professor P. Muthu Kumar at IIT Guwahati. So the title of my presentation is Bed Poisoning Characteristics of CO2 Impurity on Metal Hydride-based Hydrogen Storage and Purification System. So this is the outline of my presentation. Please next. So coming to the hydrogen energy economy, so world is witnessing a huge rise in the global temperature and also CO2 concentration. So people are switching towards hydrogen energy economy, and there is a big challenge wherein hydrogen as a renewable energy source and carrier can be produced from several sources, but always it's not possible to produce pure hydrogen. And also, since it is very light and it is very risky to store it at very high pressure. So storage and purification is a great challenge. So we have come with the solution for this. Next, please. So metal hydride-based hydrogen storage systems are the solution for hydrogen storage and purification. Here, the absorption and desorption characteristics are endothermic and exothermic in nature, and we use here the beautiful properties of this metal hydride, the alloy tailoring property. We select alloy according to our requirement. Next. So research is being done in 3 fields. One is enhancement of heat transfer technique, as the thermal conductivity of these alloys are very low. And the second is the alloy tailoring. And third is the application, as absorption desorption is endothermic, exothermic in nature. So this beautiful characteristic can be utilized for several thermal heating and cooling applications. Next. So for this study, we have selected ALA 0.9 CE 0.1 Ni5 alloy, wherein we can absorb hydrogen at ambient condition, and also we can be able to dissolve it at high temperature, and also it is suitable for hydrogen storage and purification application. Next slide, please. Yeah, so this is my system. So reactor design I'm not disclosing because the patent is under grant, so it's published. But yeah, so this is our system through which this is schematic of the experimental setup and through which we have conducted our experiment. Please next. The reactor contains 1.2 kg of La 0.9. So this is the experimental parameters wherein we have varied desorption temperature to select different flushing and desorption temperature, and also we have varied the supply pressure, and for impurity we have used 10% CO2 impurity, and we have done 25 cycle of studies. Next. So this is the activation cycle wherein 1.2 kg of alloy was able to store nearly 15.82 gram of hydrogen, which was nearly 1.328%. And this alloys was used for the further studies. Next. So in order to determine the absorption, desorption, and flushing temperature and pressures, so we did a parametric study wherein we observed that the suitable flushing temperature for this alloy was below 20 degrees Celsius, and the absorption pressure was above 5 bar. Please next. So herein we did the cyclic study wherein we did 25 cycles with CO2 study. So we can see here that there was a significant drop when the cycle from first to 25th cycle and also there was a reduction in the reaction kinetics as the bed poisoning characteristics of CO2 impurity was getting affected. In the second figure, we can observe that cycle 10th showed a very bad result. That was not because of the system problem. That was there was a failure in pump. Next is heat transfer fluid was not able to recirculate. So regeneration after bed poisoning, we were able to regenerate our bed within 2 cycles. So we can use this alloy for several thousand cycles, as we can regenerate it after every defined number of cycles depending upon the impurity content. Next. So I have not shown here the GC results limiting the time. So this alloy is very suitable for hydrogen storage and purification application, wherein we can store the hydrogen at low temperature and pressure, and also we can use it for hydrogen purification application, and wherein we can achieve excellent result. So GC result I am not showing, but I will tell that we got around nearly for 20% of impurities, we received 100% pure hydrogen after desorption. Next. So this is the acknowledgement. We would like to thank DST Center Project, Center Hydrogen Project, for providing the fund, and this system is already patented, and soon we will disclose this thing. Thank you, and for a question, you can directly contact to my email ID.
Okay, thank you very much. We will contact you direct for question.
Thank you, sir. Thank you. Thank you for
giving. Thank you very much. Nice work. Very good work.
Thank you so much all the participants for showing your zeal and efforts to make this session successful. And I also want to thank you, our chairpersons, Professor Kedar Singh and Dr. Rajesh Kumar, that you gave your valuable time to chair this session and make it successful. Thank you so much, sir.
Okay, thank you. Thank you for organizers and also participants. And also thank you very much. We are running late. Okay, thank you. Thank you.
It's a request to the chairpersons that the marks you have allotted to the participants, please send it directly to the winner of this conference, Mr. Chhagan Lal.
Sure. I will send you. We will send you. Okay.
Excuse me, sir. What about my presentation? If there is any announcement for this?
Oh yes. What is your name?
Kedar
Abhishek
sir.
Parida, sir, paper ID 5205.
Kedar sir.
Who want your presentation?
Kedar,
Wait, I have also the presentation 05159.
Okay, both of you, please wait for a while. We are creating a break room for both of you. There you can present your.
Ma'am, ma'am, my poster are also
Thank you,
left.
thank you. Okay.
Hello.
Please give, next time for, this is the Abhishek, what is the name? Abhishek Parida. He
Yes.
can.
Yes, sir.
Sir, I also want to present my poster.
Next round, right? Next round. Okay, Abhishek Parida, please
Yes, sir.
present your work in next slot. Eh?
Sir, ICRE team said, hello. Hello.
Participants, can you listen to me?
Yeah, we can listen to you.
Request to all of you that who are remaining for the presentation, please wait for a minute. We are creating some break rooms for you. There you can present yourself. Okay?
Okay.
Okay, then moving forward, let's take the pleasure of listening to the honorable and great speaker. Here I am talking about Professor Yogendra Kumar Mishra. He is currently working as Professor MSO at Medsklosion Institute, Nanosid University of Southern Denmark. He worked as group leader at Kiel University, Germany. He did habilitation in material science from Kiel University in 2015 and PhD in physics in 2008 from Jawaharlal Nehru University, New Delhi. In Kiel, he introduced a new flame-based process for metal oxide tetrapod nanostructuring and their 3D networks, which showed many applications in engineering and biomedical fields. At Nanosid, he is heading Smart Materials Group with the focus to develop new materials for green and sustainable technologies. So now I will request Professor Yogendra Kumar Mishra to deliver his talk on the title Tetrapods Based Smart Materials for Advanced Technologies. I welcome you, sir.
Good morning from Denmark. Can you hear me?
Yeah,
Yes,
yeah.
sir.
Good morning. Good morning. Good morning.
Is our slides visible?
Yes, yes.
Yeah. So can I continue?
Yes, yes, please.
Yeah. So good morning, everyone, and I'm very happy to give talk about on Sunday. It's very nice, and I have been to Jaipur before very long time, so I would really like to visit sometime when the situations allow. So, well, thank you for the invitation and your kind introduction. And the topic of the talk today is about tetrapod-based smart materials for advanced technologies. So, energy is an important topic. Definitely, we have to think about different ways of how to harvest energy, whether it's renewable or batteries or whatever. But everything is lying behind the materials, because materials are the key components everywhere. So this talk is mainly going to be a focus on the material development, how to develop new class of new type of materials with kind of improved performances. Well, the image you see at the bottom is our campus here in Sonderburg, and the city is divided by the sea line into the two parts. So this is how our campus looks like. You are more than welcome to visit us. We are Sustainable Development Goals University. Let me see if slides. Yeah, and a little bit about the University of Southern Denmark is fairly young university in the range of 20 to 25 years. It was basically created out of merging different engineering colleges in the Southern Denmark region. And we are located here at the Germany border in the Sonderburg campus, where the image I have shown. We are completely focusing on cutting edge material research for advanced technologies. We closely work with the industries in a way to ask to know what are the exact demands in terms of the material developments, and then we align our focus. So we have very strong academic and industry environment together, a technological focus. And despite of being young, university has made really a good progress in overall number of students and funding program. We have state-of-art clean room with advanced facilities, And on the top of that, we have advanced characterization facilities like helium orine microscope, 3D tomography, photoluminescence, time resolved photoluminescence, chemical imaging, and many other equipment. So we are very well equipped. And we are always looking for new collaborations. We represent more than 90 nationalities. We have international students, international master's program. So it's just for your knowledge, if somebody is interested, we will be happy to work together, definitely in collaboration. Well, the topic of today is about need of three-dimensional nanotechnology as a motivation, why we need three-dimensional nanoscale materials. And the background is like this, that since 3 to 4 decades, we have been working with nanoscale materials. We know very well that when we break the material from bulk to nanoscale level, the overall surface goes very, very high, and that leads to the new properties into the material system. This we know already, and we have developed already many ways how to kind of make these nanoscale materials by physical methods, by chemical methods, by biological, and many other methods. So we are at the situation now we know exactly how to grow these different nanoscale materials, nanowires, nanotubes. We are able to change their length scale in a controlled manner. That is also something we are successful. Also, we understood their properties in detail because we have nowadays very advanced techniques to investigate each and single nanowire. Even we can see atom by atom into the high resolution translucent electron microscope. So we have gone very far away with respect to the development of nanomaterials and understanding their properties, novel properties. But where is the challenge? The current situation is now, since last 1 decade and 10 years, that we know there is a material in this form. It has very nice, very excellent, unique properties. We also know where these properties are going to be helpful in which particular application. But how to bridge this gap from nanoscale materials to utilizing those properties into the daily life application, that has been a challenge. How to utilize those nanoscale surfaces in simple and efficient ways has been really a challenge, and there we have been working on. For example, nanomaterials individually, they try to agglomerate, and this is something what we do not want, because then we are limiting their surface accessibility if they agglomerate. If we want to make a kind of, for example, a sensor device using nanowire, we first have to make a nanowire, and then we need to somehow go to the clean room, or we need a process how to integrate a nanowire, how to connect it to the external device so that we can measure something, a change in the resistance or whatever. And this involves large number of steps, and that is leading to overall high cost. So there we have a problem actually. And in this way, we came up with an idea that what if we develop a new form of nanomaterial that is like a large form of nanomaterials in 3D form and made out of nanoscale elements like a sponge in our kitchen. That is a perfect example of if we could arrange our nanoscale elements somehow interconnected one-dimensional nanowire networks in a sponge form, then we do not have the problem in utilization. We can easily utilize at large dimensions these nanoscale materials, and the surface is also accessible in the efficient way. Also, one thing which might wonder you, here you can easily see that how the material architecture is able to introduce new properties into the material system. If it was a solid polymer, you cannot block, you cannot bend it, you cannot hold, kind of break it or whatever. But since this is Yeah, since this is a kind of probably 1/100th amount of the polymer material, porous form, interconnected network form, you have the possibility to bend it, you have the possibility to squeeze it, you can hold the water, you can release the water, chemicals, whatever. And if you think from quantum mechanics point of view, if you are squeezing, then the distance between the nanowires is individual nanowires is getting low and high accordingly. So in that way, we are able to tailor the scattering mean path if we are talking about the scattering of light. So there are a large number of possibilities if we could develop such a material in this form from any material, from metal, ceramics, oxides, whatever. Yes, the question is how to develop this new class of material into the three-dimensional interconnected network form. We can go back and we can talk in the same way like we were talking in the beginning of 2090s, that we could take a top-down approach or the bottom-up approach. In the top-down, we can take a bulk material and we can selectively try to etch using chemicals to design kind of porous materials, highly porous material. That is complicated process and we need a lot of material. Other way around, we try to interconnect, make nanowires first and then try to interconnect them together in a kind of network form. That is also a very, very complicated task. So developing spongy materials by simpler processes has been our main motivation in last 1 decade, where I am going to tell you some details about. Yeah, this is our smart materials group, and our inspiration basically started from the tetrapod building blocks. If you are walking along the coastal area in Mumbai at the beach side, you will easily see these tetrapod type of building blocks around. And this is a very nice morphology in the sense that does not matter how we put it together, it is going to form a self-assembled three-dimensional network with a random degree of porosity, and this random degree of porosity is giving a lot of examples. So we got motivated and then we decided to grow these micro and nano scale tetrapod type nanostructures into the laboratory. This is how they look like. So our main aim, main target is that we are growing these zinc oxide tetrapod nanomaterials, and then we are utilizing them in many different applications in different ways. We are doing functional engineering with the help of kind of group members and collaborators worldwide. So we actually developed a simple process for growing this zinc oxide tetrapod nanomaterial. It is not very easy, but to grow these tetrapods by simple physical methods, and that too I mentioned. So if you are looking for industrial applications, we need to really grow into the large amount. Then we need a process which could be upscalable. So after several kind of attempts, we were successful in developing a completely new method. It is called flame transport synthesis method. This is again based on the kitchen. If you take simply zinc metal particles, some micrometer diameter, mixed with polyvinyl butyrol as a kind of sacrificial polymer, put into the crucible, heat it at high temperature, the polymer burns, and then the flame carries these metallic particles into the kind of flame on the top. Then is converting these metallic particles, zinc particles, into that zinc atomic vapor, and with the combination of native oxygen around, we have nucleation and the growth. And there are several possibilities that if we want to grow well-defined structures from zinc oxide 1D structures, then we can mount a substrate on the top. Exactly. Then we have one-dimensional growth. You probably know that zinc oxide is having hexagonal wood side crystal structure. That means that the C-axis is the fastest axis growth to minimize the overall energy of the material to energy of the structure. If we do not apply any catcher substrate like this, then we have the possibility that first it is a free fall like growth. We have first a growth of a nucleus, which is octahedral in nature, and then after nucleation has happened, we have growth along the four facets, which is again the C-axis growth along 001, and this leads to the formation of micro and nanoscale tetrapods. And this talk is mainly going to be focused on the tetrapod growth. This is how the process looks like. Basically, it is a solid vapor, solid growth process. So we fill the crucible, we put it into the oven, we heat at high temperature, how the crucible looks like while the process is going on. And then after cooling down the furnace, the crucible is filled with the white powder-like material that is made out of zinc oxide tetrapod material. And the typical kind of representation you see here, that these micro nanoscale tetrapods building blocks, when they are put together, they form a self-assembled three-dimensional interconnected network. It is still a loose network, not a solid network. But if for example, if we heat it, then we have the possibility to form the interconnections at the junction. I will tell you later. And then we could form a sponge-like material out of these tetrapods, kind of, which is the ceramic material. Well, what is very important thing here when we talk about the nano, then the surface is very important. And these are 4 1D structures interconnected together via central core. So definitely 1D is important here. And if we can tune the dimension here, aspect ratio a bit, that means that we are able to kind of further improve the properties of these tetrapods. And that can be easily done by changing the parameters into the flame process. If we change the temperature and the other experimental conditions like oxygen gas inlet and the precursor material, we can make really very ultra fine tetrapod like structures with very high aspect ratio arms. So they are offering much more surface accessibility. You might wonder that when you go from bottom to top of a single arm, that it is a smooth conical surface, conical structure which is going through. That is not actually the case. Here I would show you a movie that when we go from bottom to top, we can observe a lot of kind of structures which are having a staircase structure. And we know that, yes, the surface is the most important thing in the nanomaterial, and every restructuring at the surface is going to contribute additional surface. And this, in this particular form, we have right access to this surface accessibility in a way that they do not collapse together. And this really gives us many more opportunities in terms of applications. Well, we can take the tetrapod powder and fill into the molds with well-defined volume, and the amount we can decide. So volume, the mass divided by the density, is the density which we can control into the three-dimensional networks. And afterwards, this mold is heated to high temperature around 1200 degrees centigrade for 5 hours. And in this way, we could design these three-dimensional interconnected networks with very high kind of, and well, they look like a sugar type network, but they are made out of zinc oxide and tetrapods. And the advantage of these networks is that they are having a porosity of around 95%. That means we can even also, by selecting the initial amount, we have the possibility to change the porosity. And here the porosity is just opposite to the kind of network density, that these networks are highly flammable, highly porous. High temperature is stable because of very highly porous in nature. If we subject it to the high temperature, the structure is easily able to lose the kind of additional thermal energy, leaving behind a kind of much stable and maintaining the shape of the entire network. This is light in weight compared to the conventional zinc oxide. and it is having a rubber-like Young's modulus in the range of few hundred megapascals, more or less, that we can also tailor. So it's kind of be having like a flexible ceramic material, and in this this actually offers a large number of possibilities towards applications and the material engineering. I will tell some of them. Please let me know how much time. And now I will, so well, you can ask, okay, what about the applications of these tetrapods materials? And I'm going to give some examples here, more or less, that yes, what a typical culture in the entire material research community, that if we develop a new material, we are always first going for the sensor. If it is a metal oxide, and zinc oxide is definitely a kind of a good candidate. So in the same way, we got motivated and started kind of making sensing devices. So if we want to make a thin film based sensing, we have to deposit the thin film first, either directly on the contacts, or the contacts are deposited afterwards, and then we have only the surface area on the top, which is access for the sensitivity. So imagine that sensing is nanowire based sensing is something that something is coming and touching to the surface, and the nano element is giving a kind of, it's a reflection, either the change in the resistance, current, or of any optical property, thermal kind of impedance, whatever it is. So making nanowire based sensing device or thin film or nanoparticle is, first of all, is a difficult task, and then we have limited surface accessibility, because some surface underneath is already covered, that is not accessible. In this way, this tetrapod based network has a much better advantage in the sense, because what we can easily design a kind of self-supported highly porous bridge as a kind of sensing element, nano element, and then we can directly mount it onto the desired substrate, where we have very high surface area accessibility, and that worked quite successfully. We designed such a device, and then we were using for UV and the gas sensing. We understood the mechanism carefully and the different conditions, so that is nearly well established. The width of the conduction channel accordingly changes under the exposure, depending upon the type of the gas. And this can be extended to different type of sensing models. We are somewhere here to the environmental sensing. Even sensing with the large object is not easily possible with the nanowire, because nanowire has a smaller surface area. So even if there is a large object, for example, a cell is coming, it will only touch a limited surface area. So the reflection will be only from that area. But here in the network kind of devices, the cells can easily move, bacteria can easily move inside the network. Then they will be able to touch to the many surfaces, leading to the increased response of the device. So in this way, this offers a much better geometry for the sensing behavior. Of course, they are 1D structures, and that you know from your general knowledge. Also, glass rod versus glass fiber. If you try to bend a glass rod, it is going to break. But if you try to bend a glass fiber, you can easily bend and kind of put into the pocket, because of high surface to volume ratio, high aspect ratio. In the same way, these 1D arms are bendable up to some certain extent. The bendability depends upon the curvature, depends upon the aspect ratio. And here, if the substrate is bendable, then the flexible sensing devices can be made. Often one desires a high temperature, sensing into the high temperature environment. Of course, if the substrate is stable, then these zinc oxide nano networks are stable up to very high temperatures. Additionally, you might be knowing, who are working with zinc oxide, that zinc oxide has a non-centrosymmetric hexagonal Woodside crystal structure. That means if you bend, then you are going to develop the opposite potentials across a potential gradient across the edges. If carefully connected to the external kind of electronics, then you will have the possibility to harvest some power. So that opens the direction of designing self-powered network-based device, piezotronics. So there are, and on the top of the network, we have all those nice properties which are accessible in form of sensing. Well, when think about sensing in the laboratory, we know which gas we are putting on the device, so then we know what are we sensing exactly. But what about taking this sensor, go to the university road, and then if it is able to tell which gas it is sensing, that would be so selectivity is very, very important aspect. And if you are working with kind of chemistry, please keep in mind that zinc oxide is a very rough and tough material with respect to physical conditions, but chemically it is unstable. It behaves like sodium chloride if you subject it to the solutions below 5.5 pH. So in the chemical environments, one has to think about it is going to melt away. That's something. And there are a lot of other compatibilities one has to think about. And we have tried to address them by designing, by kind of functionalizing them with different elements, and also developing tetrapods from new materials. I will tell why. So we have been working in this field since a really long time and have developed some knowledge. There is a kind of nice review about kind of materials, gas, which material works better with which gas, and what about the selectivity. If you are interested, please have a look on this review article. And now, since the last couple of years, the sensing community is more focusing, going into the biomedical sensing direction in a way, because often we diagnose disease at a very later stage. So if there are opportunities to get some information, to get some information about these that kind of diseases, then probably the cure will be easier. So, and often it is not only possible by a single component. We need to kind of put several, design a multifunctional platform. So there kind of, we are also trying to combine the toroidal approach with respect with zinc oxide networks together. We are trying to integrate. And what could be the best possibility, that if we have a single platform which can offer the diagnosis and the treatment together. So we are slowly making the transition in this direction. And if you are interested, please have a look on this review article. And yeah, so that is one dimension. And the second dimension, application direction, is of course composite engineering. Many of you are working with composite materials because they are the one which are surrounding all our life, nearly starting from the coating into the kitchen frying pans to the plain wings, more or less. These are polymeric material, and often we put nanoscale elements, nanostructures, nanowires to improve their mechanical, electrical, and many different other properties. And while designing composite materials, we often talk about the kind of agglomeration of nanostructures, wires, and tubes, simply because in the composite form, we do not want to have the agglomeration. The agglomeration is a weak point into the composite. So if the composite will break, it will be directly from these kind of agglomeration points. And in this way, these tetrapods, or these self-assembly nature, really help a lot. That does not matter how we place them together, they are going to form a self-assembled three-dimensional interconnected network. So they will not agglomerate together. And that gave us a very kind of good opportunity in terms of polymer engineering. We have been able to demonstrate increase in the Young's modulus, increase in the toughness, robustness, electrical, mechanical, and many other properties in a very good way. Not only this, we can use them as a kind of filler element, and then we can also use a standard zinc oxide function, luminescence, and other functions. Also, we can use them as a support element to put to distribute if we want another nanostructure on the top of it, so that to make sure that all these nanostructures are uniformly distributed inside the composite material. For example,
Professor Mishra.
Yeah.
Sir, sorry to interrupt you. Sir, please, it's a request. Can you sum up it in 5 to 7 minutes, as we are running?
maximum I will do that. So basically we took the spiropyran molecule on the top, and then we homogeneously kind of put into the composite material, and that composite material is able to change its color under the impact of some light, heat, and kind of the force. So the composite material is able to tell about any internal damage itself. So that's and now we are also kind of designing the composite material which is able to tell the damage, any internal damage, and also it's able to repair the damage. So this goes in the direction of advanced composite engineering. And then basically biomedical, because whenever you develop a new material, always you look for the scope in the different direction. And together with colleagues from Chicago, we found out that these tetrapods are able to bind the viruses, and they are able to neutralize the viruses over time. And this worked first. So basically tetrapod surface is really good kind of place where viruses are getting sticks, and due to its inherent properties, they are normalized. So we did this detailed studies since 2010, and this concept is working for many different viruses. This is a well-established topic now. On the top of that, with the new nanomaterial, we should be careful that it should not be highly cytotoxic, otherwise it will not go long into the biomedical engineering. So here our tetrapods are very low cytotoxic. And to keep this story short, I can tell you that the zinc oxide tetrapods, first mice was infected with virus, genital herpes virus, and then it was treated with tetrapods, and which these mice survived really long as compared to. So these tetrapods are able to bind the viruses, they are able to trigger the cell signaling that WBCs go, and then they can really grab the virus, and they are also able to promote the cell growth along, so better wound healing, faster wound healing capability. So we are at this level that animal and human studies are on the process, very positive results, and we have a company which is going to launch a product very soon. Something you might be knowing into the background from the coronavirus time, that people have been taking zinc-rich tablets because zinc is a very important element for our human body, controlling metabolic reactions. And if zinc oxide goes into the body, it can be decomposed by acidic medium. So this is important biomedical material. And not only this, these tetrapods can be used as a fill-up material to design advanced fibers and base membranes for biomedical engineering. For example, here we have demonstrated the to stop the bacterial growth at the root canal at the gingiva. And these stitching tapes into the band-aids, and also these fibers which are used in this wound care, there we could also engineer antimicrobial and antifungal properties. So we are able to integrate zinc oxide tetrapods like this into the PCL fiber, which are used as a stitching in the kind of wounds. And this really gave a much better response. And these fibers are also antiviral in nature. They are able to bind the viruses, and then they are able to neutralize the viruses. And even if we engineer the surface in a controlled way, we are able to load the drug on these tetrapods, and we are able to release into the controlled environment by the kind of light in a way. So this goes in the direction of advanced wound healing and wound dressing, more or less. So the last kind of topic I would like to address here, that with this success, whatever I could talk hours, days, and months, the applications of these tetrapods, we have been very successful. But then the question arises, can we grow these tetrapods from all the materials by the same process? The answer is no, because it is the material, their properties decides how they want to grow, and then the experimental condition. Zinc oxide is very robust in the sense, but other metal oxides not. However, we found a way to develop these tetrapods from other materials by using them as templates. We can deposit something on the top, and then we can remove the underneath backbone, and in this way we have used them as a template. You can use any process, chemistry, physical vapor deposition process, chemical vapor deposition process, whatever. And this simply works like this, that you take any solution, for example, infiltration approach, they are carbon nanotubes based solution. And then after you infiltrate, it is homogeneously wetting the entire network, and afterwards this is now a composite material. If we want, we can easily remove the underneath zinc oxide tetrapods, and that is going to give the new material into this tetrapodal scaffold form. And if we want, we can put further kind of any new function on the top of it. We can put multiple materials together. We can design completely new multifunctional materials. Starting, for example, this is a PDMS 3-dimensional network, but we are able to design. It is super hydrophobic despite of being very porous more than. So our main focus has been to engineer different properties of those tetrapods in a kind of careful way for different application, because we know here we have high surface accessibility. So with the kind of adding activated carbon nanostructures on the top, and the composite material based on tetrapods showing very nice capability to remove the chromium from the dirty water, and putting magnetic nanoparticles on the top and nanowires and nanorods on the top, and sealing them together with PDMS. A composite material is able to remove the diesel from water. So that is also very putting copper oxide nanoparticles on the top of tetrapods. The composite, the hybrid structure has to several functions together. It can decompose the dye using visible light, and it can also remove the heavy metal ions from the dirty water. So using this approach, we have been able to convert nearly all soft and hard material into the 3-dimensional scaffold geometry. And these carbon nanotubes network have shown as a very good sulfur cathodes and as a catheter for biomedical engineering, and also carbon nitrogen doped tubular carbon has shown very good supercapacitor abilities, zinc and capacitor abilities.
Sir,
Yeah.
sorry to interrupt you.
I'm done
Sir,
in a
it's a
minute.
request. Okay.
In a minute, yeah. So basically the gallium nitride behaves like a liquid marble. It is not very easy to convert gallium, to grow 3D gallium nitride and the boron nitride. So we are focusing completely this new class of materials, developing this new class of materials and putting several functions together to design completely multifunctional materials to meet the demand for their applications into our day-to-day life. So with this, I would like to kind of come to the last slide as a kind of conclusion and outlook. It is actually an outlook that after working so long into the field of zinc oxide, I could comment that along with the material properties, the shape also is very important, and this tetrapod shape has given very nice opportunities in the direction of accessing surface, having nanoscale surface, how to access, engineering further properties, making new materials, and putting kind of into the right form where we have the right accessibility. And zinc oxide, as a material, engineering its natural properties like defect and other thing, there is a much more scope being left. So this field is going to be much advanced in future, and we are trying to learn day by day the new opportunities. So with this, I would like to kind of end up my talk, and I kindly request you to have a look on these review articles for more overview, especially the materials today. And I would like to say thank my colleagues, working colleagues. Previously, I have been in Germany for a longer time with Professor Edlung. Thanks to him and the funding agencies and the colleagues in Denmark, and the funding agencies, Max-Clausen Fund, BIOL funds, and European Union. And I have been working with collaborators worldwide because this is definitely very helpful in understanding new properties. So with this, I would like to say thank you very much for your kind invitation. I have been fast enough in the last part. So if there are any questions, I will be happy to answer. And if you are looking for collaborations, so we are more than welcome to help you out. So with this, I say thank you very much, and thank you for the invitation again. Okay.
Okay. Thank you, Professor Mishra. This is a very nice talk. Really, it's a very good talk. There is one or two questions from audience side. Query, then please.
Hello.
Yes, please.
Hello, Yogesh.
Yes.
How are you?
Good, very good. I'm so happy to see you after so long.
I hope now you will not even come to NSC as a director.
You never know. I'm still like the same, like we met 20 years before nearly. I think we met nearly 20 years before. So I'm still with the same spirit, keep on working for science, whatever we can do.
Very young and young professor.
Yes, it was all your inspirations, more or less. I remember those good old motivations you have been giving to us, and I keep on asking about you with different kind of colleagues. Thank you very much, and I wish you very good kind of health and everything. Please be safe, and I would really like to see you sometime in Jaipur.
We were in contact, but suddenly you disappeared for last 10 years.
I don't know. Maybe you disappeared. So I got quite busy, more or less. Let's see. In a way,
I like this thing. You are doing wonderful work, and you are living in a beautiful city, beautiful country also. Denmark is a very good country.
Yeah, apparently I'm still living in Germany, and I'm able to make this combination of Germany and Denmark. So I live in Germany and I go to Denmark every day to work. So it's 110 kilometers away, but I'm commuting every day. But it works perfectly. It works perfectly. This northern Germany and southern Denmark.
Coming to India then?
Usually I come usually every year, but since Corona, it has kind of made little bit complicated. I was locked in Lucknow 2 years back, and now thinking to visit at least in next month. So I will be in India, for example, in May or April and something. It's not freeze, but there I will be there. Yeah. And I will definitely be there in Jaipur too. That's kind of I already have got a lot of invitations.
You come next time, come to Jaipur also.
Definitely, this is now in the agenda. I have been invited by several colleagues already. So really, and I'm looking forward to see you.
Thank you. Okay.
Yeah, most welcome. So happy to see you.
Very nice talk, Yogesh.
Yeah, most welcome, Rajesh. Yeah, I'm very happy to see you. It has been a long time.
Very long time. Yeah.
Good.
So when you are coming to India?
More or less at the end of April. That is not fixed the schedule, but more or less is going to be. It will be a really kind of. Yeah. I will let you know as soon as.
Oh, okay.
Formalized. Yeah.
When you come back to visit our university.
Yeah, definitely. You are in New Delhi, so I should.
Yeah.
I mean, last 2 times it has been happening that somehow I didn't stay in Delhi. I directly flew to Lucknow, and also last time it was Corona, but since 2 years it has been. But I hope you all are kind of keeping your health at a high level, under the proper and the secure conditions, more or less.
Yeah.
I don't know if there are any questions. I will be happy to answer from candidates.
If
Otherwise,
there is any question, please ask to Professor Yogendra, I think.
Otherwise, I'm reachable via email to whatever
Professor, Yogendra, I have one question really.
Yes.
This is Professor Kedar Singh, School of Physical Sciences, JNU.
Yeah, thank you very much. I remember you and from my early days, so I'm very happy to talk to you. Indeed. Yeah, please.
Okay, thank you.
Please.
Yeah, my question is this: how we can control, this is the shape of this is the, this is the nanomaterial, tetrapod, some other material. There, could you please focus a little bit?
Yeah, basically the shape of the tetrapod growth is due to this kind of nature into the solid vapor solid kind of growth process without applying any substrate, because if we apply a substrate, then we are offering a boundary condition to grow along a particular direction. We are offering nucleation sites, but if we do not apply, then this is the optimum possible geometry what is going to grow into this flame process. So if you follow the same using kind of wet chemistry, then you are going to end up with multipodal particles, because in the chemistry it is very difficult to control the environmental condition. Even if there is a change in the fraction of a second in any parameter, it will change the morphology. I mean, zinc oxide is very good material in that sense. For nanostructuring, whatever chemistry you do, you will end up with some kind of complex geometry. And that is also a drawback. I often start my talk with the comment, please do not work with zinc oxide. There are more than 1 million papers existing already. So you want to start your career with something which has not been done. But in the flame process, actually, the kind of in our process, the flame is offering a much better control in the sense in this flame environment, it provides a local control over the oxygen content and also atomic zinc vapor, and that is very helpful in terms of kind of initiating this growth process, and then coming out that this tetrapod is the best possible energetically favorable morphology, which is leading to growth of this. And this works. This has been kind of successfully demonstrated since last 12 years. I have been more or less kind of doing that. So that is the that is a well-established process, I would say.
Okay, thank you. This is really very nice talk and also very good work. Really, it's a very
most welcome. Most welcome. I will be visiting JNU. Some of colleagues have invited, so hopefully we will have some interaction. I am very happy to belong.
Yeah, sure.
to JNU family. So it's very nice. I'm happy.
We will contact you very soon. For
absolutely. More than I did PhD from JNU already, so I really enjoyed that privilege, more or less. Yeah, thank you.
Who was your supervisor? Sorry,
I did with Dr. Devesh Avasthi, so it was from my USC in New Delhi. DK Avasthi.
Okay. Okay, thank you.
Most welcome. Most welcome.
Okay, thank you.
It's my pleasure.
Yeah. Yes, if there is no question, then now I again thank Professor Yogendra Mishra for very good and very nice talk. Thank you again. Okay.
Most welcome. It's my pleasure. Thank you very much.
Now I would like to welcome our next invited lecturer from Dr. Subramaniam Sappathy. Dr. Sappathy has been research assistant in University of Hyderabad and a short-term visitor in Abdus Salman International Center for Theoretical Physics, Italy. He has been researcher in Raman Research Institute till September 2011. Currently, he is Associate Professor in Department of Physical Chemistry, Gdansk University of Technology, Poland. Today, he will share his knowledge on descriptors to predict dye-sensitized semiconductor-based photocatalyst for hydrogen evolution reaction. We welcome you, sir.
Yeah, am I audible?
Yes, yes.
Oh, thank you. Thank you for the invitation. How much time I have? Is it half an hour or?
You have 20 minutes really. If you complete 20 minutes, this would be better really.
Yeah. So actually, I think the previous speaker spent a lot of time on the zinc oxide.
Yeah. So that's
I
right.
mean, it's a good start for me in order to continue that work, like in terms of the computational perspective. Yeah, the title of the talk is Descriptors for Predicting Efficient Dye-Sensitized Semiconductor Photocatalyst for Hydrogen Evolution Reaction. So basically, currently I am working in the Gdansk University of Technology, Poland. It's closer to the Baltic Sea, where it separates Poland as well as Denmark and other nearby countries. So the work for which I performed in my PhD in ICRE Pune with Professor Prashanjit Ghosh. So this is the view of Gdansk University of Technology main building, and this is the current view in Poland. And this is the overall view of the entire campus. And there is this is the chemistry building where currently I'm working here. And there are a lot of engineering buildings also nearby. And it mainly works on both applied science as well as other basic science also. Now, I'll quickly go to my research activities, like basically divided into 4 categories. I work till the date. I started my career in 2009, Masters in University of Hyderabad. So since then, I'm working on these computational aspects, like mainly on drug molecules, descriptors, and hydrogen bond networks. Now I moved to biophysics, where my current research stands here. So in drug molecules, I explored anti-cancer, antiviral, and antifungal. In the hydrogen bond networks, I mainly focused on proton-coupled electron transfer, excited state proton transfer reactions in the dye molecules. Now, also works on ATP hydrolysis, where I focused on the hydrogen bond networks. This is my PhD works, where I spent quite a bit time in photocatalytic water splitting with zinc oxide, titanium oxide, and silicon nanoparticle, and iron oxide nanoparticle, and some palladium cages. So in these aspects, I will discuss more today. And later, currently I'm mainly working on this particular lipid bilayer DNA proteins and radiolytic experiments on nucleotides. So I'm starting my group soon. So this is an advertisement, PhD job opportunities in Poland, Gdansk University of Technology. It published in your access. You can note it down, or I will keep it in the link in the later time, or you can note it down this number. This is currently I will be a co-host along with one more supervisor here. His name is Asik Jub. We are mainly working on these properties, in this area, lipid bilayers and DNA proteins. So my research journey started on in University of Hyderabad, where I worked on descriptors for thermally stable materials. This will help to synthesize new materials for defense, DRDO, India. Then I moved to nuclear quantum effects in an HIV cancer inhibitor, where I studied on ellipticin. Then the descriptors for so this topic we will go through soon. Sorry. During my postdoc, I spent 3 years in ICRE Tirunanthapuram as well as Raman Research Institute, Bangalore. So there I spent some time with chiralities in silicon nanoparticles, and then proton-coupled electron transfers in something like aqueous nanochannel in LLC. Then I moved for finding the drug molecule against SARS-CoV via natural compounds. And even I'm working with medicinal plants in Indian and Indo-Nepal region. So that we got an interesting results also here. So this is the current work which I'm focusing on. So slowly from the pure chemistry and physics, I am moving to the biological way. So that's how my journey started, and spent like most interest like part is like how does proton behave in the confined environment. That's the strong hydrogen bond environment. So these are very common in the protein. So hence, I feel that's an interesting area to look into that. Because of the one proton jumps, the entire behavior of the proton or entire behavior of enzymatic activities or the drug behavior will perturb a lot. So that's a key role to study. Though it looks like very low energy, maybe it's in the range of 10 to 30 kcal per mole, but it's worth to spend quite a bit time in the hydrogen bond and the proton transfer within the hydrogen bond. So the outline of my talk, I will maybe I may not spend much time on the introduction because it's well. This is the last day of this conference probably, and I think quite a bit of talks on this hydrogen evolution reaction. Even the previous talk also on the similar aspects, like one of the application. And so I spent most of the time on the zinc oxide nanoparticle. I don't think I will give an enough introduction for that. No need to give an enough introduction. So this is very explained in the previous talk. And the components of the photocatalytic, this I will spend some time, and the conditions for the photosensitizers. So these are the aspects which I worked like almost like 4 to 5 years, so that I understood which descriptors helps us to give a better hydrogen evolution or hydrogen yield, which helps for the further steps. Now, maybe for the students, this is the good initial steps to understand what kind of computational details we are using and how I'm modeling the system. Then I will go for the resultant discussion and the conclusion, future direction. So we know that these are the basic fundamental reactions in the chemistry, and where we have synthesis reaction, decomposition reaction, combustion, single, double replacement, acid-base reactions. So in the first step, like A plus B gives rise to AB, and vice versa, AB gives rise to A plus B. So these are synthesis, and this is the decomposition reaction. Whereas another possible reactions is AB plus O2, like this is the O replaced by B, and this is the different formulation of things. So in thermodynamic perspective, these are the people are looking into these kind of reactions: water splitting, glucose formation, carbon dioxide reduction, and ADP hydrolysis. So where you can see that the corresponding energy parameters like water splitting and glucose formation is more or less like a similar order, and you can see that CO2 reduction and ADP hydrolysis also in the same region. So just I'll give a brief animated way. Currently, I'm working on this ATP hydrolysis. Just this is the ATP and the triphosphate. Maybe the color codes are replaced here. The important thing is that the bond breakage step and how the phosphate, inorganic phosphate, is forming in within the protein environment. It makes a planar geometry. Later, it interacts with the closest water molecule and forms like a PO3 minus kind of thing, HPO3 minus. So this is from the reaction starts from ATP to ADP, adenine diphosphate. So this is the one of the important reaction which people are looking into that. Yeah, coming to the introduction, in order to split this water, it's not the usually in the world industrial approach is much more common, but which is very expensive in terms of cleaving, like forming this bond. So the clean way is that via sunlight, under the sunlight, photocatalytic way. But in order to decrease the barrier of this 1.23 VV uphill process, it's not that easy to handle. So one should use the photocatalyst. So maybe by now you understood that why zinc oxide is important and why other such nanoparticles are important. So Even though if you use the zinc oxide, though it's that important, but it falls in the UV region, the band gap, and the recomposition is also higher in this case. So what we are doing is like we are sensitizing with the azo dyes, which will help us to decrease the band gap, and as well as the recombination also it will stop because of the interaction between the nanoparticles. And I also tried with different sensitizers. Now the basic fundamentals to understand, like in one picture, we can see that photocatalytic splitting in all the steps. Like for example, charge. For example, if you shine the light, there is formation of exciton and charge transfer to the corresponding cathode and anodes, and the hydrogen evolution will take place in one of the anodes, and then the oxygen evolution will take in the other cathode place. So these are the major important pathways for the photocatalytic splitting. Then if you represent in a the main interest is in the charge exciton formation. And if I understood properly the water splitting mechanism, it results into 4 different components: photon absorption, exciton separation, carrier diffusion, carrier transport, catalytic efficiency, mass transfer. If you see their particular catalytic these cycles, those should work in a proper way concurrently. For instance, like these are first 2 steps are happen in the femtosecond to picosecond region. The shining of the light and the formation of the exciton. Then the carrier, these 2 will happen simultaneously, carrier diffusion and carrier transport in the scale of nanosecond to microsecond. And the final things are, so the first 2 will happen within the low time scale region. It has to work immediately, otherwise the next steps are not that easy to propagate. And these 2 are these 2 means like carrier diffusion and transport will happen both independently and yeah. So what are the conditions for the photosensitized anchor and composite? So first thing is it should operate in the visible region, and home of the molecule should be on the zinc oxide band gap, because as I said, I mainly working on the zinc oxide. And the important thing is the valence band maxima and conduction band minima of the composite should be cradle the oxidation and reduction
Hello,
potential.
Pooja,
Yeah.
you have to let me into the.
Is it okay? I can continue?
It's okay. Okay, please continue.
Yeah. So this is the important thing, which I will show you in the pictorial way in the next slide. How the position of this position matters a lot. Yeah. So I think if people already know this, this is known as type 2 kind of mechanism. And then the efficient electron injection from the excited dye molecule to the empty conduction band of zinc oxide ZNO. So if this is not happening, then the recombination will takes place, and it may not propagate to the further cathode and anodes. Then the prevention of electron hole recomposition. These are 4 important parameters in a schematic way. So this is the zinc oxide band structure. Let us suppose the density of states. This is the conduction valence band of the zinc oxide, and this is the conduction band. These are the dye molecules, and this is oxidation reduction potential of water splitting. So the previous slide, this particular point, what it means that both oxidation reduction potential should be in between these things, and then the home of the dye molecule should place in between this. This is the very necessary step. Otherwise, the reaction will not happen. Why? For instance, when we shine the light, the HOMO of the electron will go to the LUMO. Then the LUMO, that electron has to go to the zinc oxide conductor band. Then because by external source or some like for example electrolyte, in this case methanol, or something like in between the co-catalyst, where it can take the electron from the zinc oxide conduction band, for instance platinum kind of thing, then it will go to the corresponding anode and cathode to give the hydrogen and oxygen evolution. So what are the things we have to stop, for instance? So these recombinations we should stop. This is the first thing. And second thing is, once electron goes, it should not come back to the hole of the die. This also you should not prevent. And second thing is, this electron should not jump to the electrolyte. That's also not desirable. It has to go to the respective cathodes and anodes, means electron and hole. Now, so how we are addressing this question? Like usually, the moment we are talking about exciton, it's in excite state. One should address with many body excite state calculation, but we are trying with the ground state oxidation potential, which is a cheaper way to address. And this is the way we are trying to address the things. That means that whatever you compute the ground state profile, density of state profile, we are trying to address with that only. But in general, one should do the excited state. Yeah, so this is an electron in the HOMO of the molecule. Let's suppose this is the band gap of the system. When you shine the light, it can go to the LUMO or conduction band minima. So there is several possibilities. The red curve is the zinc oxide density of states, whereas dashed lines, the blue curve is belongs to the molecule. So there are a few possibilities of the, like mostly three different possibilities of overlaps. One is the minimal overlap between the zinc oxide and the molecule, whereas some more overlap, like partial overlap and full overlap. So these are the different possibilities of exciton formation, and where electron is like after how the electron will penetrate to the zinc oxide is very important to understand. So usual when you have an external source, a light, so then this HOMO to LUMO is quite common. Like we'll get in via TDDFT calculation, where we can get from the oscillate strength, then we can understand that how does this electron will jump to the corresponding LUMOs. Now, so what are the descriptors we have to understand based on this? One is that coefficient of injection, like how does the electron of the LUMO goes to the zinc oxide conduction band. And the second thing is, what is the full width of maximum of the overlaps? And the next thing is electron hole separation. That's important. If it is more, then the recombination will be less than the product of these two components. So how we computed? Coefficient of injection is the overlap between the density of states of dye on zinc oxide. That means like how does dye is projected on this. And the second thing is the electron hole separation, where if you see this properly, this is the density of state, like the ratio of the density of state with the position. That means it's a kind of a dipole moment, like it's a effective mass of the electron and effective mass of the hole. Like that's the difference. These are the very important parameter along with the sigma. So this is the playing a major role to understand this. So there is several other possibilities, like it can go to the overlap, it can go to the partial overlap and full overlap. Now, for the students, like just have a look at these particular terms, like we are using plane wave based density functional theory, and we are doing GGA with parameterization, like Hubbard-U parameterization, and I'm using for zinc 12 electron and 6.5 is for oxygen, and ultrasoft pseudo potentials, and maybe the previous talk already explained different possibility of surface, and this is the 101/0, one of the stable, and it's not showing any dipole moment in that particular area. So this is very good for the anchoring the dyes, and this is also stable among all. And this is 6 bilayers we used, and we passivated with pseudo hydrogens in order to decrease the dipole effect from the surfaces. This is 4x2 supercell and 600 plus atoms anchored with the chromophores, iodized and glutathione. Yeah.
Sir, please kindly, if you could sum up in 5 minutes. We are running short of time. Our next guest is with us.
Yes, yeah. So this is the model system we have, where one of the slab we have, and this is the anchoring site. This is the molecule. So maybe now we understood that how does the previous setup I did. So this is the one of the model, and these are the dyes which I took, and this is the density of state of the composite, and this is the HOMO of the molecule, and this is the conduction band minimum of the zinc oxide. So this is the proper fit for hydrogen HER and OER activity. So our important goal is to see that overlap of this injection site, which is the overlap site. So if you find it in a different fashion, then I computed all the electron hole separation, injection, and the product and dipole moment and wavelength. So this is the import. So where we got the highest overlap and like this value. So that means that is the important parameter in order to understand whether this electron exciton will go to the corresponding zinc oxide or not. So in terms of a different perspective, and this is for the again a different different dye molecule. In this case, only this is good for hydrogen activity, not for the both the cases. So I went through another set of dye molecules. We found a good correlation, and on changing the resonance activity, we got a increase change in the HOMO molecule, and the LUMO molecule also perturbed a lot, and the corresponding injection rates as these are the values. And if you change the anchoring site, there is a perturbation in terms of HOMO again, but this is not that strengthened. Anyway, so I will conclude. I will quickly show the correlation between the our experimental and theoretical. So with the three values, we got a nice correlation, but it's luckily not luckily. I mean, like we got CC of 0.98, but is it true for the other dyes? So the question we posed that does it valid for a different family of sensitizers? So we started with this different oligothiophene, and we checked their corresponding values, which are very quick to understand, and we computed this thing. We found an interesting values with the brominated one, and we selected those particular drugs and asked experimental to study those things, and we got their results. And what we found is along with that, so our predicted value is this red point, and their predicted values, I mean the experimental value is this one. Like we got a very less difference. That means our particular way of understanding the descriptors and their evolution, their like those are very important, very good for the experimental to synthesize rather than synthesizing the different set of things. So these are the for injection, electron hole separation, and this combination, we got a nice correlation. So what are the key findings? Like we studied, like most of the sensitizers which I studied are hydrogen evolution HER activity, HER active, and we got some linear correlation. And this is the halogen substituted oligothiophene is suitable for HER activity. And these are the anchoring sites which I tried, compared. In the future direction, I try to understand implicit solvent and explicit solvent molecules. Anchoring with the different functional groups. These are the nanoparticles which I addressed. And recently, this is the work which we have, where I addressed the chirality in the silicon nanoparticle, and it is maybe it will be delivered in the next Tuesday. So this is the latest work, and this is the summary. So in this talk, I mainly addressed with my articles published in the previous years, in last decade, in 2005, 2018, and this one, and the latest article. So thank you. Any questions which I can answer?
Thank you, sir. We have 3 minute question answer session.
Yeah.
Yes, if there is any question, please ask.
Sorry, I went very quickly. in order to cover.
No problem.
Yeah.
No problem. If there is any question, definitely they will ask.
If you guys have any questions in later time also, you can connect me, and regarding the positions also, you can discuss with me. So I'm giving my Gmail information in the chat box, and you can see that your access also. Yeah. Any other questions?
If there is no, then participant can ask you question or you throw your email.
Yes.
So there is no problem. Thank you, Dr. Subramanian, for this very nice talk. This very informative talk also. Thank you. Thank you very much.
Thank you.
Thank you. Hello.
Now I would like to invite our next guest, Dr. Daniel Mirabal Gatia, for the keynote lecture. Dr. Gatia has done his PhD in materials for energy and environment. His research activities are mainly focused on the synthesis and characterization of materials, in particular on X-ray diffraction analysis and electron microscopy. He has been working on hydrogen storage materials for many years. His current research interests include materials for additive manufacturing as metal alloys and applications in energy sector. Sir is the author of many papers on peer-reviewed international journals and co-inventor of 2 patents. He has been the reviewer for international journals, European and Italian institutions. He is also a member of SISM, Italian Society for Microscopical Sciences. We are delighted to have you amongst us.
Now our duty over. This is the session. Hello.
Very happy to have you here. On a short notice, you have come for the talk, and I hope our collaboration will go on. Your work on hydrogen storage is very nice. Thank you very much.
Hello. Hi to everybody. Can you hear me?
Yes, sir. Yes, sir, we can hear you.
Okay. Can you see the screen? Well, yes.
Yes, sir, the screen, your PPT is visible. Sir, I request you if you could kindly switch on your video.
Hope it is, you can see the screen in the right way. I hope you can see my presentation.
Yes, sir, your presentation is visible.
Okay. Thank you very much for the presentation, and thank you very much for inviting me for this keynote lecture. And I really would like to thank also the organizers of this international conference on renewable energy, which is a very interesting conference. And also I would like to thank Professor Jain for our collaboration during these years. I will talk about magnesium-based materials for sustainable energy storage applications, but also I would like to talk about energy storage in general. And I will present something, I will say something about my institution in Italy. And then I will talk about the main scenario, which is related to renewable energy sources and energy storage. And I will talk about hydrogen as energy vector and storage methods, and in particular materials at the solid state, and issues related to reactors. Finally, I will present some activities that we've done in collaboration with the Center for Non-Conventional Energy Resources, with Professor Jain, and also with Mukesh Kumari, who had a fellowship, ICTP fellowship, and spent some time in our laboratories in Rome. And so we'll see something about some results about magnesium hydrides and catalysts, iron-based catalysts. So ENEA is a public body aimed at research, technological innovation, and the provision of advanced services to enterprises, public administration, and citizens in the sectors of energy, the environment, and sustainable economic development. There are some focus sectors, which are not all the focus sectors in ENEA, but the main are related to energy technologies, so renewable sources in particular, energy storage, smart grids, and also nuclear fusion, nuclear safety, energy efficiency, and also strategic raw materials and in studies and on new materials, innovative materials, and new technologies. There are different laboratories and centers, research centers in Italy, and also we have an office in Brussels. Our institution has about 2,500 employees. So let's talk about scenario. So the problem is of course, the use of fossil fuels for energy production. And the use of fossil fuels presents many critical issues related, of course, to shortage and to pollutant emissions. And so one of the solutions, of course, is use of renewable energy sources. But there are some issues related to the use of these energy sources, and in particular, intermittency of supply. So if we could consider different curves, but these could explain you better. What happens is that when you have energy consumption peaks, you could have a reduction. You could have also, depending on the type of energy, renewable energy plant, you could have a reduction of production power. So what you need is to store the energy that you are going to produce when you have the peaks of production, and then use when you have peaks of consumption. So one of the solution could be for energy storage could be hydrogen. Hydrogen, as you know, is an important energy vector, and it could be used for to go toward decarbonization. So no pollutants, no emissions, and production only sustainable products for the environment. As you can see, of course, hydrogen has the highest mass energy density of any fuel. It has quite 3 times the energy density of gasoline. But of course, at ambient conditions, you have that energy content is quite low. You can reach the maximum energy density when you have liquid hydrogen. If we consider this loop, we can think about producing primary energy by primary renewable energy sources, and use this energy for hydrogen production. You can store hydrogen. You can then use this hydrogen for producing energy again, and using, for example, this hydrogen in fuel cells, producing electricity. And byproducts are related only to water substantially in the environment. So it is a complete energy loop relying on renewable energy sources. I would like only to spend a few words on other aspects.
Sorry
Which
to
are
interrupt you, sir. Your slides are not moving.
not moving.
It's
Your
not in
slides are not moving, and I think that is because of slideshow mode. So you can present your presentation without slideshow mode.
Can you see the slides now or not?
Yes, now we can see it.
I'm sorry. I'll try to improve okay.
Yeah, it's okay, sir. Now we can see it.
Okay, so I wanted only to spend some few words about the use of hydrogen for the synthesis of hydrocarbons, which is another solution, of course, to be used in this transient. And you can use energy, renewable energy sources to feed electrolyzers, and produce hydrogen, and then you can capture CO2 and synthesize hydrocarbons for internal combustion engines and for production of energy. This is another activity that is going to be done worldwide. But we talked about energy storage, and in particular hydrogen storage. There are some challenging applications for hydrogen storage, which considers the dimensions of the quantity of hydrogen of energy you have to store, and the energy needed. So part of portable power applications, automotive stationary applications. And what you can see here is that, of course, for portable power, you need to be competitive with batteries, lithium-ion batteries, and it's really difficult to be competitive with these systems. And in the case of automotive, of course, you have also other critical aspects, and in particular, the weight and the volume needed to feed these type of cars. And while in the case of station applications, you have less critical aspects related to, of course, dimensions of the systems. So what we are talking about rapidly onboard hydrogen storage systems, you know that DUE gave some important targets to be reached in order to have a suitable energy storage system for light-duty fuel cell vehicles. But of course, not all these targets have been reached. So you need to have a specific system gravimetric capacity. You need a system volumetric capacity. Then you have you need to the system has to be durable during time and have a suitable charging rates. So there are, and also safety is one of the main problems. So what in the case of vehicles, one of the solutions is, of course, storing hydrogen at gases at high pressure, but you are going to consider system with 700 bars, 800 bars on board. So in terms of safety, could be some there could be some problems. And also, the solutions considered is not only, of course, high pressure storage, but also solid storage and liquid storage. And every one of these type of storages has problems, but what you need is, of course, always a gaseous hydrogen to be fed to fuel cell stack in order to produce energy needed to move the vehicle. And so we can consider this hydrogen supply path. And of course, all the other problems are also related to the not only gas storage, but also to the transport of hydrogen and refueling systems. I would like only to show you this example, which has been realized in Germany. Is one of the first train powered by fuel cells, so using hydrogen, gaseous hydrogen in this case. And of course, they're competitive only in the case when you have to replace all diesel powered engines and where you have high electrification costs. And so the solution was to realize to use fuel cells and in conjunction with hydrogen stored at compressed hydrogen stored in tanks. And also it is an hybrid system because you have also lithium-ion batteries which are recharged during braking, and also when you have surplus of production of energy with fuel cells. So this is an interesting solution which could be the range of this train is 600 to 800 kilometers, and it is a good example of how we could move in the future. But in the case of stationary application, you can see basic scheme that are reported here. So you can produce hydrogen as energy, as I told you, by renewable energy sources, and you can use this surplus of energy to produce hydrogen with electrolyzers, and then you can store hydrogen in tanks before final use. And here they are reported some hydrogen storage solutions, which of course they are you can consider compressed gas, liquid gas storage, but these two types of storing hydrogen has some problems related to high pressures and also the weight of the containers that you're using to store hydrogen. And in the case of liquid hydrogen, you have open systems and you have to spend a lot of energy in order to store hydrogen in the liquid form. So what is could be considered is that to store hydrogen at the solid state by physics option or chemistry option. And there are different families of materials that you can use for doing this. There are metal hydrides, of course, magnesium could be used, but also other elements could be used for storing hydrogen in this at the solid state. And you have different alloys which are known to be useful for storing hydrogen, like AB5, AB2, AB alloys. And then you have complex hydrides, which allow you to reach very high hydrogen content, about 18% of hydrogen in some cases, but the problems with complex hydrides is reversibility respect to metal hydrides. There is also the possibility to store hydrogen by physisorption and with high surface carbons, so carbon nanostructures or metal organic frameworks. But also in this case, what it has been shown is that you can observe some interesting quantities of hydrogen stored only at very low temperatures. So rapidly, I would like to talk about, in general, about storing hydrogen at the solid state and in metal hydrates. What you have is, of course, the thermodynamic, which is controlling these systems. And when you have the reaction of metals with hydrogen, you have heat is involved in these reactions, of course, and so you have that absorption generally is strongly isothermic, while desorption is stronger endothermic. For this reason, these materials could be used also for heating or cooling applications. And what I would like to underline here is that the properties of these materials changes with type of composition, and we have different applications, so different temperatures, different pressures with different materials. So everything is governed by thermodynamics. And this is a simple scheme of hydrogen storage reactor. This is a simplified scheme, as I told you. Of course, you have a material inside in a cylindrical configuration. You have hydrogen inlet and for storing and hydrogen outlet while desorption. And then you have, of course, a system for heat management. In one case, you have to heat the system, or during absorption you have to remove it from the reactor. I would like only to show some results that we obtained on room temperature and rise, only to underline that the thermodynamics is controlling everything in these systems. And we worked on AB5 alloys modified by composition. So we wanted to modify the product pressures and the properties of these materials by exchanging titanium with mish metal, which is a low-cost material, and exchanged some nickel with aluminum. And the application in this case was not stationary, but naval application, so for transportation, but for we wanted to realize a tank for ships on boats on Venice Lagoon, where the temperature is quite constant during the year. And then, of course, we performed some cycling. We studied the cycling behavior of these materials during, in order to understand how the microstructural properties change during time. What I would like also to underline here is that there are some problems related to the realization of tanks and reactors. And one of the main problems is improving heat management in these systems. So there are different solutions. You can see in some cases fins are used, for example, aluminum fins, where when aluminum is compatible with these materials, and or, for example, also foams have been used. So as I told you, you have to remove heat during absorption. You have to supply it during desorption. And also there are other examples performed at CNRS in France, where you can use copper fins. So, and you can use, also the system related by McPhee, where phase change materials have been used. But what I would like to tell you is that these are quite old problems, not really completely successfully resolved, because also in 80s, during 80s, Daimler Benz realized the hydraulic containers for vehicles and also for stationary applications. So there is a lot of work to be done in order to improve the reactors, in particular because when you put powders inside these reactors, you have that after long-term cycling, some parts of the reactor are not working at all, and because of sintering on the material, or because of you have entrainment of hydrate particles in the supply or hydrogen supply systems. So there are some mass of materials which is not reacting at all. So you have lowering of the performances of this type of these reactors. So many efforts have to be spent to improve the materials and the, how you put the materials inside these reactors. So rapidly, let's talk about magnesium nitrate, which is magnesium is one of the most interesting materials for hydrogen storage materials, because it reacts reversible with hydrogen, and also it could store. It has a very high gravimetric, quite high gravimetric and volumetric hydrogen capacity. And also it could be cycled for many times, and it is one of the magnesium is one of the most abundant element on Earth. And also you could obtain quite at relatively low cost. And what is very important is that it is quite widespread on Earth, and it is environmentally sustainable. But there are some issues And the issues are related to the low desorption kinetics, depending, of course, on temperature. There is a high stability of magnesium hydride due to thermodynamics. Also, there is a lot of it involved in these reactions. And then you could have a surface oxidation of magnesium-based powders and slow diffusion of hydrogen through magnesium hydride. So what the solution could be mechanical treatments and trying to non-structuring the material, for example, by ball milling. So why ball milling? Ball milling because it creates defects in the matrix, obtaining an crystalline material. It could crack the surface of magnesium oxide on the particles, and also and so you could increase hydrogen mobility, and you could insert in the matrix a catalyst which enhance kinetics, and also it works on splitting of hydrogen molecules and so enhancing absorption and desorption reactions. So here you can see one of the materials we produce by ball milling, which is magnesium hydride with niobium oxide, quite well dispersed in the matrix, as you can see here, some particles. So there is, as I told you before, filling the reactor is not reactors for hydrogen storage. In particular, in the case of very large quantities of materials, is not so easy. It means that if you, as I told you, if you use simply powder, what you have, you could have some problems, technological problems with the reactors. And so what it is possible to do is to compact these powders and to add to this material, to these compacted powders, some carbon-based materials or thermal conductivity materials like aluminum, copper. In particular, what it has been demonstrated is that the carbon-based materials are very good for enhancing thermal conductivity, in particular along radial direction in the case of a cylindrical geometry. Also, what we have done in the past is that we worked a lot on enhancing the mechanical stability of these compacted powders, and in particular, because of long-term cycling is causing swelling. So swelling means that the pellets could return to the powder form, and you're going to obtain lower performances to respect to the starting system. So we worked on understanding this mechanism and also to improve the mechanical stability of the pellets by, for example, covering the pellets with aluminum or copper. And but here we present the results that we obtained in collaboration with Center for Non-Conventional Energy Sources. And what we did, what we've done is we produced the nanostructured magnesium hydride in presence of catalysts, in particular iron and iron oxides. We use this catalyst because it is a very cheap catalyst, and it is why, of course, abundant on Earth. It could be also recovered after after the final use of the tank. You can recover quite every part of the material used. So what we've done is we mix and mill these materials with modified vials under inert gas, and then we also use the expanded network graphite in order to enhance mechanical stability of the pellets that we prepared. But firstly, we started the behavior of the powders. So here you can see scanning electron microscopy images of magnesium hydride with iron and iron oxides, and you can see how the morphology of the materials is going to change dramatically after before cycling and after cycling. And you can see that magnesium ball milling is very useful to disperse the catalyst in the hydride particles. Here there are some results obtained by X-ray diffraction. What we observed is that also probably the reduction of the oxides, iron oxides in the matrix, and also we can observe an increase of the crystalline size during cycling. Of course, with DSC, so calorimetry, we demonstrated that effectively iron is good iron, but also oxides are good catalysts for enhancing absorption desorption reactions. And you can see also stability of in terms of hydrogen released during cycling, and in terms also of kinetics. So this is T90, which is the time to reach the 90% of hydrogen stored in the matrix. So I have to hurry up, I think. Not only powders, as I told you, but also we worked on pellets, so compacted systems. You can see here pellets before cycling and after cycling, so after 20 cycles and after 45 cycles. And you, of course, we have expansion of these pellets, but you can see that the pellets remained quite were not destroyed by cycling, so they gave us good results in terms of cycling. You can see also here kinetics, and we observed a slight increase of the desorption time during cycling, while absorption remained quite the same in terms of kinetics. Here the results are summarized. You can see we cycled about till more than 45 cycles. This is the weight percent of hydrogen stored, and you can see that it is quite it is quite constant in absorption and desorption. And you can see that kinetics of absorption kinetics were performed better during cycling, while there is a slight increase in desorption kinetics. Here you have scanning electron microscopy images of pellets after 20 cycles and after 45 cycles. You can see that effectively there is not formation of cracks on the pellets, even at microstructure level. And here I show the cross section obtained by cross sections of the pellets. So you have the pellets embedded in resin, of course, they're being grinded and polished. And you can see here these black strips are the spandonate graphite, which is going to transport it along this radial direction. These arrows represent the axial direction, so the direction of compression of the pellets. So also here you can see that the shape of the pellets remain exactly the same, even if we observe this expansion volume expansion. So also only I would like to highlight some results within by X-ray diffraction and by Rietveld analysis. And of course, we observed that there is an increase of the crystalline size, which could explain the hydrogen desorption increase time. But what you can see is that it is going to reach the crystalline size is going to reach plateau. So it means that the system is going to stabilize and could work for a long time in reactors. So what I would like to underline here in my presentation is that substantially in order to attain important hydrogen storage systems which are going to perform well during time. You have to enhance the materials and a lot of works have to be done in order to attain a very stable hydrogen storage systems. And even if lots of works have been done in the past, also a lot of works has to be done in the future in order to move toward more sustainable energy systems and technologies. I would like only, before my conclusions, I would like to only show this plan, which is a Italian funding program, a very important Italian funding program, which will last from 2021 till 2026. And it is a national recovery and resilience plan of the Italian Minister for Ecological Transition. And but I wanted only to show that there are 6 missions, and the second mission considers the use of hydrogen in industry and transport. So not only the use of state-of-the-art systems and technologies, so fuel cells and electrolyzers, but also lots of research and development on hydrogen has to be done in the next future. So I conclude here, and I would like to thank you for your attention. Hello?
Hello. Hello.
Yes.
Thank you much, Dr. Daniele.
Hello,
Yes,
Dr. Are you listening to me?
Yes, I can hear you.
Oh, you have given a good talk. I'm very happy to see you here in a short call. And how are you?
Thank you very much.
A good presentation.
Thank you very much. Thank you very much for inviting me, and in this very interesting conference, international conference. Thank you very much and congratulations.
Yeah, thank you very much, sir. And if somebody want to ask any question to Dr. Daniele, please ask.
I would like to say, if you want to contact me, you can find my email here, and you can contact when you want, if you want. So,
sure. Sure. Okay.
Okay. Thank you very much. Have I got to stop sharing my screen, or you can do it?
Yes, sir.
Okay.
Now I would like to invite Professor M.A. Basit for keynote lecture. Dr. Basit is serving as a professor in the Department of Physics of Bangladesh, University of Engineering and Technology, Dhaka. Dr. Basit achieved his PhD degree from the Materials and Condensed Matter Physics Group, University of Glasgow, UK, in 2011. His research interests include transmission electron microscopy characterization of patterned ferromagnetic nanostructures by lithographic techniques. At present in BUET, Dr. Basit is working mainly on preparation and characterization of multifunctional nanomaterials for energy-related and spintronic applications. He has published more than 40 research papers. He is the reviewer of a number of reputed journals published from American Physical Society, American Institute of Physics, Royal Society of Chemistry, etc. In BUET, Sir has established nanotechnology research laboratory for the synthesis and characterization of nanostructured materials. We welcome you, sir.
Thank you very much for the nice introduction. Am I audible clearly?
Professor Basit,
Yes.
I'm very happy to see you here. I
Thank you very
saw
much, sir.
on hydrogen energy. It's very nice to see you here.
Sir,
You are very.
Thank you very much. Thank you very much for inviting me. Am I audible clearly?
Yes, sir, you are audible.
Okay. I've shared my screen. So first of all, I thanks again the organizer for inviting me in this interesting conference, and I'm very delighted to be here. So I think this is the last day of the conference, and you are sometimes lag behind. So I'll not make much delay, and I'll try to short my talk as much as possible. I've already deleted some slides, and within a short span of time, I would like to finish my talk. And I know you have another program later on. So the title what I have selected for today is perovskite nanomaterials for efficient photodegradation and solar hydrogen production. And this is our university. Its full name is Bangladesh University of Engineering and Technology, and this is located at Dhaka. So actually, our university is mainly an undergraduate university. We have only a few students for the postgraduate programs, but right now it is increasing. However, the works that I will demonstrate today in front of you, most of these works are done by undergraduate students, and some of them are master's students. Okay, so the content of my talk is initially I will show you about some brief introduction of perovskite materials. Then I will describe some. Hello. Hello. Is it okay? May I proceed?
Yes, sir. You may continue.
Okay. Thank you. So then I will show some synthesis techniques using some low-cost techniques actually, which are ultrasonication, hydrothermal technique, salt gel technique, and hot injection technique. Finally, I'll show some properties of the synthesized materials and their applications. So, first of all, this term perovskite actually it came to us from from Russian mineralogist Leo Perovsky. And there are different kinds of perovskite materials, and which is there are inorganic oxide perovskites, halide perovskites, and they are also subdivided into different perovskites. My talk will actually emphasize mainly on some inorganic oxide perovskites, and later on I will show some halide perovskites materials. First of all, so most of the studies so far are done based on single perovskite materials, which are cubic perovskites, where, for example, neodymium iron oxide, where neodymium is the center of the atom, and there is B oxygen octahedra. When this single perovskite material is added with similar type of another perovskite, then double perovskite created. For example, neodymium iron oxide and neodymium chromium oxide. When we added them, we obtained actually neodymium 2 iron chromium oxide. This is the double perovskites. And this year we have shown actually by knowing the properties of the single perovskite materials, we can actually determine the physical properties of double perovskite materials, which are experimentally unknown so far most of the double perovskite materials. So this is very common property of the perovskite materials. This is the multiferroic property where two ferroic orders are coincide with each other, coincide together at the same phase at room temperature, and here electric polarization can be tuned by magnetic field, and magnetization can be tuned by electric field, and these are known as the multiferroic materials. And a huge number of research are going on the preparation and characterization and the application of these multiferroic materials. So one of the very common and cheap multiferroic is the bismuth ferrite multiferroic materials, where actually this is the rhomboidally distorted perovskite structure. And I think its Curie temperature is high, around 1103 Kelvin, and its antimonoclinic temperature of 643 Kelvin. And this has a spiral modulated spin structure, and the resulting magnetization goes to 0. And this is antiferromagnetic up to 643 Kelvin at room temperature. We just get a line, we don't observe any hysteresis loop. So early 2014, my students started to synthesize this type of materials by using very cheap technique, which is solid state reaction technique. And they have distorted the structure of this material, perturbed it by adding some other, by doping with some other materials, and which was gadolinium and titanium. And they found that for a particular concentration of this gadolinium and titanium, which is around 10%, a single phase of this material was formed, and this was 99% of this material was rhomboidally distorted perovskite structure. Later on, we have studied their magnetic properties, and we found that yes, at the center of this magnetic hysteresis loop, some weak ferromagnetism is created, and actually, so we can tune these magnetic materials, and some other properties like exchange bias effect and some other effects can be created with it, because they have this is the two-phase materials. This is antiferromagnetic dominated. Actually, weak ferromagnetism is there. So due to this two-phase, actually there are some exchange bias effect was present there, and we have studied it in detail. I will not go on that topic today. Rather, I will discuss something about how can we produce this material using some low energy technique, and we can produce them for energy harvesting applications. This material has another property which is known as the ferroelectric property, but this is very confusing actually. Most of the people we observe this ferroelectric hysteresis loop will publish it, but one of the very nice article was written by Jeffrey Scott, where Jeffrey Scott says that these are actually artifacts. Most of this electric hysteresis loop that you observed experimentally are the artifacts. Even you take a banana and take a hysteresis loop, you can get a hysteresis loop, and people see this hysteresis loop and they publish paper, those as papers. More than 100 papers are published. Even one paper was published in Nature, and now probably the total number of these artifacts publication exceeds a couple of hundreds or thousands. Okay, so we are interested to get some ferroelectric hysteresis loop of this material, and we found that actually if we control the leakage current of the material, that is the defect of the materials with low leakage current and low oxygen vacancies, this material, then we can observe a true hysteresis loop. Otherwise, it is very difficult to get a ferroelectric hysteresis or a true intensive hysteresis loop of these materials. So this is always a misleading investigation, and we performed investigation on number of materials, and we hardly found few materials which are actually truly ferroelectric. Anyway, so this was some introductory part of my talk. So then actually we think that if we produce this material by using the solid state reaction technique, this is a high temperature technique. Actually, materials go there, and it is almost very difficult to produce nanoparticles using that technique. Therefore, we have tried to develop a technique which is by using ultrasonic energy. And in this technique, actually, we use the precursor materials. Then we made them pelletized, and after pelletizing, we break this material, make them bulk powder, and then on the bulk powder, we mix them with some solvent and treat their ultrasonic energy. So after ultrasonication treatment of couple of hours or couple of minutes, actually, we got the nanoparticles. And if you look at some images, so this is the bulk material which was prepared by solid state reaction technique. The crystal structure of this material was nice, but they are bulk and they are actually they are highly agglomerated. And after ultrasonication treatment of just about 60 minutes by using a ultrasonic bath, which is very cheap actually, and its power was around 50 watt. So after 60 minutes, we got nanoparticles, which are the size of these nanoparticles as with the narrow distribution, and their size was around 10 to 15 nanometer. So we found that actually by using this ultrasonic energy, we can produce nanoparticles successfully. Then what we did actually, we think again, our initial material was developed by solid state reaction technique, which is a high synthetic temperature used. Then we changed this technique. Instead of using solid state reaction technique, we used the hydrothermal technique, where hydrothermal vapor capture was used. So by adding the nitrate materials, bismuth nitrate, iron nitrate, and gadolinium nitrate, and by adding the potassium hydroxide and deionized water, and we heat them in a hydrothermal reactor, and just heated them for by 160 degrees centigrade, and then centrifuge these materials, and we are successfully able to form the nanoparticles. And compared to the solid state reaction technique, the reaction temperature of hydrothermal technique is much lower. That is, in the solid state reaction technique, it is around 800 degrees centigrade, whereas in the hydrothermal technique, the reaction temperature was around 160 degrees centigrade. So these are the materials, and here we found some other interesting properties actually. This is the bulk material, and this is the bulk rate. So this is the material treated at 200 degrees centigrade hydrothermally, then 180 degrees centigrade, 160 degrees centigrade. And you look at here, just by tuning the temperature just by 20 degrees centigrade, if you go at 140 degrees centigrade, then we found that we can actually tune the phase of the materials. So up to this was perovskite type of materials, but below 20 degrees centigrade, that 140 degrees centigrade, the type of the material was selenide structure was formed. So in this way, we found that actually by tuning the temperature, reaction temperature, we can transfer from one structure to another structure, and this is reproducible actually. And you see at low temperature at 160 degrees centigrade, the morphology of these nanoparticles was quite promising, and it is the size of around 10 to 30 nanometer with a narrow distribution of their sizes. So then we again created them ultrasonically, and we have taken some TM images, and you see here, this is the TM images of these nanoparticles, and their size is around 10 to 15 nanometer. And this is the crystalline planes from the high HRTM images, and these crystal planes are very clearly visible. So actually, our purpose was to use these materials for solar energy applications. That's why we have done their optical characterization, and this is the UV visible characterization and the absorbance of these materials. This is the bismuth ferrite nanoparticle, and this is the gadolinium bismuth ferrite nanoparticle. And you see their band gap, direct optical band gap is around 2 electron volt. And for the BGF nanoparticles, that is gadolinium bismuth ferrite nanoparticles, it is band gap is around 1.18 electron volt. And we have taken some PL intensity, and from this intensity curve, actually, we can qualitatively say that so the recombination rate of gadolinium bismuth ferrite nanoparticles is much lower compared to its parent materials. Okay, so where you use these materials actually? One of the purposes is to use these materials as catalyst materials. So the ideal characteristics of catalytic material is their promising surface morphology, but we think that we have produced it successfully, smaller particle size and high surface to volume ratio, suitable band gap, which we also observed, and light absorption capacity to generate electron hole pair, and also separation of electron hole pair. So I think our synthesized nanoparticles actually meet most of these characteristics, and we have utilized these materials for solar energy applications. So first applications what we have tried is water pollution caused by the release of dyeing and painting liquids. So in subcontinent or even in Bangladesh or India or some other countries, there are lots of painting and dyeing industries. So from this painting industries or dyeing industry, lots of dyes are being mixed with water. And actually this textile dyeing and finishing industry is the second largest polluter of water globally, according to UNEP. So this is a global concern. Another concern is actually our pharmaceutical industries. So lots of antibiotics are found in the waste discharged by pharmaceutical factories into lakes, rivers, and the surrounding environment. Even some antibiotics like ciprofloxacin, enoxacin are detected at more than 1 microgram per liter in water. So this problem should be solved scientifically, and we tried to use our materials for the degradation of these industrial pollutants as well as pharmaceutical pollutants. And we actually established this setup where there was a 500 watt xenon lamp, which was used as a solar simulator, and we irradiated light, and we mixed catalyst with a common industrial dye, which is rhodamine B. And after magnetic steering, we have taken their absorbance curve, and we found that after absorbance of a couple of hours, actually around 3 to 4 hours, the dye was found to degrade. And we did it for two types of materials, for bismuth ferrite nanoparticles and gadolinium bismuth ferrite nanoparticles. For comparison, using the identical actually conditions, we used the titanium oxide nanoparticles as a reference. So compared to the commercially available P25 titanium nanoparticles, our synthesized materials actually showed a high degradation efficiency after about 240 minutes of solar irradiation. And our pseudo first order rate constant for this rhodamine degradation was also higher for these nanoparticles, which is BGF for nanoparticles. To check the reproducibility, we used another dye actually, which was methylene blue, and we got the same results. And after doing the dye degradation experiment, actually, we have taken again our XRD pattern, and we found that before using them as photocatalyst and after using around 5 degradation cycles, actually their structure was remained same, which actually shows the stability and recyclability of our materials. So then actually when you study the photocatalytic dye degradation, again, there is a confusion arises whether this is purely photodegradation or this is the dye sensitization effect, because rhodamine B is the colored dye and rhodamine B can themselves absorb the light photon. So we used a ciprofloxacin, an antibiotic, which is colorless and which is not actually, we cannot absorb photon directly. So using this antibiotic, that is ciprofloxacin and levofloxacin, we used our nanomaterials to degrade the ciprofloxacin and levofloxacin antibiotic, and we found actually almost 71% ciprofloxacin and almost 67% levofloxacin was degraded by BFO within bismuth ferrite nanoparticles within 240 minutes. Again, the degradation was much higher compared to the BFO for the BGF nanoparticles, and it was around 80% and 79% for within about 240 minutes of solar irradiation. So this actually gives us two information. One information is that our nanoparticles actually, what we observed here, this is purely photodegradation. This is not the dye sensitization effect. And secondly, that both the same nanoparticles can degrade both the industrial pollutants as well as the pharmaceutical pollutants. So then we checked their recyclability, and after 5 consecutive cycles of the irradiation, we found that the materials are their performance are almost same. Only a few percentage was degraded, but it was almost intake. So it actually shows their stability and reusability. Then to understand the mechanism actually of this degradation process, we did some scavenger test and used 4 different types of scavengers, and we found that actually for the degradation of rhodamine B dye, whole was the main principal reactive species responsible for this degradation of rhodamine B dye by bismuth gadolinium iron oxide nanoparticles, and hydroxyl radicals are the principal reactive species responsible for the degradation of ciprofloxacin by bismuth gadolinium iron oxide nanoparticles. So after doing the scavenger test, actually we went to, I'll show some other parts that actually we performed for the double perovskite materials, and this double perovskite materials was synthesized by soldier technique, and this is a flowchart of the soldier technique. Due to your time limit, I'm not describing it, but this is a very simple technique. And nanoparticles, double perovskite nanoparticles, we have synthesized these gadolinium iron oxide nanoparticles, and you see here there are the TM images. The size is around 40 to 50 nanometer, and their crystal plane is also really very promising. And this is the selected electron diffraction pattern. And this double perovskite actually has a very interesting property, and probably we are the first time, for the first time we are seeing some multiphasic behavior of this double perovskites at room temperature. So this is the hysteresis slope, magnetic hysteresis slope taken as room temperature. This is the ferroelectric hysteresis slope taken at room temperature, and both of the loops are exist at the same phase at the same temperature. And we think that in our theoretical some calculations also suggest that yes, this is the room temperature multiphasic materials, and this work is in process at the moment. Later on, our interest was to produce some metal halide perovskites. So this is a bit challenging to synthesize this metal halide perovskites. So some of my students actually established some facilities, and by hot injection technique where folic acid was used and some other ligand are used, and both ligands, oleic acid octadiamine, and cesium carbonate was added into a beaker, and it is stirred to produce the cesium tilchloride halide perovskites. So this was the cesium carbonate. We added with oleic acid, and another beaker they have tin chloride was added there with olediamine, and both actually was injected. This oleic acid cesium olate was injected into this beaker and heated it at around 1.5 hours, around 200 degrees centigrade, and simultaneously we passed there the argon gases, and then we cooled them using an ice bath, and after centrifugation and washed, we got the cesium tin chloride nanocrystals. And if you see here, this is the crystal structure of these nanocrystals, and the lattice parameter is around 5.583 angstrom. This is well meshed with the reported values, and this is the FESM image of these nanocrystals. So a paper was published in 2020, and this group also produced this cesium tin chloride nanocrystals, actually using a different technique actually. But we think that our nanocrystals produced by this hot injection technique is not bad actually. This is comparable. To some extent, we can say that it is a bit better, the morphology. So to understand it or to study it more, more professionally, we have taken some TM images, and we found that this is the cubic structure of these cesium tin chloride nanocrystals, and this is their crystal plane. And this actually gives us some encourage to use these materials for energy applications, and we are doing so. Already we did some experiment. However, just I would like to show you some optical characterization of these materials. Their band gap is around 2.98 electron volt. But if you see there's the steady state photoluminescence spectroscopy, and most importantly the time resolved photoluminescence spectroscopy, the quantum heat efficiency of this material is around 91%. So this is very promising actually for solar cell applications and other related solar energy applications. Finally, I will show a number of our speakers actually discussed about the hydrogen production, and all backgrounds were discussed. I will not discuss much more about it. And just I would like to say that, like others, we are also interested to produce hydrogen, carbon-free hydrogen, and we would like to do it by photovoltaic water splitting experiment by using the nanoparticles that we are synthesizing locally in our laboratory. And just one example we have showing here. This is the nanoparticles, lanthanum iron oxide nanoparticles, and we made them some composite of this lanthanum iron oxide nanoparticles with MOS2 molybdenum disulfide, and we produced the solar hydrogen by using this nanostructured composite material. And you see it, if you compare with this is the for titanium oxide nanoparticles, the evolution rate. This is for the lanthanum iron oxide this time, and this is for our composite nanomaterials. So we think that we can produce some hydrogen, but still we have to go a long way, and we are building up some facilities as well as the expertise for the evaluation of hydrogen. But some initial works are doing by our undergraduate students. I will not take much time. I am in just the summary of my research is just we have established some facilities and some expertise for the synthesis of perovskite nanomaterials by using some local and cheap technique. We use very cheap material for using them in the catalyst, but our main purpose was to produce the materials at very low temperature from energy consuming point of view. And we investigated their structural and physical properties, and we have demonstrated some application of these nanomaterials for environmental remediation. So these are the true contributors of my work. Actually, none of these work were done by me. These are the very young students, and they are mostly undergraduate and master students that did these experiments. All these works are their works. I have just presented it, and I'd like to thanks my donors and Tohoku University, Japan, for helping us for TM imaging. So if you have any question, I will be very glad to answer you. And if anyone would like to ask you later on anything, then please just send me an email. And thank you very much once again, the organizers, for inviting me. That's all for today from my part.
Thank you so much, sir, for this interesting and informative session. If there are any questions,
Professor Batit, I'm very happy to see you here. And
Thank you very much. Thank you very much.
Impressed by hydrogen production without carbon dioxide, solar hydrogen production, peroxide solar cell. how much work you do. You do a lot of work. And I want to say one thing, that our coordinator, convener of the conference, Dr. Chagan Lal, is a coordinator of in our center for perovskite solar cell. So if you like to collaborate, he is ready to do that.
That will be excellent.
Thank you for your lecture. And now after
You're most welcome.
the break, we'll have a validatory. So you will be here.
Yes, I'll be here. I'll be there. I'll be here.
If there are any other questions for Professor Basit, then you may interact here.
Thank you. Thank you very much once again.
Okay, so we'll be having a 5-minute break for everyone, and then we'll be back. We'll be back again. Till then, please be here with us.
सर की आवाज क्या बोलेगी? लिफ्ट करेगी?
दिनेश, सबसे पहले मेरा नहीं, सबसे पहले तो ये बोलेंगे ना, रिपोर्ट बनाएंगे, रिपोर्ट देंगे।
पहले रिपोर्ट देंगे सर, या पहले गेस्ट बोलेंगे? पहले बासित जी बोलेंगे।
कीनोट स्पीकर, कीनोट स्पीकर का पहले स्पीच वो देंगे या सर पहले रिपोर्ट? पहले सबसे पहले रिपोर्ट आप पढ़ोगे, फिर उनको स्पीच के लिए, फिर वोट ऑफ थैंक्स लास्ट।
और वो वेबसाइट पर दे दी अपने लिंक।
अच्छा,
और जो बेस्ट अपन बोल रहे हैं
ये भी
वेबसाइट पर। Okay, thank you. Good evening, everyone, distinguished guests, faculty members, colleagues, participants, ladies and gentlemen. On behalf of Energy Research University of Rajasthan, chapter. I would like to thank you all for attending this 3-day international conference on renewable energy. We hope that you all found the conference informative and worthwhile. The goal of this event was to provide a common platform for researchers from all over the world to present their cutting-edge findings in the field of renewable energy. The conference was organized under more than 8 different themes such as hydrogen energy, solar energy, advanced nanomaterials for energy application, sustainable energy and development, energy and management, green energy technologies, energy harvesting technologies, wind, bio and geothermal energies. Professor Rajiv Jain, Honorable Vice Chancellor, University of Rajasthan, Jaipur, India, was patron of this conference. Professor I.P. Jain, Founder Director, CNCER, University of Rajasthan, Jaipur, was the honorary chairman of the conference. Professor S.N. Dolia, Present Director, CNCER, University of Rajasthan, Jaipur, was the chairman of the conference. Dr. Manisha Gupta, Dr. Mamraj Singh, Dr. Amanpal Singh were the organizing secretary of this international event. This conference was organized by was inaugurated by Professor Ibrahim Dinser from Ontario Tech University, Oshawa, Ontario, Canada, the chief guest of the conference. He delivered his plenary keynote lecture on new integrated biomass energy systems for multi-generation. Professor John William Sheffield from USA delivered his keynote talk on green hydrogen, a global perspective of technologies. Eminent speakers around the globe, expert in their field, enlightened this conference with their lifelong knowledge. Professor Bobet from France on hydrogen generation from waste, MG Alloys light mobility. Dr. Daniel from Italy, his talk was on magnesium-based material for sustainable energy storage applications. Professor Basit from Bangladesh talked about perovskite nanomaterials for efficient photodegradation and solar hydrogen evolution. Dr. S. Rama Prabhu from IIT Madras talked about nanomaterials for energy applications. Professor Sharif talked about advances in energy efficiency and achieving net zero energy in the invited states. Professor Mondal from USA talked about net zero carbon emission in the electricity and transportation fuel sector. Professor Yogendra Kumar Mishra from Denmark talked about tetrapods based smart material for advanced technologies. Dr. Panos from Japan gives talk on nanoparticle scaffold for multi-layered silicon-based lithium-ion battery anodes. Dr. Dinesh Patak from West Indies talked about fourth generation photovoltaics, hybrid materials. Dr. Ranveer Singh from South Korea talked about ultra-fast optoelectronic devices, hot carrier generation and injection. Dr. Satpati from Poland gives talk on described to predict dye synthesized semiconductor-based photocatalyst for hydrogen evolution reactions. Dr. Dinesh Topwal from IOP Bhubaneswar gives talk on new generation of photovoltaic materials, understanding the fundamentals. And Dr. Rajendra Singh Dhaka from IIT Delhi gave talk on development of 2D materials as anode for sodium-ion batteries. Dr. Sushant Kumar from IIT Patna, Bihar, India talked about tri-phase photocatalyst for CO2 reduction and nitrogen fixation with efficient electron transfer on a hydrophilic surface of transition metal duct, Mill 88 iron. Dr. Kamil from Poland gives talk on the physiochemical properties of a high entropy nanocrystalline oxide developed for application in hydrogen technologies. Dr. Balaji from IIT Tirupati gave talk on wind energy opportunity and challenge. Beyond of these invited talks, more than 350 researchers, faculty members, research scientists around the globe were participated and presented their papers under the different themes of the conference. The conference being held in 5 technical sessions in addition to 14 parallel sessions. The first oral session was chaired by Dr. Ravinder Jangid, RR CAT Indore, India, and Dr. Sushant Kumar, IIT Patna, India. Second oral presentation session was chaired by Dr. Ranveer Singh from South Korea and Dr. Vidyadhar Singh from JP University, Chhapra, Bihar, India. And the third oral presentation session was chaired by Dr. Brahmananda Chakrabarti from BRC, Mumbai, India, and Professor Ghanshyam Sharma from Kota University, Kota, India. And last oral session was chaired by Professor Rajesh Kumar from Indraprasth University, New Delhi, India, and Professor Kedar Singh from Jawaharlal Nehru University, New Delhi, India. The poster presentation was chaired by Dr. N.K. Acharya, MS University, Baroda, Dr. Vaibhav Kulshrestha, CSIR, CS, MCRI, Bhavnagar, Gujarat, Dr. Chandrasekhar Tripathi, BHU, Varanasi, and Dr. MP Sharma, Guru Ghasidas University, Bilaspur, Dr. KC Bhamu from South Korea, Dr. Dinesh Kumar, Dr. Sunita Mawar, Dr. Narendra Jakhad, Dr. Dalpat, Dr. Manisha Gupta from Department of Physics, University of Rajasthan, Jaipur. Professor M.A. Basit was the chief guest for the valedictory function and he delivered his keynote lecture also. And now we welcome Basit sir for the valedictory speech also. In the valedictory session, all the sessions were conducted and the certificates were distributed to the participants. Once again, I thank you, all of you, for this event. And I thank you all for joining this event. And I think you really enjoyed this 3-day event. And after summing of this conference summary, I really thank you to all of you being with us. And Jai Hind.
Hello. Yes, am I audible?
Yes.
Hello?
Yes, sir, you're audible.
So can I start my speech? Is it now? Yes, okay, thank you. Okay, thank you very much once again for giving me this opportunity. Ladies and gentlemen and dear organizers, a very good afternoon from Bangladesh. Since my childhood, I have felt an unknown pleasure within my heart hearing the name Rajasthan. I always felt that this place is not the same as many other places of this subcontinent. Rather, it is the heaven on earth. Right now, we can say confidently that Rajasthan is definitely one of the most beautiful, old and colorful states of India. So far, I know University of Rajasthan was set up on 8 January 1947, exactly 6 years and 11 months later, after the birth of Jagadit Singh, the king of Ghazals, who was born in Ganganagar, Rajasthan. Mr. Ashok Kumar, a former hockey player of Indian team, was an alumnus of the University of Rajasthan. He was a key member of the Indian hockey team that won the World Cup in 1975. In the same year, I was born in the eastern part of Bangladesh, which is very close to Silchar, the headquarters of Kashar district of the state of Assam, India. It is indeed a lifetime experience for me to be a part of this second international conference on renewable energy organized by the Center of Non-Conventional Energy Resources, University of Rajasthan, India, in association with the International Association of Hydrogen Energy USA and Materials Research Society India, Rajasthan chapter. I am honored and thankful for providing me this opportunity to deliver a keynote speech and also to allow me speak in this valedictory function as a chief guest. I must thank and congratulate the organizers for successfully organizing such a notable conference. In this conference, there were 8 keynote speeches and 9 invited speeches, along with other oral and poster presentations, where speakers presented their cutting-edge findings in the field of renewable energy. I came to know about this conference from Professor I.P. Jain, and I was really astonished looking at the theme of this conference, which are hydrogen energy, storage, production and applications, solar energy, perovskite solar cells, advanced nanomaterials for energy applications, sustainable energy and development, green energy technologies, energy harvesting and technologies, wind, bio, and geothermal energy. All these topics are very demanding in this 20th century and have enormous impact on the daily life of mankind from developed to underdeveloped countries. It is well known to us that hydrogen generation via gasification of fossil fuels is inefficient since it involves complicated post-processing steps and emission of harmful carbon dioxide. Therefore, the production of hydrogen using renewable energy is gaining sincere attention among the scientific community because they are simple, efficient, and have significant potential for future development. Because of its low cost and environmentally friendly nature, hydrogen has emerged as the most feasible substitute for traditional fossil fuels and as the most promising green and efficient energy source with high energy storage capacity. Therefore, I can certainly say that the organizer was extremely thoughtful to organize this international conference on renewable energy. Their aim was to create collaborative links between researchers, scientists, academicians, and industrialists to share knowledge and host discussions of highly relevant issues of the energy. I had listened to a number of speeches delivered by renowned scientists in their respective fields, and I can say without any reservation that this is a very successful conference. I hope we'll go back soon to a normal life, and the University of Rajasthan will arrange physically the 3rd International Conference on Renewable Energy in near future. We will be there to participate in that conference, and definitely will not miss the opportunity to visit the attractions of Jaipur like Albert Hall, Hawa Mahal, Jal Mahal, etc. Once again, my heartiest gratitude to the organizers to invite me, to give me this opportunity. I'm really honored. May God bless you all. Thank you very much once again. Thank you. That's all from my part.
Thank you so much, sir. Now I would like to invite for the feedback session Renu Kumari and Jeet Kumar. Renu Kumari and Jeet Kumar.
Hello.
Sorry, Jeet Sharma. I repeat again. Renu Kumari and Jeet Sharma, you are invited for the feedback.
Yes, hello, I am available.
Yes, ma'am.
Okay. Firstly, I will thanks to team
Ma'am, is it
organization
possible
of.
to turn on your video?
Yes, ma'am. So firstly, I want to say thanks to committee members of ICRE 2022. It's a very nice conference and very informative sessions, and also it was very it was very it was very good and also very knowledgeable. Thank you and best of luck.
Thank you so much, Renu Kumari. Now I would like to call Rajan Pandey for the feedback views. Rajan Pandey, are you willing to share your thoughts about our conference?
Anybody else? Generalize कर दो. कोई भी. Anybody else? Anybody else?
Dear audience, if anybody wants to give the feedback views about our conference, then they are most welcomed. And if you want to give any suggestion for improvement, then also you are most welcome.
Hello, can I audible?
Yes, ma'am, you are audible.
Here I am Dr. Rashmi Saxena from Jaipur. मैं ये कहना चाहती हूँ क्योंकि मैं यूनिवर्सिटी ऑफ राजस्थान से ही मैंने अपनी पीएचडी करी है कंप्लीट, और मुझे यहाँ पे जो भी कॉन्फ्रेंस होती है अटेंड करना बहुत ही अच्छा लगता है। और ये आईसीआरई जो कॉन्फ्रेंस हुई है ऑनलाइन, उसमें इतने लोगों का जुड़ना और इतनी नॉलेजेबल चीज़ों का हम लोगों को देखना बहुत ही अच्छा लगा। ये बहुत ही इंफॉर्मेटिव थी और मैं ये एक्सपेक्ट करूँगी कि अगली बार हम लोग सब फिजिकली प्रेजेंट होके इस कॉन्फ्रेंस को आगे और इन फ्यूचर में और अच्छे से इसको अरेंज करें। और जो बाहर से गेस्ट जिन्होंने अपने लेक्चर्स दिए उनका भी जुड़ना, तो ये हम लोगों के लिए रिसर्च स्कॉलर्स और एज अ फैकल्टी हम लोगों के लिए बहुत ही नॉलेजेबल रहा। सो थैंक यू ऑल द टीम एंड बेस्ट ऑफ लक। थैंक यू सो मच।
Okay, thank you so much, ma'am. Anybody else who want to share your views? Isn't our conference was interesting?
Hello, myself.
Yes, it was very interesting.
I'm from the Assam. Yeah, the conference was great actually. First time I attend the conference, who basically is dedicated to the hydrogen energy generation and storage. So this is very informative one. This is the new the type of the energy generation. This is maybe the future the energy, and the conference are totally dedicated to this theme. It is great. I like to suggest one thing is that when I'm talking about the renewable energy, basically one part I always made it is that it is called a solar cooker, and more on the renewable energy conference, some has a theme like the solar cooker generation, and now this is area actually totally no one is doing any initiative to do the solar cooker research. So if this theme is included in this conference, it would be great in future. So this is from my side. Thank you again. Thank you.
Thank you so much, sir. Now moving forward, as someone said, quitters never win and winners never quit. With this note,
I wanted to give feedback. Can you allow me?
Casey Bahamu. Are you interested in saying something?
Yes. So first, I would like to say thank you to Professor I.P. Jain sir, and Dr. Chagan sir, Dolia sir, and entire team of this conference for providing a wonderful platform to discuss ideas. So it was really a very nice conference where we were lucky to have eminent speaker from all the world, from Italy, Poland, Denmark, and then Bangladesh, and Rajendra Dhaka from IIT Delhi. So all the lectures were very informative. So overall, I have my 100 by 100 marks for this conference. So I have one feedback that most of the talks were from I can say that all the talks were from the experimental guys. So for the next conference, it would be better if you include a few sessions or few talks from theoretical people, so that we can join together. I'm always happy to hear that both the sessions from the experiment and theory. So if you join the theory and experiment, then it's better for participants also. Yeah, thank you.
Thank you so much for your suggestions and views. Okay, then moving forward, I would like to welcome and invite Dr. Manisha Gupta, Organizing Secretary of International Conference on Renewable Energy 2022, University of Rajasthan, to deliver the vote of thanks.
Very good afternoon to all. Ladies and gentlemen, it is my privilege to have been asked to propose a vote of thanks on this occasion. On behalf of the entire team, ICRE 2022, and my own behalf, I would like to take this opportunity to extend the most gracious thanks to all the speakers for gracing your important words and sharing with us your experiences and opinions. We are fortunate to have eminent delegates speaker from various universities, international and national institutes, laboratories working in areas of renewable energy. I am sure that participants have benefited by attending the conference. We also express our appreciation to Honorable Vice Chancellor, Professor Rajiv Jain, for this his continuous support and advices which have greatly helped towards the successful organization of ICRE 2022. We are grateful to our chief guest of today's valedictory function, Professor M.A. Bassett, Department of Physics, University of Engineering and Technology, Dhaka, Bangladesh, for kindly accepting our invitation and gracing this valedictory session, and also for accepting our invitation for keynote talk. I am very much thankful to International Association of Hydrogen Energy, USA, and International Journal of Hydrogen Energy, IJHE, for sponsoring this international conference, and MRISI Rajasthan chapter for their association. Without their generous support and association, it would not have been possible to organize the conference. I also wish to express my gratitude to Professor I.P. Jain, Honorary Chairman, ICRE 2022, for taking the initiative for hosting the conference at CNCR, University of Rajasthan. Special thanks to Professor S.N. Dolia sir, Chairman and Director of CNCR, for his flawless logistic support and guidance to make this event successful. I must mention our deep sense of appreciation for Dr. Chagan Lal, convener of ICRE 2022, for his untiring work and dedication, who remained always on his toes for making this international conference a successful and memorable one. We are also grateful to conference advisory members who have shared their valuable insight for organization of this conference. We are also thankful to Head Department of Chemistry for providing the technology hall towards organizing this event. I take this opportunity to express my gratitude to all invited speakers who have open-heartedly accepted our invitation in a very short time and graced the event with their presence. The success of this conference depends on the efforts of many people. We have been fortunate enough to be backed by a team of highly motivated and dedicated colleagues of Department of Physics of University of Rajasthan, who know their jobs and are result-oriented. We acknowledge the support received from our Department of Physics HOD, the faculty members and the staff members. We also express our warm appreciation to all the research scholars who have greatly helped us in organizing the conference. I would like to express a sincere thanks to media team also for giving an excellent coverage for this conference. I cannot thank everyone enough for their involvement and their willingness to take on the completion of task beyond their comfort zone. I know due to pandemic situation all over the world, all would be missing our pleasant weather of the Jaipur and historic monument of this Pink City Jaipur. But I'm sure you all enjoyed the academic sessions, discussions during the conference a lot. As the nature laws, every good thing has come to an end. So as our conference is, but as we all know, renewable energy is continuous and sustainable, and we make sure that in future also we would try to organize more of such event. And Dr. K.C. Bamu, we have noted your point. In future, we will try to include some theoretical researches also, so that all theoretical and experimentalists can enjoy this event. And in the last, especially I would like to thank the three anchor girls. So they were all time at their toes, without any break, without any tea break or without any lunch break. They remained there. So I'm very much thankful to them also. And their names, I would like to announce their names also. Rachita, Garima and Pooja and Shivani from Environment Department of University of Rajasthan. One more important announcement I have to make here. We have extended the date of full paper submission till the March 15th of 2022. Okay, so you may submit your full paper till 15th of March of this month. And also all the results are also available on the website. You may check the website all the time and be updated further amendments or further updated information. So keep in touch in the website, and we would surely meet in the next year also with the same great some event. Also, I would like to thank Dr. Pankaj from Department of Environmental Sciences of University of Rajasthan for their great help. And also Dr. Parma E. Solomon for their untiring or unconditional support all the time. Thanks a lot. Thank you very much. So with this, I would now hand over this mic to the anchors. Shivani.
The certificates will be provided after 3 days on the email IDs. Further details regarding the abstract book and the conference is available on the university website. The date for the submission of the paper is extended till 15th March 2022. If there are any suggestions from your side, you are free to give it on the Telegram group or the email ID of ICRE. Thank you.
अभी अनाउंस करने के विनर्स कर दो सर, आप कर दीजिए मोस्ट। हाँ, मैं कर नाम वो लिस्ट दे दो मेरे पास एक। हाँ, ये
As we earlier said, quitters never win and winners never quit. It's all about participation and how much you learn and grow. With these lines, I want to request our team to announce the winners of our conference presentations.
This is the most awaited moment which I have reached for the announcement of best presentations. Out of so many presentations, all these 3 days, we have some best presentations. I'm announcing those names here. The first name is Nicholas Kirali. His ID is 05190. Am I clear to all? And next one is Dr. KC Bamu. ID is 05184. Renu Jagdish. ID 04165. Savan K. Raj 03139. Sandeep Sharma 0105. Rajita 0104. Shivani 07278. Garima 07282. Jyoti Vaishnav 03122. Nattulal 03146. So with this, I would like to congratulate all the best presentations and thanks all.
Congratulations, all the winners. It's a very proud moment. And in the last, I want to thank everyone. I express a heartfelt gratitude to all the eminent speakers, participants who were sincerely committed to this event to make it a success. This event would not have been possible without your support. So thank you everyone for staying with us for these 3 days. Thank you very much. And continuously keep visiting our website for further instructions and informations regarding abstract or paper and any other informations. Thank you. And see you all in the next conference, ICR 3. Thank you very much.
Switch off हो गया क्या?
If anybody have any kind of suggestions or views, then you can share us or write us on our emails. Thank